Hey everyone, welcome to the course on Mastering Kotlin for Android development. In this engaging series, you're going to learn how to create compelling apps using Kotlin. We're diving deep into the MVVM architecture, exploring Jetpack libraries, and getting our hands dirty with asynchronous programming using Kotlin coroutines. So buckle up for some fun hands-on coding exercises. And oh, don't forget to check out the GitHub repository in the description. It's got all the code we cover in the series. Make me stick around until the end because you'll have the opportunity to showcase your skills with a final project that will be available right there in that same repository. Now, let's jump right in and get started. To dive into the thrilling world of iOS app development, we are going to explore Xcode, Apple's integrated development environment, often called IDE. Now, this powerful tool isn't just where you write code. It's really where creativity meets functionality. Today, we're going to guide you through downloading, installing, and familiarizing yourself with the Xcode interface. And guess what? We'll even create your very first app. So buckle up, the journey has just begun.
All right, let's dive in and get Xcode set up on your Mac. First things first, head over to the Mac App Store. Just type in Xcode in the search bar and hit that download button. It might take a few minutes, so why not grab a snack or, I don't know, check your social media while you wait.
Once it's downloaded, go ahead and follow the installation prompts. Should be pretty straightforward. Then open up Xcode and let's get familiar with its user interface. You'll see this welcome window pop up, giving you options to create a new project, open an existing one, or dive into some tutorials. Now, navigating this user interface can seem a bit overwhelming at first, but no worries, we'll break it down together. On the left sidebar, that's where you'll find the Project Navigator, which shows all your files and resources. The editor area is in the middle, where most of your coding magic is going to happen. And on the right side, you have the Utilities area. This is your go-to spot for quick access to properties and controls that will help you manage your project effectively. There we go. Let's get started.
The figure displays a bar chart titled Time Required for Key Steps in iOS Development with Xcode. That quantifies in minutes the typical duration for 5 sequential tasks. Download Xcode, which takes about 5 minutes, install Xcode, around 10 minutes, create project, just 3 minutes, run in simulator, 7 minutes, and finally run on device, taking a bit longer at 12 minutes. From these values, we can spot some clear patterns. Creating a new project is definitely the quickest task, clocking in at just 3 minutes. While preparing and testing on a real device, well, that's where things get a bit more demanding at 12 minutes. Now, installation and device deployment really stand out as the two primary time sinks. Installation takes about 10 minutes, which is roughly double the time it takes to download, sitting at just 5 minutes. And running on a physical device takes noticeably longer, 12 minutes, compared to the simulator, which is only 7 minutes. These differences bring some practical planning considerations to mind. You'll want to allocate extra time for that initial setup and for doing your device testing, definitely. And you can expect those iterative development cycles to be significantly influenced by deployment and verification on actual hardware. So when you're estimating your development sessions, make sure to budget a modest amount of time for project setup, moderate time for the simulator-based checks, and the most time for installing tools and validating behavior on real devices. Now, let's get our hands dirty and create our first iOS app. Click on Create a New Xcode Project from the Welcome window. A new window will pop up with various app templates to choose from. For simplicity, let's select the app template under the iOS section. Click Next and fill out the necessary fields like product name, team, organization name, and organization identifier. Be sure to choose Swift as your programming language and Storyboard for your user interface. Now click Next, choose a location to save your project, and click Create. Voila, your very first iOS project is ready. To give your app a little personality, let's add a simple user interface. Open the main.storyboard file and you'll see an empty view controller. Let's drag a label from the object library, yeah, that's the panel on the right, onto the view controller. You can double-click the label to edit it. Let's say we'll put Hello World in there. Feel free to adjust the font size and color in the Attributes Inspector. And voila, you've just added some flavor to your app.
Now, let's see how we can implement changes to our label when the view first loads. In the viewDidLoad method, which is called after the view has been loaded into memory,
We'll begin by invoking the superclass's implementation with super.viewDidLoad. This ensures that the parent class performs any necessary initial setup before we apply our customizations. Next, we'll directly access our greeting label outlet that we created earlier and set its text property to Welcome to iOS Development. This is where the magic happens. The text displayed in the label on the screen will now update dynamically to reflect this new message, instead of just the familiar Hello World. By modifying the label in this method, we guarantee that the new greeting will appear as soon as the view presents itself to the user, effectively enhancing the interaction and user experience right from the start. Feel free to customize the text further to suit your app's theme. This is an excellent opportunity to get creative and bring your own personal touch to your iOS application.
Let's take a moment to run our app in the simulator. You can do this by selecting the simulated device from the drop-down menu at the top of the Xcode window. You'll find options like the iPhone 14, iPhone SE, and a whole bunch of others. Once you've made your choice, go ahead and click that play button. Watch as the magical world of your creation springs to life in the simulator. It should display your label along with your custom message. Now, keep in mind that testing in the simulator is super handy for quick checks. But you might really want to see how your app performs on a real device. To do that, you'll need to connect your iOS device to your Mac via USB. Just make sure you've enabled developer mode on your device first. Once you've got that set up and connected, it'll pop up in the device dropdown in Xcode. Just select it and run the app again. This time, you're testing it live.
Next, we will implement the action method that responds to the button press. This method is marked with the @action keyword, which connects it to the button we created in the storyboard, allowing it to respond to user interactions. The method takes a parameter, _sender uButton, which represents the button that triggered the action. Now, let's see how we change the label's text within this method. Inside the body of change greeting, we access our previously created label outlet, greeting label, and set its text property to you press the button. This action updates the interface dynamically whenever the button is tapped, providing immediate feedback to the user. By doing this, we effectively link user input to a visual response in the app. Aha! It demonstrates the fundamental concept of event handling in iOS development, enabling you to create an interactive user experience. As a result, when you run the app and press the button, you'll witness the label's text change, reinforcing the idea of how actions can control the app's behavior based on user engagement.
At this point, you're not just a spectator, you're an iOS developer. But let's not stop here. Oh no, we can add even more functionality to our app by introducing navigation. For instance, we can create a new screen that details the subjects you've learned about iOS development. This can be done by creating a new view controller along with a navigation controller. To start, drag another view controller from the object library onto your storyboard. Now, we need a way to navigate to this new screen, right? First, we'll embed our initial view controller with a navigation controller. So, select your initial view controller, then head over to the menu and click Editor, then Embed In, and select Navigation Controller. This action will create a new controller connected to the original one. Next, let's create a button on your original screen that will take us to this new screen. Control-drag from the button to the new view controller in the storyboard, and when you let go, select Show to create a segue. With the segue established, selecting this button will now take you right to your new screen. How cool is that?
Now, let's implement the Detail View Controller class, which will be used to display detailed information. This class inherits from UI View Controller, which is a fundamental building block of iOS apps. Here, we define a variable named detailMessage of type string?, which is optional, and will hold the information passed from the previous view controller. Next, we override the viewDidLoad method. This is where we can perform additional setup after loading the view. It's an ideal spot to set the label's text based on the detailMessage variable.
while the actual implementation for updating the label is left blank in this snippet. It's your chance to customize how this data is presented to the user. Now, let's see how we can pass data between view controllers using the prepare for sender method in the original view controller. In this method, we check if the segue is the one we expect by matching its identifier. If it is, we cast the destination view controller to detail view controller. This allows us to access the detail message property directly, where we can assign it data from the first screen, creating a seamless flow of information in your app's navigation.
As we wrap up, always remember that app development is a continuous learning journey. Like, seriously. Explore building different interfaces, implementing various features, and most importantly, don't hesitate to troubleshoot. Be curious, persistent, and creative. Xcode offers a plethora of resources, such as documentation, forums, and tutorials to help guide you along the way. And keep in mind the importance of testing your app regularly, both on simulators and real devices, to ensure that everything functions as it should and performs smoothly. And don't overlook user feedback. It can be truly invaluable. As you continue coding, remember that every great app you use today started out as a simple idea when someone turned on Xcode for the very first time. So with that, you now have a solid foundation in Xcode and iOS app development. Get out there and start building something amazing. Happy coding!
To successfully run and trust your iOS app on a device, it's essential to understand how the Developer Ops Certificate plays a critical role. This certificate is a special file that's installed on your iOS device alongside your app, allowing it to be signed and trusted by the device. In this lesson, we're going to delve into the details of Ops certificates, device provisioning, and the steps to run your iOS app on a physical device. So far, we've learned about setting up Xcode, Apple's IDE for iOS app development, and how to create our first app. We've explored the user interface, added a label and button, and learned how to connect them to our code for interactivity. We also navigated between view controllers and passed data between them, which laid down a strong foundation for app development. Just a quick reminder, remember to test regularly and keep learning as you continue your journey in creating amazing applications. Now, let's cover how to run your app on an iOS device while making sure it's trusted and set up correctly. Let's start with how to obtain a Developer App Certificate. This process typically begins on the Apple developer website, where you'll need to enable your developer account. Just to get started. Once you're logged in, you'll want to navigate to the Certificates, Identifiers, and Profiles section. Here, you need to create a new certificate by selecting the appropriate type based on your app's needs. The two common types are development and production certificates. Now, for our purposes, we'll focus on the development certificate. To create this certificate, you'll need to generate a certificate signing request, or CSR, using Keychain Access on your Mac. So, open Keychain Access, and from the top menu, select Certificate Assistant. Then choose Request a Certificate from a Certificate Authority. You'll fill in your email and name, select Save to Disk, and then click Continue. This action will give you the CSR file that you'll upload to the Apple Developer Portal. And that's it, you've got your CSR. You're well on your way to setting up your Developer App Certificate. The accompanying pie chart titled Importance of Certificate Types and Trust in iOS App Development displays 4 categories and their relative importance. Development Certificate at 40%, Production Certificate at 30%, Provisional Profile at 20%, and Device Trust at 10%. Now, if we take a closer look at this chart, it's clear that the development certificate carries the largest single share at 40%, indicating that it's the most emphasized element in day-to-day development workflows. Following that, we have production certificates at 30%, and when we add those two together, we account for a whopping 70% of the depicted importance. This really highlights that certificate management, particularly for development and production, absolutely dominates the overall focus. Now, provisional profiles, well, they represent a meaningful but smaller portion at 20%. This signals that device provisioning and profiles are important for enabling those device-specific installs. Lastly, we see device trust as the small smallest slice at 10%, which shows that while trusting the developer identity on the device is necessary, it occupies a smaller fraction of the overall certificate and profile concerns. These proportions suggest that we should prioritize certificate creation and correct signing first, then move on to provisional profiles, and finally ensure that device trust steps are completed. Now, let's take a look at how to determine whether automatic signing is enabled in Xcode. So, the code snippet that we're working with begins with a conditional statement that checks the value of the auto-signing enabled variable. If this variable is set to true, the application will print a message saying automatic signing is enabled. This feature really simplifies the signing process because it allows Xcode to manage the signing identity and provisioning profiles for your app automatically, which is particularly beneficial for new developers who might find managing certificates and provisioning profiles a bit daunting. Now, on the flip side, if auto-signing enabled is false, the output will indicate that manual signing will be required. This usually happens when developers prefer to take the reins, handling the signing processes themselves for greater control over which certificates and provisioning profiles are used. Understanding this code is essential for developers, so they can be aware of their app's signing state before running it on a physical device. This knowledge ultimately guides them on the necessary steps to ensure the app is properly signed and, trustable by the device. Getting this right can really help prevent potential deployment issues, making it a core component of the app development workflow.
Once your device is connected, you may need to trust your developer certificate on the device. To do this, head over to Settings on your iOS device, navigate to General, and scroll down until you see Device Management. Find your developer app certificate there. Select it, then tap Trust Your Developer Name. This step is crucial because it establishes the trustworthiness of your app, allowing it to run smoothly on your device without any hiccups. All right, with everything properly set up, you're ready to run your app. Just choose your physical device from the list of targets in Xcode and press that Run button. Xcode will compile the app, install it on your device, and launch it. And voila, you should see your app pop up on your home screen, ready to be used. For those of you who are curious about managing different types of builds, it is indeed possible to designate a debug or release build. In the project settings, under Build Settings, you can configure various build configurations. This is where you can specify which ones correlate with development and production builds. Pretty neat, right?
Now, let's take a look at how we can check for network availability within your app, which is crucial for ensuring smooth functionality, especially if it relies on internet access. So to start, the code begins with importing the necessary connectivity manager from Android's networking library. This manager serves as the gateway for accessing information about network connections. Next, we define a function called isNetworkAvailable, which takes a connectivity manager instance as a parameter. Within this function, we retrieve the current Octave network information using connectivitymanager.octavenetworkinfo. Now, this property provides details about the network connection currently in use, if any. To determine if the device has an active internet connection, we're going to check if network info is not null and if the device is connected. If both conditions are met, the function returns true, indicating that network access is available. This simple yet effective method enables developers to incorporate connectivity checks into their apps, allowing for better handling of potential network issues, sounding reassuring, and enhancing user experience by adapting to the current connectivity state. The process of running and trusting your app comes with its own set of potential hurdles. For instance, errors can occur if the provisioning profile doesn't match your app's bundle identifier. So always double-check that the bundle identifier matches the one specified in your Apple developer account. Updating your identifiers takes only a few clicks in the Certificates, Identifiers, and Profiles section of the developer portal, and it's super easy. Now, debugging can also add another layer of complexity. Thankfully, Xcode provides a robust debugging toolset that allows you to set breakpoints and view the console output. Using the debugger helps you inspect app behavior in real time. It's a fantastic way to figure out where things may be going wrong and to ensure that your app is functioning as intended. Enhancing user experience is another critical aspect while testing your app, so pay attention to how your app responds to various gestures and inputs. Regular testing on different devices can reveal issues related to different screen sizes and orientations that you might not encounter on your simulator, so don't skip this crucial step. Finally, after successfully running and testing your app on your iOS device,
Remember to distribute it effectively, especially if you plan to share it with others. One great way to do this is by using TestFlight for beta testing. This platform makes it super easy for your peers or clients to install the app and give you valuable feedback on its usability and performance. Now, creating an effective beta testing strategy is crucial. Make sure you provide clear instructions alongside the app link, detailing exactly how your testers can install the app and report any issues they encounter. And remember, always listen to feedback during this phase, as it can really highlight areas for improvement. By now, you should have a clear understanding of how to run and trust your iOS app on a device, along with the steps involved in setting everything up. The key components include working with developer ops certificates, provisioning profiles, and efficient testing practices. Each of these plays a vital role in ensuring that your app runs smoothly on physical devices, ultimately paving the way for successful app deployment in the real world. In summary, we've gone through the essential steps for iOS development, which include obtaining a developer app certificate, setting up provisioning profiles in Xcode, and the crucial steps for running your app on an iOS device. We also dived into debugging practices and explored how to ensure a smooth user experience by thorough testing. Now, I know at first glance, the world of iOS development can seem a bit daunting, but trust me, with a little practice and a sprinkle of patience, you'll really start to master the art of creating and delivering amazing applications to users everywhere. So, keep pushing those boundaries. And remember, the most important part is to enjoy the journey of development. Congratulations! You've just created and run your first iOS app in the simulator. That's an exciting milestone, and today we're going to dive deeper into making the most out of this experience while exploring some handy features, enhancements, and techniques to further your journey as an iOS developer. So far, we've learned about the importance of the Developer Ops Certificate and the steps required to set it up for running an iOS app on a physical device. We explored how to create a development certificate, configure Xcode with provisioning profiles, and verify the app's trustworthiness on a device. Additionally, we discussed debugging techniques and best practices for testing, ensuring a smooth user experience. Through these processes, we've laid the groundwork for successful iOS app deployment and development. Now, we'll cover running your app, troubleshooting common issues, and implementing improvements to enhance functionality. So, let's get started. First things first, when you're running your app, always make sure to look out for unexpected behaviors. It's pretty common to hit snags, like those pesky warnings during development. Just remember, they're there to help you catch potential issues. Now, in terms of troubleshooting, if something doesn't work as expected, don't panic. Start by checking your console logs. They can give you hints on what's going on. Now, let's talk about enhancements. Consider implementing user feedback mechanisms to improve your app over time. Engaging with your users directly can reveal invaluable insights. All right, so as we journey forward, keep experimenting. Try out different features, and don't hesitate to reach for the documentation whenever you need clarity. Remember, even seasoned developers rely on guides. With each step, you're going to build your knowledge and skills as an iOS developer. So embrace the learning process, and let's keep moving forward. Let's kick things off by exploring how you can run your app in different scenarios. You've probably been working with the simulator, which is a fantastic way to test your app without needing a physical device. But let's not forget, testing on a real device is crucial. When you run your app on an actual device, you truly get to feel how it interacts with the hardware, how it manages battery life, and of course, its performance under real-world conditions. So to run your app on a real device, it's pretty straightforward. First, just make sure your device is connected to your Mac and it's trusted. Next, open your Xcode project. And now here's the fun part. Select your device from the device list in the Xcode toolbar, and then just click that play button. This will compile your app and deploy it directly to your device. Easy peasy, right? The accompanying figure titled Key Concepts in iOS App Development presents a ranked distribution of focus areas by importance, which is expressed as percentages. Now, the tallest bar corresponds to running the app on device at 35%, indicating that testing on physical hardware is, well, the single most emphasized activity. The second largest bar is running the app on simulator at 25%, showing that simulator-based testing remains a significant but secondary focus. Then we have debugging techniques sitting at 15%. This highlights that active debugging receives notable attention, though still less than direct testing. Logging user actions registers at 10%, suggesting that instrumentation and runtime logging are indeed important practical tools for understanding user behavior. Lastly, user feedback integration, error handling, and continuous learning, each at 5%, form a lower tier that still represents essential, ongoing commitments. From these values, we can conclude that practical execution and observation, like device and simulator testing, take priority. Meanwhile, the diagnostic practices, which include debugging and logging, serve as substantial supports. The smaller allocations for feedback, error handling, and learning underscore that these responsibilities are continuous and should not be neglected, even though they receive fewer immediate resources.
Now, there's nothing quite like the anticipation and, let's be real, the tension of launching your app for the very first time on a real device. You might feel super confident, thinking you've covered all your bases, but things can sometimes go a little sideways. One common issue you might run into is, you guessed it, code signing errors. These usually pop up when Xcode is a bit lost and can't find the right provisioning profile for your app. To tackle this, go ahead and navigate to the Signing and Capabilities tab within your project settings. Once you're there, just make sure you've selected the correct team and that you've got the right provisioning profiles in place for both debug and release builds. That should set you straight.
Now, let's see how we can implement a function to process user input effectively. In this example, we define a function named processInput that takes a single parameter, input, which is a string. The main purpose of this function is to handle. Now, let's see how we can implement a function to process user input effectively. In this example, we define a function named processInput that takes a single parameter, input, which is a string. The main purpose of this function is to handle the input provided by the user, ensuring it's free from unnecessary whitespace or new line characters. First, we utilize the trimming characters method to remove these extraneous characters, creating a new variable called processed. This is critical since user input can often contain unwanted spaces that could lead to errors or misinterpretations in our application, definitely something we want to avoid. Next, we employ a conditional statement to check if the process variable is empty after trimming. If it is, the function returns a user-friendly message indicating that no input was provided. Conversely, if there is valid input, the function constructs a string that includes the processed input, which can be really useful for informing the user of the data they have entered. This approach not only enhances user experience by providing clear feedback, but also demonstrates good practices in handling and validating user input within our application. Now, let's take a look at how we can implement logging to track the app's behavior more effectively. In the given code, we override the viewDidLoad method, which is a fundamental part of the view controller lifecycle in iOS. This method is called after the view controller has loaded its view hierarchy into memory. By invoking super.viewDidLoad, we ensure that any necessary setup to find in the superclass is executed first. Following that, we introduce a simple yet powerful logging mechanism using the print function. Within this method, we include a line that prints a message to the Xcode console stating "view has loaded." This log serves as a confirmation that the view has successfully appeared, offering immediate feedback during development. Utilizing print statements like this is extremely useful in the early stages, as it helps you track the flow of your app and understand what methods are being called and in what order. Now, as you progress, remember that while print is excellent for development, transitioning to more robust logging frameworks will be beneficial for production. They offer enhanced management of log data and functionalities, which can really streamline your debugging process. So keep that in mind as you refine your application further.
Next, we're going to write a function to validate user input, ensuring it meets certain criteria before moving forward with any processing. The function is called isValidUserInput, and it takes one parameter, input, which is a string containing what the user has entered. First thing we do inside the function is trim away any unnecessary whitespace or new line characters from the input using the trimming characters in method. This step is super important because it helps prevent users from, accidentally entering just spaces, which we definitely don't want as valid input. So after we trim it, the function checks if the resulting string is empty. If there's some content, it returns true, and if it's empty after trimming, it returns false. Now, by wrapping this validation logic in its own function, we can reuse it throughout our application. Instead of writing this validation code over and over in different spots, you can just call this function wherever user input needs to be checked. This not only cleans up your code and makes it more maintainable, but it also reduces the chance of bugs. Since any adjustments to the validation logic only need to be made in one place, it keeps everything neat and less prone to errors. Which is exactly what we want.
Now, let's see how we can implement error handling in our app using Swift's do-catch blocks. In this example, we define a function called fetchData, which is responsible for retrieving data from a database. Inside this function, we start with a do block, right? Here, we attempt to call another function, fetchDataFromDatabase, which could throw an error if something goes wrong during that data retrieval. By using the try keyword, we send a clear signal that we're aware this operation might fail, and we're prepared to handle any potential errors that could arise. Now, if the data is fetched successfully, we're going to print a confirmation message along with the retrieved data. However, if an error occurs, the execution will seamlessly jump to the catch block where we can manage the error in a graceful manner. Here, we'll print an error message to the console that contains the localized description of the issue. This approach prevents the app from crashing and allows us to inform the user or even log the error for further investigation. Proper error handling not only enhances user experience by managing failures seamlessly, but also aids significantly in debugging and maintaining robust applications.
Now let's implement a button that will remain centered in the user interface, making for a polished experience across devices. We start by creating a UI button of type system, which allows for consistent appearance and behavior with other native iOS components. After setting the title of our button to Press Me, it's essential to disable the automatic constraints provided by the system by setting Translates Auto-resizing Mask into Constraints to false. This step is crucial as it indicates that we'll be using auto-layout constraints to manage the button's position manually. Next, we add the button as a subview to the main view, ensuring that it will be part of the view hierarchy and displayed on the screen. Now, let's see how we can set up the constraints to ensure that the button remains at the center of the view. By activating the constraints, we pin the button's horizontal center, the center X anchor, to the view's horizontal center and the vertical center, the center Y anchor, to the view's vertical center. This programmatic way of setting constraints guarantees that regardless of the device size or orientation, our button will always appear perfectly centered, contributing to a user-friendly interface.
As we wrap up, let's take a moment to appreciate the importance of continuous learning and staying updated with the latest iOS advancements. Apple frequently rolls out updates to its frameworks, introducing exciting new features, and enhances performance. Keeping pace with these updates will not only boost your app's functionality, but also establish you as a well-informed developer in the community. Now, a fantastic place to stay in the loop is through Apple's developer documentation and forums. Here, you can dive into discussions and discover fresh techniques shared by other developers. Engaging with the community on platforms like Stack Overflow or through iOS developer Slack channels can offer you invaluable insights and tips. So today, we covered quite a bit. We talked about how to run your app, both in the simulator and on real devices, troubleshooting common issues, the critical role of debugging, how to log user actions effectively, perform refactoring, manage errors efficiently, and elevate user interfaces. Now take this knowledge and go out there to enhance your skills, because honestly, there's a whole world filled with possibilities waiting for you in iOS app development. Happy code! Developing and running your iOS app on a physical device is a critical step in the app development process. While simulators can effectively assist in the initial testing stages, they just can't completely replicate the nuances of hardware performances and functionalities your app may encounter in the real world. In this lesson, we're going to dive into setting up your physical device, preparing your app for testing, and using Xcode to deploy your application directly to an iOS device. So far, we've covered the basics of creating and running an iOS app in the simulator,
emphasizing the importance of code signing and familiarizing ourselves with Xcode. We've also touched on debugging techniques and the art of logging user actions, as well as the significance of crafting cleaner, more efficient code. Additionally, we learned about enhancing our user interfaces with auto layout. Now, we will shift our focus to the hands-on experience of testing our app on a physical iOS device, understanding why it's essential, and ensuring everything is set up correctly.
The first step toward executing your app on physical hardware involves prepping your device, so let's make sure we're ready. First off, you need a compatible iOS device for development. Now grab that device and connect it to your Mac using a USB cable, and don't forget to unlock your device. If this is your first time connecting the device to your Mac, you'll see a prompt asking you to trust the Mac. Just tap Trust when you see it. All right, next up, we've got to ensure Xcode has the necessary permissions to recognize your device. Open up Xcode, and from the menu, navigate to Preferences. Go ahead and click on the Accounts tab, and make sure you're signed in with your Apple ID. This step is super important because it relates to provisioning profiles and code signing that are essential for running your app. Now, let's delve into provisioning profiles and code signing, which allows your app to run on physical devices. For that, we need to set up a new provisioning profile. Head over to the Apple developer website and log in. Once you're in, navigate to Certificates, Identifiers, and Profiles, and create a new app ID. It's crucial here to match the app ID with your Xcode project's bundle identifier, which you can find in the project settings after clicking on your project name in Xcode. For example, if your bundle identifier is com.yourdomain.yourapp, make sure the app ID you create matches exactly. Once that's done, generate a new provisioning profile. For development, select iOS App Development. Choose the app ID you just created. Select the certificate you created or already have, and finally add your device's UDID. You can find that in Xcode by selecting your device from the Device and Simulators window. So it's a straightforward process. Just ensure everything lines up correctly and you'll be good to go. The accompanying chart, titled Key Steps in Developing and Running Your iOS App on a Physical Device, breaks down the relative emphasis placed on 6 major tasks: setting up device, which takes up 15%, provisioning profiles at 25%, code signing at 20%, testing on device, also at 20%, debugging at 10%, and finally, finalizing for App Store, which is at 10% as well. Now, the largest slice of this pie goes to provisioning profiles, sitting at a solid 25%. This indicates that without a doubt, managing profiles and associated certificates is the single most substantial process in this workflow. Code signing and testing on device, both at 20%, show us that these two share a comparable level of importance. One ensures that the app is trusted and executable, while the other validates how it behaves on actual hardware. Now, let's talk about setting up device. Even though it only accounts for 15% of the chart, it's visually emphasized, exploded, if you will, to signal its practical importance. After all, this is the necessary initial step where you connect, trust, and enable the device for development. Debugging and finalizing for the App Store each represent smaller but still non-trivial portions at 10% each. This highlights that diagnosing runtime issues and preparing the build for distribution do take some effort, even if it's less than the other steps. So from this distribution, we can conclude that developers should definitely allocate most of their attention and time to those provisioning and signing processes, while ensuring robust on-device testing. And we can't overlook that initial device setup, despite its seemingly smaller slice, is crucial. Moreover, debugging and final packaging are essential finishing steps as well.
Now, let's see how we can implement the necessary configurations in the Android equivalent using Kotlin. The provided code outlines the Android block within the build.gradle file, which is a crucial part of any Android project setup. First, we specify the compile SDK version, which indicates the API level that the project will be compiled against. In this case, it's set to version 30, allowing access to features and functionalities introduced in that version of Android. Following that, the default config block lays out essential attributes for the application. The application ID defines the unique identifier for your app on the Google Play Store, which must resemble your intended package name. Here, it's set to com.yourdomain.yourapp. Next, we define the Min SDK version as 21, indicating that the app will be compatible with devices running Android 5.0 or Lollipop or higher. The Target SDK version, also set to 30, informs the system about the version of Android on which the app is designed to run optimally. Finally, version code and version name denote the internal version number and user visible version, respectively. These properties are integral in managing updates and ensuring users have the correct version of the app. With all of this set up, you can now finally run the app. So go ahead and select your device from the list of available simulators in the Xcode toolbar, and then click that Run button. If everything goes smoothly, your app will build and launch directly on your iOS device. Now heads up, the first time you do this, it might take a little longer, since Xcode needs to handle all those file transfers and processing. But once it's done, you'll be able to navigate through the app just like it was downloaded from the App Store. Pretty cool, right? Here's the magic part. Any changes you make to your code can be tested in real time. Just remember, you'll need to stop the app and run it again after making any changes. Now, if your device isn't showing up or you hit any build errors, don't panic. Just check the device logs. You can access those through the Devices and Simulators window in Xcode. This gives you great feedback to help troubleshoot any issues that might only show up on real devices.
Now, let's see how we can implement camera functionality in our app. The provided code defines a view controller class that inherits from UI view controller and conforms to the UI image picker delegate and U navigation controller delegate protocols. This setup allows our view controller to respond to image selection events when using the image picker. First, we'll implement an action method called openCamera, which gets triggered when the user taps a button. This method initializes a UI image picker instance and sets its delegate to the current view controller, empowering it to manage the image picker's actions. By specifying the source type as .camera, we indicate we're presenting the camera interface for capturing images. Once the user snaps a picture, the delegate method ImagePickerController did finish picking media with info is called. Within this method, we safely unwrap the captured image from the info dictionary using the key .originalImage. If an image is successfully retrieved, we assign it to the image view property so we can display it right in our app. Finally, we dismiss the image picker, allowing the user to return to the app seamlessly. This implementation provides a straightforward way for users to interact with the camera directly from your application.
Next, we're going to implement a very simple logging mechanism that will help us keep track of important events in our app. The logger class we've created serves a specific purpose, to log messages with a timestamp. This provides us with better insights into user behavior and app activity. Inside this class, we define a static method called log, which takes a single parameter, a message of type string. Now, the key feature of this logging method is its use of the print function. It outputs the current date and time alongside the message passed to it. And this timestamp is crucial for understanding the sequence and timing of events when debugging your app. For example, whenever a user taps a button, you can call logger.log with a message like user tapped the button. This way, you can review the user interactions logged in real time. By utilizing this simple logger class, you'll acquire detailed insights into your app's behavior during testing. Each log entry helps you gain a better understanding of how users interact with your app and identify any issues that may need addressing. Trust me, this approach becomes an essential part of your debugging toolkit.
Finally, once you're satisfied with testing, don't forget to prepare your app for distribution. If you plan on releasing your app on the App Store, you'll need to archive your build in Xcode. So let's simplify this process a bit. Go to Product in the menu, then select Archive, and follow the prompts that guide you through validating your build, uploading it, and creating a listing for the App Store.
across various device types and different iOS versions to make sure everything is compatible. User feedback is really essential, so consider releasing a beta version through test flight.
To sum it all up, we've journeyed through the steps of connecting and preparing a physical iOS device for your app. We dived into the implications of code signing and provisioning profiles, explored deployment, and really embraced the testing capabilities that real hardware brings to your applications. With these skills in your toolkit, you can leverage hardware functionalities, smoothly implement debugging processes, and effectively release your app into the world. You're well on your way to becoming a proficient iOS developer. Always remember, coding is just the outline. The real experience unfolds when you step into the user's shoes and see how they interact with your app. Happy coding.
When it comes to iOS app development, running your application on an actual device is a crucial step. While simulators allow for convenience and ease of access, they cannot replicate the true experience your users will have. Running your app on an actual iOS device ensures you can test hardware components and software APIs that are critical for smooth performance and user experience. So far, we have learned the importance of developing and testing iOS apps on physical devices as opposed to simulators, which focus on setting up the device, code signing, and provisioning profiles. We covered the process of manually managing provisioning profiles in Xcode, ensuring a seamless connection between devices and applications. We've also explored the capabilities of real hardware in testing functionalities such as the camera and debugging tools provided by Xcode. Finally, we highlighted the essential steps for preparing the app for distribution, including the use of test flight for beta testing. Now we will dive deep into the practical aspects of running your app on an actual iOS device, exploring the necessary steps, troubleshooting common issues, and optimizing our app for real-world use. First, let's discuss how to prepare your iOS device for development. Ensure your device is connected to your development machine. Open Xcode, select Devices and Simulators from the window menu, and your connected device should appear in the left-hand sidebar. If it doesn't show up, you may need to check your cable connection, or your device might require authorization. On your device, an alert will prompt you to trust this computer. Tap Trust, and that should establish a connection. The displayed pie chart titled Key Aspects of Running iOS Apps on Devices divides effort and attention among 5 labeled areas: provisioning profiles 15%, device testing 30%, Xcode setup 25%, debugging 20%, and user experience 10%. The largest slice, device testing at 30%, highlights that the most significant portion of the workflow should be devoted to validating the app on real hardware, verifying sensors, cameras, network conditions, and platform-specific behaviors. Xcode setup at 25% and debugging at 20% together form nearly half the chart, indicating that a substantial share of time goes into configuring the development environment and iteratively diagnosing issues that only appear on devices. Provisioning profiles occupy 15%, underscoring their essential but relatively smaller role in the overall process. They are a gateway step that must be completed to enable device deployment, but typically require less continuous effort than testing or debugging. User experience at 10% is the smallest segment, suggesting that while UX is crucial, in the context of running apps on devices, this chart emphasizes operational and technical readiness over design refinements, a reminder to allocate time proportionally. Ensure provisioning is completed early, invest heavily in device testing and a robust Xcode setup, and maintain ongoing debugging cycles to support a polished user experience. A common pitfall for developers is the unconcerned handling of provisioning profiles. These profiles allow your app to run on your physical iOS device. You'll need an Apple Developer account to create and manage provisioning profiles. Log into your Apple Developer account and navigate to the Certificates, Identifiers, and Profiles section. Here you will create an app identifier and a provisioning profile associated with your app. Once done, download and double-click the profile to install it in Xcode. Once you have configured everything in your developer account, you need to ensure that your app's bundle identifier matches that of the provisioning profile. You can easily check this in the Xcode project settings. Open the project, go to the General tab, and look for the bundle identifier field. This should match exactly with what you defined in the provisioning profile unless you configured wildcard identifiers. Now let's see how we can configure our iOS app to target a physical device by adjusting the settings in the build Gradle file of our iOS module. The code snippet begins with the iOS configuration block, where we are setting up the specific details relevant to the iOS application. Inside this block, we declare binaries, which is where we define various binary outputs of the module. Next, we define the framework, indicating that we're creating a framework that will be shared across different platforms. Within this framework block, base name is specified as my app, which sets the base name for the generated framework. By customizing the base name, we ensure clarity and organization, especially when dealing with multiple frameworks or modules in a larger project. This structure is critical because it informs the build system about how to compile and link your application properly, making it ready for deployment to an actual iOS device. This setup will enable you to run your app directly on a connected device, thereby allowing for genuine testing and interaction with real hardware components that simulators cannot fully replicate. Next, we will write the following code to implement camera functionality in our app. The first part of the code defines a function called OpenCamera, which serves as a trigger to open the device's camera. In this function, we create an intent using intent media store action image capture, which specifies that we want to capture an image. Once the intent is set up, we call start activity for result intent request image capture, which starts the camera activity and awaits a result, enabling us to process the captured image later. It's essential to understand that before using the camera, we must ensure that our application has the necessary permissions. Therefore, in the manifest file of our application, we need to add a specific permission line. Uses permission Android name equals Android permission camera / This line informs the operating system that our app intends to access the camera hardware. By including proper permissions, we enable a smooth user experience, ensuring that when users trigger the camera, they are not blocked by permission issues. This code not only executes the desired functionality, but also emphasizes the critical importance of handling user permissions gracefully within your app. Now let's implement logging to provide insights into our app's behavior. Logging is an essential practice during development, as it helps track the application's state and identify potential issues. In this example, we'll utilize a simple print statement to output the current user's name to the debug console. Next, we will write the following line of code. Print current user username. This line demonstrates how to use string interpolation in Kotlin, allowing us to embed the value of the username variable directly into the string. When this code executes, it will display the current user's name, giving developers immediate feedback on who is interacting with the app. Utilizing print statements like this is particularly useful for debugging purposes, as they can help trace the flow of execution and understand the state of variables at specific points in time. Remember that effective use of logging can quickly lead you to the root of performance bottlenecks or unexpected behavior, making it a vital tool in your iOS development toolkit. While testing, being aware of performance is critical, especially on various devices with different hardware capabilities. Run your app on multiple devices to ensure that it performs well across the spectrum because your users will have varying hardware. Use Xcode instruments to analyze performance metrics and pinpoint memory leaks or performance bottlenecks. Instruments can be accessed through Xcode's menu under Tools. When you're ready for beta testing and want to distribute your app to a small group of testers, TestFlight comes in handy. To do this, build your app for release configuration in Xcode, then navigate to Product, select Archive. Once archived, distribute the build via TestFlight, where testers can download and provide feedback on their experiences, a critical phase in app development. Lastly, let's check the code signing aspect again to ensure you are adequately set up for submitting your app to the App Store eventually. Non-initiated app attempts may occur due to invalid signing configurations. Open the Signing and Capabilities tab in your target settings in Xcode. Ensure that your team is selected and automatically manage signing is checked. This way, Xcode takes care of renewing provisioning profiles and certificates. You can also have a family of various certificates to support different versions and features of your application. It's best to review your certificates regularly via your developer portal to avoid expiration issues, as this will block your app from running on devices. In summary, running your app on an actual iOS device not only provides invaluable testing opportunities, but prepares your app for real-world environments. From setting up provisioning profiles to leveraging device-specific capabilities, you must ensure your app is robust and user-friendly. As you embark on this journey, remember to keep testing diligently, debug wisely, and gather feedback. The more prepared you are, the better the user experience you can deliver. Now, equipped with this knowledge, you can confidently test your iOS app on real devices, bringing you one step closer to a polished and professional product. Happy coding! To unlock the full potential of developing iOS apps, it's crucial to grasp the concepts of developer mode and trust settings. As Apple introduced developer mode during the Worldwide Developers Conference in 2022, it's a requirement for running, debugging, and installing apps on devices operating on iOS 16 or newer. So far, we learned the significance of testing iOS apps on physical devices to ensure optimal performance and user experience, highlighting the necessary steps for preparing devices for development, including managing provisioning profiles and Xcode setups. We discussed the importance of debugging on real hardware, utilizing tools like Xcode's debugger, and implementing features such as camera functionality. Additionally, we covered performance testing across various devices and the process of using TestFlight for beta testing. Finally, we emphasized the need for thorough preparation and regular updates on code signing to facilitate app distribution. Now we will talk about developer mode and trust settings, shedding light on how to navigate these important concepts in iOS app development. Developer mode is a powerful tool that Apple has introduced to unify and simplify app development on iOS devices. Prior to its introduction, developers had to jump through various hoops to get their apps onto connected devices. Now, with developer mode, the process is smoother and designed with efficiency in mind. Enabling developer mode activates certain features, such as enhanced logging, the ability to use certain debugging tools, and direct installation of apps without going through the App Store. First off, to enable developer mode on your device, you'll need to access the settings. Start by heading into Settings and scroll down to Privacy and Security. Here you'll find the developer mode option. As soon as you tap it, you will encounter a toggle switch that you can switch on. However, do take note, enabling this mode requires a device restart, and you will also need to confirm the action on your screen. Once rebooted, your device should allow you to install and debug apps with great ease. The accompanying figure presents a pie chart titled Key Concepts of Developer Mode and Trust Settings in iOS App Development that quantifies emphasis across 4 areas. Enable developer mode 35%, grant trust to app 25%, debugging tools utilized 20%, and user feedback integrated 20%. The largest slice, 35%, corresponds to enabling developer mode, signaling that making the device development ready is the single most emphasized activity in this workflow. The second largest portion, 25%, highlights the importance of establishing trust for developer-signed apps. This reflects the practical step of trusting a developer profile before an app can run on hardware. Debugging tools and user feedback are shown as equal slices, 20% each, indicating parity between time spent on technical troubleshooting and on incorporating user-driven insights. Interpreting these proportions together, the chart suggests a workflow priority. First, ensure the device and environment are configured developer mode, then establish trust for app execution while dedicating substantial balanced effort to both debugging and soliciting or integrating user feedback. Combined, the latter two account for 40%, which collectively outweighs any single initial setup task and underscores ongoing validation and iteration during development. Now let's see how we implement location tracking functionality in our app. In this code, we begin by defining a location activity class that extends fragment activity, which provides support for fragment management in an activity. We initialize a fused location provider client that allows us to access location services seamlessly. Inside the onCreate method, we check for the necessary permissions to access the device's find location. Utilizing the ActivityCompat class, we verify whether permission has been granted. If permissions are not yet granted, we request them from the user, which is essential to ensure that we uphold security and user privacy. If permissions are granted, we proceed to invoke the getLastLocation method, which uses the fused location provider client to obtain the last known location of the device. The resulting location is provided through a success listener that captures the location data, allowing us to utilize it as needed. This structured approach ensures that our app adheres to permission policies while efficiently accessing and leveraging device features. Now, developer mode also tightly interrelates with trust settings, especially regarding how apps are trusted to run on a specific device. Trust settings determine whether an untrusted developer's app can execute on a device. These settings are incredibly important in maintaining device security and preventing the installation of malicious applications. When you develop apps with developer mode enabled, you often need to trust the developer certificate associated with the app. This trust is established once the app is installed on a device, and users must go through a series of steps to grant this trust. In iOS, the process involves navigating to Settings, General Device Management, or Profiles and Device Management. Here, users should see listed developer profiles that have signed their apps, and they'll need to tap Trust before they can run the app. Let's illustrate this with a hypothetical scenario. Imagine you've just developed an app called My Cool App and want to test it on your device. After compiling your app through Xcode, the app doesn't run immediately because iOS doesn't recognize the app's developer certificate. To efficiently test My Cool App, you should go through the trust settings. In this situation, follow these steps post-installation. 1. Open the settings and navigate to General. 2. Locate Device Management or Profiles and Device Management. 3. Find your developer profile listed under Developer App. 4. Once you tap Trust, you'll see a notification indicating that the app is now trusted. Now imagine your friend, who is an amateur developer, has shared his app with you. You'll take the same steps to trust him as a developer. This critical trust setting process ensures that only verified developers can execute apps on iPhones and iPads, thereby safeguarding users from potential security threats. Now let's see how we can implement error handling within our application. When developing apps, it is crucial to anticipate potential issues that may arise during execution, which could cause the app to crash. To manage these situations effectively, we utilize a try-catch block, a fundamental aspect of robust application development. In this implementation, we begin by wrapping the portion of our code that performs a potentially risky operation inside a try block. This is where we execute the code that may throw an exception if something goes wrong. By doing this, we establish a protective layer around our code that allows us to catch any errors that may occur. Should an exception arise, control will transfer to the catch block, where we can handle the error appropriately. In this example, we simply print out a message that includes the details of the exception, helping us understand what went wrong. This practice not only prevents the app from crashing, but also provides valuable feedback during the testing phase. By adopting such error handling techniques, we can significantly enhance the quality and reliability of our applications as we continue developing in developer mode. Now let's see how we can implement logging to track user actions in our app. Logging is an essential practice for debugging, enabling us to gain insights into the app's behavior as it runs. In this example, we'll utilize Android's log class to capture and report user activities at the debug level. Initially, we create a function called logUserAction, which accepts a string parameter representing the user action. Within this function, we call logd, passing user action as a tag to categorize the log message and the action string to document the specific event. This method helps ensure that each logged action is clearly labeled and can be easily traced back when examining the output in the logcat. Next, we can invoke this function each time a user performs an action within our app, such as button clicks or screen transitions. For instance, we demonstrate this by logging a message when a button is clicked. By incorporating this logging functionality, we can effectively monitor the app's state and user interactions, allowing us to identify unexpected behaviors and refine the user experience based on real-world usage. Now let's see how we can implement a simple unit test in Kotlin to validate our application's functionality. The code begins by importing necessary testing libraries from JUnit, which are essential for creating and executing test cases. We define a test class called mathUtilsTest, where we will house our test methods. Within this class, we annotate a function, testAddition, with test, indicating that this method should be executed as a test case. In this function, we first call a private helper function, add, passing the integers 2 and 3. The purpose of the add function is to return the sum of these two integers, showcasing how we can test our mathematical operations. Afterward, we utilize the assertEquals method to compare the expected outcome, 5, with the actual result returned by the add function. This structure not only ensures our addition logic is correct, but also demonstrates the ease of running such tests within developer mode. allowing for quick feedback as we develop our application. Incorporating automated testing practices like this helps maintain code quality and ensures that functionality behaves as intended as our application evolves. As we conclude our discussion on developer mode and trust settings, it's important to reiterate how these features work together to create a secure and efficient app development ecosystem. From enabling debugging to managing app trust, understanding these concepts equips you with the tools needed to develop high-quality iOS applications. So we've covered the significance of developer mode introduced by Apple, how to enable it, the importance of trust settings, and the way they help maintain a secure environment for app development. Additionally, we explored error handling, robust logging practices, and the benefits of automated testing, all critical elements for developing successful apps. Going forward, continue exploring and experimenting with the tools provided within developer mode. The more you practice, the better you'll understand how these components work together to enhance your application's functionality and user security. Remember, solid groundwork today leads to exceptional apps tomorrow. Happy coding and see you in the next lesson. Developer mode is a critical feature introduced by Apple during their Worldwide Developers Conference in 2022. It is fundamentally designed to streamline the process of installing, running, and debugging applications on devices using iOS 16 or greater. In this session, we will explore the nitty-gritty of developer mode, its importance in iOS app development, and why you absolutely need to embrace it if you want to finesse your apps. So far, we learned about the importance of developer mode and trust settings in iOS app development, highlighting how developer mode simplifies the process of debugging and app installation on devices. We discussed the steps to enable developer mode and the significance of managing trust settings to ensure apps can run securely on devices. Additionally, we covered best practices for error handling and logging, as well as the role of automated testing to maintain app quality. Moving forward, we'll delve deeper into practical applications and advanced techniques for utilizing these features effectively. The displayed figure is a horizontal bar chart titled Key Features of Developer Mode in iOS Development that ranks 8 developer mode features by their importance on a 110 scale x-axis labeled Importance Level 110. From the data shown, debugging tools is the single highest rated feature at 10, indicating it is considered the most critical capability provided by developer mode. A secondary tier of high importance rating 9 includes install apps, automated testing, and simulators, which together emphasize that rapid installation, rigorous testing, and device environment coverage are nearly as essential as debugging itself. Mid-tier items at importance 8 are enable developer mode and live reloading, showing that enabling the mode and fast feedback loops are important enablers for development workflows. Error handling sits slightly lower at 7, reflecting that while handling exceptions is important, it is often supported by the higher priority debugging and testing features. Finally, dynamic colors is the least prioritized at 6, suggesting UI color customization is a lower immediate concern compared with tooling and validation capabilities. The overall pattern highlights a clear focus on observability, deployment, and automated validation as the primary values of developer mode, supporting iterative development and reliable device testing, while UI polish features are comparatively less emphasized. Let's start with enabling developer mode. Imagine you have this amazing app idea, a spark of genius waiting to be explored. But before you can share it with the world, you need to test it extensively, right? This is where developer mode comes into play. To enable developer mode on your iOS device, follow these simple steps. 1. Go to the Settings app and scroll down to Privacy and Security. 2. Tap on developer mode and switch it on. 3. You will see a prompt asking you to restart your device. Confirm this. 4. Once rebooted, you'll get the chance to enable developer mode again. Simply click on Turn On. Once enabled, this feature allows you to run any unverified apps directly on your device, circumventing the normal restrictions that safeguard users against potentially harmful applications. This is especially vital for new developers and agile teams who need to iterate quickly on their creations. Now that we've established the necessary setup for our iOS app, let's take a look at the core structure of our application defined within the AppDelegate class. This class serves as the entry point for your app, acting as a bridge between the system and your app's content. Here we have a property called Window that holds the app's main window where all of our visual elements will be displayed. Next, we will implement the method called Application did-finish launching with options, which is a crucial lifecycle method in iOS applications. This function gets called when our app is launched, providing an opportunity for initial setup tasks. Inside this method, we can conduct any configurations or adjustments required before the app becomes visible to the user. For instance, if you wanted to modify user settings or initialize third-party libraries, this function is where you would handle those tasks. Finally, the method concludes by returning true, signaling to the system that the app has successfully finished its launch sequence. This foundational code is essential as it lays the groundwork for how the app behaves and interacts with the operating environment. Understanding this structure is key to developing robust iOS applications. Now let's see how we can implement a simple logging mechanism in our application using Kotlin. The code defines a class named sampleClass, which contains a function called performAction. When this function is invoked, it initializes a variable called state with the string action performed. This line effectively captures the current state of the operation being executed. Next, the println state statement logs this state to the console. This is particularly useful for debugging purposes as it allows developers to see real-time feedback about the application's execution flow. By viewing this log, you can easily track the method's activity without needing a complex debugging setup. This function serves a dual purpose. It showcases basic variable usage in Kotlin and emphasizes the importance of logging and understanding your app's behavior. When you call performAction, you will see action performed in the console, providing immediate insight into what step your code has reached during execution. Such practices are essential to maintain efficient debugging, especially when facing unexpected behaviors in your applications. Now let's see how we can implement error handling in our application to ensure a smoother user experience. In the given code, we define a class called userAction that contains a method named executeAction. This method demonstrates how to wrap potentially error-causing operations within a try-catch block. By surrounding the code with a try block, we are preparing to handle any exceptions that may arise during its execution. In our example, we simulate an error by throwing an exception explicitly with a message sample error. This helps illustrate how the error handling mechanism works. When an exception occurs, the control is passed to the catch block, where the caught_exception object E provides access to the error message. In this instance, we log the error message using println, which displays it in the console. This logging step is crucial for debugging, as it allows developers to understand what went wrong without crashing the application. In conclusion, incorporating effective error handling practices like this in your code not only enhances its robustness, but also keeps users engaged by preventing frustrating crashes during unexpected scenarios. Next, we will write a simple unit test in Kotlin to illustrate how automated testing can help verify that our application's functionality works as expected. In this example, we define a class named simpleTest, which contains a method annotated with test to indicate it as a test case. The method addition is correct tests a specific feature. It checks whether the addition of two integers 2 and 3 produces the correct result of 5. To achieve this, we call the add function, which performs the addition operation. Immediately after, we use assert equals to compare the expected result 5 with the calculated sum. If these values match, the test will pass, confirming that our addition logic is correct. However, if the values differ, the test will fail, highlighting a potential bug that needs to be addressed. This approach allows developers to catch issues early in the development process, ensuring that future changes don't inadvertently break existing functionality. Implementing automated tests like this instills confidence as we release new versions of our app, knowing that critical logic has been validated. Now let's see how we can configure build types in our Android project to tailor our app for different environments. The provided code defines an Android block where we specify various build types, namely debug and release. In the debug configuration, we utilize the application id suffix to append debug to the application ID, allowing us to differentiate the debug version of the application from the release version. This is particularly useful during testing, as it helps avoid conflicts when installing both versions on a device. Additionally, a version name suffix of debug is added to the version name, providing clarity on the current build being tested. Moving to the release build, we set minify enabled to false, which means that code shrinkers like ProGuard are not activated. This is helpful during the development phase to retain full debug information while you're actively working on the application. By organizing these build types, you can seamlessly switch between development and production environments, ensuring that your testing and deployment processes remain efficient and well-structured. Now let's see how we can implement a simple UI component using Jetpack Compose. The greeting function we define here is a composable function, marked by the @composable annotation, which means it can be called within the Compose framework to build UI components declaratively. Within this function, we create a button, and within that button, we add a text label. The button's onClick parameter is where we can define what happens when the button is pressed, although in this snippet it currently lacks an action. The text displayed on the button incorporates the name parameter, which allows for dynamic content. By using a string template, we can easily insert the name variable within the greeting message. This simple structure showcases how to create interactive elements in your app, demonstrating the power of Compose for building user interfaces quickly. As you adjust the name parameter and recompile, you will see those changes immediately reflected in the UI thanks to the live reloading capabilities of developer mode. This not only enhances productivity, but also makes for a more engaging development experience. Now let's take a look at how to set up a simulator for testing our app. In the provided code, we define a function named setUpSimulator that simulates the selection of a device type for running our application. This function utilizes a simple variable named device, which is set to iPhone 13. By using the println statement, we print a message to the console indicating which device is currently being simulated. This approach allows developers to easily customize and switch between different device types for testing purposes. By simply updating the value of the device variable, you can simulate your app's performance across various iOS devices, ensuring that it behaves as expected on different screen sizes and orientations. This step is crucial as it enables developers to identify UI elements that may not display correctly or function optimally on all devices before launching the app. So, implementing such a setup not only streamlines testing, but also significantly enhances the overall quality of the application as part of the developer mode features in Xcode. In conclusion, understanding developer mode isn't merely a step in an iOS developer's toolkit, it's a vital component of creating high-quality apps. It allows for iterative development, thorough testing, quick debugging, and dynamic environment configurations. These capabilities not only boost productivity, but also enhance the overall quality of your apps. Having discussed everything from enabling developer mode to implementing automated testing and configuring app builds, you now possess a solid foundation to leverage these features. Embrace developer mode, and you'll not only streamline your development process, but also bring your app vision closer to reality, one iteration at a time. Stay curious, keep experimenting, and happy coding. Developer mode is an essential feature for anyone diving into iOS development, introduced by Apple during WWDC 2022. It facilitates the smooth installation, running, and debugging of apps on devices operating iOS 16 or greater. So let's strap in and explore exactly what developer mode brings to the table, how to enable it, and why it's a game changer for developers. So far, we learned about developer mode, a crucial feature for iOS app development that simplifies debugging, app installation, and error handling. We explored enabling developer mode using debugging tools and the importance of automated testing to ensure app quality. Additionally, we discussed configuration settings for different environments and the benefits of live reloading and simulators in facilitating a smooth development workflow. Moving forward, we will continue to examine practical applications and advanced techniques for maximizing these features. First things first, enabling developer mode on your iOS device is a straightforward process, but it must be done before any meaningful development work can happen. To enable it, navigate to the Settings app on your iPhone or iPad, scroll down and select the Privacy and Security option. Inside this menu, you will find a toggle for developer mode. Flip that switch and the device will prompt you to restart. Upon rebooting, a confirmation dialog appears just to ensure you really want to go ahead with this. A simple tap on Turn On and boom, developer mode is active. Your device is now equipped to handle the aromas of debugging and development. The displayed figure is a vertical bar chart titled Key Concepts of Developer Mode in iOS Development that quantifies the relative focus placed on 6 aspects: debugging 20, app installation 30, error handling 25, automated testing 15, simulators 5, and security 5. The x-axis lists the aspects, while the y-axis shows an importance level scale with numeric labels. Each bar has a numeric data label at its top corresponding to its value. Visually, app installation is the tallest bar 30, followed by error handling 25 and debugging 20, forming a clear top 3 cluster. Automated testing sits midway at 15, and both simulators and security are minimal at 5 each, creating a sharp drop-off after the mid-range value. From this distribution, we can conclude that the dominant priorities represented are deploying apps onto devices and managing runtime problems, installation errors, and debugging, with testing acknowledged but less emphasized, and simulators and security shown as comparatively low priority in this specific view. These patterns suggest a practical, device-focused workflow where getting builds onto hardware and diagnosing failures are primary activities, while test coverage and simulator-based or security-focused work are present but receive less immediate attention, indicating areas where teams might choose to rebalance effort if broader coverage is desired. Now let's implement a simple function to demonstrate how to add two numbers using Kotlin. The function addNumbers takes two integer parameters, a and b, and returns their sum. This function encapsulates the addition logic and serves as a reusable component within your application. You can visualize its utility in amplifying code efficiency. Wherever you need to perform additions, call this function with the relevant values. Next, we will see how the function integrates within our main program. In the main function, we declare a variable named result and assign it the output of calling addNumbers with the values 5 and 10. This showcases the function's capability to calculate and return the desired outcome. Finally, we print the result to the console using println, which serves as a straightforward way to verify our addition operation. This approach not only highlights how to structure functions in Kotlin, but also offers a neat demonstration of function calls and variable assignment, essential concepts in programming that help in breaking down problems into manageable, modular pieces. As you continue coding, think about how to leverage reusable functions like this to enhance clarity and maintainability in your code. Now let's take a look at a basic configuration setup for an Android project using Kotlin multi-platform in the build Gradle file. This snippet outlines the essential parameters that define your application's structure and compatibility. First, we specify our target environment under the Android block, setting the compile SDK version to 31, which ensures we're using the latest features and optimizations available. Next, we define the default configuration for our app, starting with the application ID, which uniquely identifies our application in the Play Store. We also set the minimum and target SDK versions. The min SDK version of 21 indicates the app can be run on Android devices starting from version 5, Lollipop, while the target SDK version of 31 specifies the app is designed to work optimally with Android 12. Importantly, the version code and version name parameters manage the app's versioning, where version code is a numeric value that the Play Store uses to distinguish between updates, and version name is a string representation for user-facing purposes. Following this structure ensures your app is well configured for deployment and functionality on diverse Android devices, providing a solid foundation for further development. Now let's see how we can implement a basic error logging mechanism in Kotlin, which will help us gracefully handle exceptions that may arise during application execution. We start with a function named logError, which takes a string message as its parameter. This function is designed to log errors dynamically and can be extended in the future to log data to external files or systems. The current implementation simply prints the error message to the console, allowing developers to quickly identify issues that occur during app runtime. Next, we move to the main function, where we employ a try-catch block to manage potential errors. Here we attempt to perform a division operation that intentionally causes an arithmetic exception by dividing a number by 0. This simulates a scenario where an error is likely to occur. Instead of allowing the application to crash, we catch the exception and utilize our logging function to output a relevant message. This approach ensures that the application handles errors cohesively and informs the developers, thus maintaining a better user experience by preventing unexpected crashes. Now let's see how we can implement a simple automated test for a function in Kotlin using the JUnit test framework. In this snippet, we define a class called mathTest, which contains a test method to verify the functionality of our addNumbers function. The method is annotated with test, indicating that it is a test case that the testing framework will recognize and execute. Inside the testAddition method, we call the addNumbers function, passing in the values 5 and 5. The expectation is that the result should equal 10. To confirm this, we use the assertEquals function, which takes two parameters, the expected value and the actual result returned by our function. If the values do not match, the test will fail, signaling that there may be a bug in the code. This proactive approach to testing is crucial as it helps catch issues early in the development cycle, thereby increasing the reliability of your application as you continue to enhance and iterate on your features. By implementing automated tests, you can build confidence in the functionality of your code before it reaches users. Now let's see how we can implement device-specific layouts to enhance user experience in our application. The first function, displayLayoutForDevice, checks whether the device is a tablet by calling the isItTablet function. If the device is detected as a tablet, it prints display tablet layout. Otherwise, it defaults to printing display phone layout. This structure allows us to easily differentiate how our app responds based on the device type users are on, an essential step for responsive design. The Is It tablet function simulates the check for the device type. For simplicity, it is hard-coded to return true, indicating that a tablet is being used. However, in a real-world scenario, this function would incorporate logic to dynamically determine the device type, ensuring that users receive an appropriate layout tailored to their device. This functionality is significant as it can save time during development and provide a clearer path for user engagement, as different devices often require different interface elements to enhance usability and accessibility. Now let's implement a function that records user activity, which is essential for keeping track of how users interact with your application. The function recordUserActivity takes a parameter activity of type string representing the specific action the user has taken. Within the function, it features a straightforward println statement that outputs a message to the console, confirming that the user activity has been recorded. However, since this output may often contain sensitive information, it is critical to consider security best practices at this point. While the current implementation simply logs the activity, we should ensure that any sensitive data, such as user logs or personal details, is handled securely. This could involve encrypting the logged information before storage or displaying it, along with implementing additional security measures to protect user privacy. By following these secure coding practices right from the start, you'll create a more trustworthy application that minimizes the risk of data breaches and upholds user confidence. As we wrap up, it's important to highlight that developer mode not only simplifies the development and debugging process, but also enhances security testing and overall application quality. We covered its activation, debugging capabilities, installation processes, error handling, automated testing, and simulator advantages. With these tools in hand, you're now better equipped to tackle the challenge of iOS development while creating quality applications. Remember, the road to becoming a proficient developer may have bumps along the way, but with developer mode, these bumps should be a bit easier to manage. Keep coding, keep testing, and keep improving. Before we dive in, let me give you a quick rundown. Today, we are going to explore the fascinating world of developer mode in Xcode. This is a critical feature introduced by Apple at WWDC 2022, designed specifically to enhance your app development experience on iOS devices running version 16 or higher. So far, we learned about developer mode, which streamlines iOS app development by facilitating debugging, app installation, error handling, and automated testing. We covered the process of enabling developer mode, utilizing debugging tools like Xcode for efficient code inspection, and the significance of automated tests in maintaining application quality. Additionally, we explored the role of simulators in testing across different devices and the importance of security practices when handling user data. Going forward, we'll delve into more advanced techniques to maximize these features. Let's start with what developer mode actually is. Think of developer mode as a gateway that unlocks the advanced functionalities of your iOS device for development purposes. This feature allows you to install and run apps directly from Xcode, push updates, and even debug your application seamlessly. It's an essential component if you want to optimize your workflow as an iOS developer and create robust applications. Enabling developer mode is the first hurdle. It's not overly complicated, but understanding the steps is crucial. To enable it on your device, first connect your iPhone or iPad to your Mac. Open Xcode and make sure it's updated to the latest version. Once connected, unlock your iOS device and navigate to Settings, Privacy, and Security. You will find an option labeled Developer Mode. It's a simple toggle. Once enabled, your device will restart, and voila, you're ready to do some serious coding. Now you might wonder, why is this step so important? Developer Mode enhances your ability to interact with your device in ways normal users can't. For example, it lets you run apps that are not yet published on the App Store, allowing you to test new features and performance metrics without any restrictions. The figure titled Key Concepts in Developer Mode is a horizontal bar chart that lists 6 development phases on the vertical axis and assigns an importance level on the horizontal axis. Each bar is labeled with its numeric value, and the chart shows the following importance distribution: automated testing 30, using Xcode 25, debugging 20, enable developer mode 15, using simulators 10, and security practices 5. This ranking immediately highlights automated testing as the top priority activity, followed closely by proficiency with Xcode and solid debugging practices. Together, these three dominate the chart and represent the core operational focus. Enable developer mode sits in the middle, indicating it is a necessary enabler but not the primary ongoing activity. Simulators are shown with modest importance, reflecting their role as a practical but secondary testing aid, while security practices appear with the smallest value, signaling that within this particular distribution, security is represented but given comparatively less emphasis. From these patterns, we can conclude that the workflow being emphasized favors establishing strong automated test coverage and deep familiarity with Xcode and debugging tools first, while still acknowledging the supporting roles of device-enabling simulators and security measures, a balance that naturally leads into the subsequent topics of debugging and test automation. Now let's take a look at how to create a simple user interface in our iOS application using Kotlin. We begin by defining the main activity class, which inherits properties and behaviors from app-compat-activity, offering us access to essential Android features. Next, within the onCreate method, which serves as the entry point for our activity, we first call superonCreate, ensuring the parent class initializes properly. After setting the content view with our XML layout through setContentView, we proceed to initialize our UI elements, a button and a text view. This is done by using findViewById, which links our Kotlin code to the corresponding UI components defined in the XML layout file. Now let's implement the interactive element. We assign a click listener to the button so that when it is clicked, it triggers the performAction function. This function updates the text displayed in the text view to let users know that the button has been clicked. This direct interaction demonstrates the fundamental principles of user engagement in mobile apps, showcasing how UI components can work together to enhance functionality. Next, we will write a function that deals with nullable inputs, an important concept in Kotlin that enhances type safety. The calculateValue function accepts an optional integer parameter named input. By using a question mark in the type declaration, we indicate that input can either hold a valid integer value or be null. Inside the function, we employ the elvis operator denoted by, which allows us to provide a fallback mechanism. If input is null, the operator will execute the code following it. In this case, we throw in a legal argument exception, ensuring that the function will not silently fail or return an unintended value if the input is not valid. This allows developers to maintain control over the flow of the application and handle errors effectively. In scenarios where you call this function without a valid integer, the exception will be raised, making debugging easier as you can quickly identify where the issue lies. Using this pattern not only promotes robust error handling, but also enhances overall code quality by making expectations around input clear. Now let's see how we can implement a simple unit test in Kotlin to verify the functionality of an addition method. In the provided code, we first import necessary testing libraries from JUnit, including the assertion method, which will help us validate our results. Next, we define a class called calculatorTest, which will house our test cases. Within this class, a method annotated with that test signifies that it is a test method to be executed by the testing framework. In the additionIsCorrect function, we invoke our add function with sample inputs, specifically 2 and 3, and store the result. To ensure that our method works as expected, we use assert_equals to compare the actual output with the expected result of 5. If the output matches, the test will pass. If not, it will indicate that our addition method has issues that need addressing. Additionally, by encapsulating the add method within the test class, we maintain a clean structure, allowing for easier modifications and the potential addition of more test cases in the future. Leveraging this approach not only aids in catching bugs early, but also reinforces the reliability of the code as you continue to develop your application. As we move forward, let's talk about utilizing simulators for cross-device testing. Simulators are an integral part of the development process in Xcode, allowing you to emulate various device configurations without needing the actual hardware on hand. With just a few clicks, you can switch between different iPhone models, screen sizes, and software versions directly in Xcode. When you run your application on a simulator, the experience is nearly identical to testing on a real device. You can debug your app efficiently, test the performance of various UI elements, and even see how your app behaves under different network conditions. To run your app on a simulator, simply select the desired simulator from the drop-down menu in Xcode and hit the Run button. There's a lot of joy in watching your creations come alive on different devices, ensuring compatibility across Apple's diverse ecosystem. Now let's see how we can implement a function to request camera permissions in our app. This is an essential feature as it ensures we respect user privacy by asking for permission before accessing sensitive device functionality, such as the camera. In this function, we start by checking if the camera permission has already been granted. We use the context compat check self permission method for this purpose, passing in the current context and the camera permission constant. If the permission is not granted, we proceed to request it using activity compat request permissions, which takes care of prompting the user with a dialog. This method requires us to pass an array of permissions, along with a unique request code, to identify this particular request later. On the other hand, if the permission has already been granted, we can confidently call the open camera method, which allows us to proceed without any interruptions. This dual approach of checking and requesting permissions is a best practice that promotes user awareness and control over their data, aligning with modern security standards in app development. Implementing such functionality not only enhances user trust but also ensures compliance with privacy regulations. So as we round up our exploration of developer mode in Xcode, remember that it is more than just a toggle switch. It's a powerful feature that opens the door to streamlined debugging, efficient testing, and enhanced security for your applications. You can think of it as the Swiss Army knife in your development toolkit, packed with multiple utilities that refine your development experience. So far, we've covered how to enable developer mode, the use of Xcode for setting up a project, debugging techniques, automated testing, using simulators, and essential security practices. With this foundation, you're well on your way to mastering the art of iOS development. In future sessions, we will dive deeper into advanced techniques that can further optimize your development workflow. After all, the world of coding is vast, and every step we take brings us closer to creating innovative and engaging applications. Keep coding. To effectively run your app on an iOS device, understanding the differences between the simulator and real hardware is crucial. This will not only deepen your development skills, but also prepare you for real-world application scenarios. So far, we've learned about the importance of developer mode in Xcode for iOS app development, including enabling debugging, conducting app testing, and implementing security practices. We've activated developer mode on our iOS device and explored Xcode's capabilities. Moving forward, we will talk about how to run your app on an actual iOS device, why it matters, and the steps to get your application onto your phone or tablet. Let's start with some context. While the simulator provides a useful environment for preliminary testing, it simply cannot replicate the performance nuances and hardware specificities of an actual device. For example, if your app relies on hardware features such as the camera, microphone, GPS, or accelerometer, the simulator won't be able to simulate these components effectively. Testing on actual devices allows developers to get a genuine feel for how the app will perform in a real-world context. First, let's dive into the specifics of how to set up your iOS device for app testing. Ensure your device is running an iOS version compatible with your app. You'll need to connect your iOS device to your Mac via USB. Once connected, trust the computer on your device. On your Mac, open Xcode and navigate to the Window tab in the menu bar. From there, select Devices and Simulators. Your device should appear in the sidebar. If it doesn't, make sure it's properly connected. Next, we will look at how to implement a button-click action within our app, which is essential for triggering device-specific features. In this code snippet, we begin by retrieving the button from the layout using its ID run button. This line of code creates a reference to the button, allowing us to manipulate it programmatically. Now let's implement the button's click listener. By using setOnClickListener, we define a block of code that runs every time the button is clicked. Inside this block, we specify a variable, deviceId, that should contain the unique identifier of the device we want to target. This is crucial because it allows our app to communicate directly with and manage the functionalities of the specific device. Finally, we call the function build and run app device ID, which we assume is responsible for handling the app's building process and executing it on the designated device. This integration enables users to seamlessly interact with hardware features of the device, making for a more engaging and functional app experience. Now let's take a look at a fundamental function for logging data transactions within your app. This Kotlin function, logData, takes a single parameter of type string and utilizes the logd method to output debug messages to the console. The first argument, appdebug, is a tag that helps categorize the log entry, making it easier to filter and identify in the console output. By effectively logging data, you can monitor what is being communicated between your app and the device's hardware components. This is especially valuable during debugging, as it allows you to track real-time app interactions and identify issues that may not be visible during regular operation. In practice, you can call this function whenever you want to capture specific information, whether it's user actions, hardware responses, or any significant state changes within your app. This proactive logging can clarify what happens leading up to an error, ultimately helping you to fix bugs more efficiently. Remember to remove or adjust logging levels in the release version of your app to avoid cluttering the logs with unnecessary information. Now let's implement the following permissions in the info.plist file for our iOS app. This is crucial as it declares to the system which hardware features our application will access and provides transparency to users regarding data usage. In this snippet, we declare two necessary permissions: NS camera usage description and NS location when in use usage description. By including NS camera usage description, we inform the system that our app requires access to the camera to capture photos. This description not only serves as a prompt for users when they are first asked to grant camera access, but also builds trust by clarifying the purpose of the request. Similarly, we add NS location when in use usage description, which indicates that the app needs the user's location to offer personalized services. This ensures users understand why location access is necessary, thereby enhancing their confidence in granting permissions. By explicitly stating these permission requirements along with their respective explanations, we ensure compliance with Apple's privacy standards and improve overall user experience by making these requests clear and understandable. After testing on an actual device, it's also critical to gather feedback about the app's performance. Hardware can often exhibit issues not visible on simulators. Battery drain rates, memory usage, and CPU performance metrics are crucial to assess. Monitoring these metrics allows you to optimize your app better and ensure it works seamlessly under various conditions. To get this information, consider using Xcode's Instruments tool. Instruments provide a comprehensive environment for profiling and performance analysis of your application, allowing you to record and analyze how your app utilizes system resources. Start with selecting the profile type related to your needs, such as time profiler allocations or energy log. Once your app is running, run the chosen instrument to gather performance statistics. Now let's implement the functionality for user feedback within our app. To do this, we first need to create a button that users can click to submit their feedback. In our code, we declare a variable named feedback button, which references the button defined in our app's layout using its ID, RID feedback button. This is a typical way to link UI elements with their corresponding functions in Kotlin. Next, we set an on-click listener for the feedback button. This listener is crucial because it defines what happens when users interact with the button. The code within the listener, indicated by the comment, handle feedback submission, is where we will define the actions taken when feedback is submitted. This interaction is essential as it establishes a direct channel for users to communicate their thoughts, suggestions, or issues related to the app. By actively encouraging this kind of feedback, we not only create a more engaged user base but also show that we value their input. This commitment to user experience can significantly enhance the overall quality and relevance of the app. In summary, running your app on an actual iOS device offers invaluable insights into how it performs under real-world conditions. While simulators are undeniably useful for early stages of development, only through real device testing can you ensure that your app functions as intended, leveraging actual hardware features while adhering to iOS application standards. You will find that testing on a real device enhances your understanding of performance metrics and helps in identifying potential issues that may not be apparent when using a simulator. Be sure to meticulously manage permissions, leverage the power of Xcode's debugging tools, and construct effective feedback channels for your users. Your journey does not end with just running on a device. It is about continuous optimization based on actual user interactions and experiences. This exploration into real device testing is just one step of many as you navigate the rich ecosystem of iOS app development. The insights and techniques you've gained are vital for becoming a proficient developer, setting the foundation for advanced programming techniques that we will discuss in upcoming tutorials. Happy coding! Developer mode in iOS apps is a critical feature that allows developers to install, run, and debug their applications directly on devices. Introduced by Apple during the Worldwide Developers Conference in 2022, it has become an essential requirement for anyone looking to develop apps for iOS 16 or greater. In this session, we will dive deep into what developer mode entails, its prerequisites, and how it enhances your development experience. So far, we learned the significance of testing iOS apps on real devices rather than solely relying on simulators. We explored how to set up devices for testing, manage provisioning profiles, and effectively debug applications using Xcode. We also discussed the importance of handling permissions and gathering user feedback to enhance app performance. These insights lay the groundwork for deeper exploration into iOS app development in future lessons. Now let's talk about why developer mode is pivotal. Imagine trying to debug an application using only a simulator. While simulators are great, they don't capture the nuances of real device performance and behaviors, like how the app handles gestures or utilizes various sensors. Developer mode bridges this gap by allowing you to install your apps directly on actual devices, providing access to all hardware features and performance metrics that simulators can't accurately replicate. Let's look into the requirements to enable developer mode on your iOS device. First, you need a Mac with the latest version of Xcode installed, paired with an iPhone running iOS 16 or higher. You'll also need an Apple developer account, which, while it can be free for initial account setups, provides a more extensive set of capabilities with paid tiers. To start with, ensure that your macOS is up to date and Xcode is installed from the App Store. Once your environment is ready, it's time to configure your device. Connect your iPhone to your Mac using a USB cable and open Xcode. On your device, navigate to Settings, Privacy and Security, and you will find an option for Developer Mode. Toggle this setting on. Note that when you enable Developer Mode, your device may reboot, so don't be alarmed when it does. After rebooting, you'll be prompted to activate Developer Mode again to finalize the setup. The accompanying horizontal bar chart summarizes the relative importance of the key requirements for enabling Developer Mode on iOS. It displays 4 items on the vertical axis: Mac and Xcode, iOS 16 Plus, Apple Developer Account, and USB connection, with importance scored as percentages on the horizontal axis. iOS 16 Plus at 100%, Mac and Xcode at 90%, Apple Developer Account at 85%, and USB connection at 75%. The chart makes 2 clear points. First, platform version compatibility. iOS 16 Plus is shown as the single most critical prerequisite, indicating that having the correct OS version is non-negotiable. Second, development environment readiness. Mac and Xcode at 90% and account provisioning, Apple Developer Account at 85%, are nearly as important and should be prioritized next. The USB connection, while lower at 75%, still registers as a necessary practical requirement for device pairing and initial configuration. Reading these bars together leads to a practical conclusion for planning setup. Prioritize ensuring your device runs iOS 16 Plus, confirm your Mac and Xcode versions are compatible, then secure developer account access, and finally verify physical connectivity. Following that order minimizes setup friction and aligns with the detailed steps described above. Now let's take a look at how we can set up a class in Kotlin for handling API requests. In this example, we define an API service class that will facilitate interaction with a web service. The class begins by initializing an instance of HTTP client, which is part of the Ktor library designed for making asynchronous HTTP requests. By installing the JSON feature, we configure this client to handle JSON data seamlessly, utilizing the Kotlin serializer for automatic serialization and deserialization of JSON objects. This setup is crucial because it simplifies the process of converting JSON data into Kotlin objects and vice versa. Next, we see a suspend function called fetchData, which accepts a URL as a parameter. This function makes a GET request to the specified URL using the client.get method. The suspend keyword indicates that this function can be executed in a coroutine, enabling our app to handle network requests efficiently without blocking the main thread. By leveraging this class, you can easily retrieve data from any web service, which is fundamental for building dynamic applications that rely on external data sources, enhancing user experience significantly. Now let's see how we can implement a simple logging mechanism in our Android application to track essential events. In this code, we define a main activity class which extends app compat activity, establishing the main entry point for our app. First, we set up a constant tag that we will use throughout the class for our log messages, ensuring we can easily identify them. Within the onCreate function, which is called when the activity is first created, we trigger a log statement indicating that the application has started. This provides a clear entry point and helps us confirm that our app's initialization is working as intended. Next, we have a method called fetchData, where we log another important message indicating that data is being fetched from an API. This is a crucial step in our app as it allows us to observe when data retrieval actions occur. Using logging in this way not only helps us during debugging to ensure that our code executes correctly, but also allows for a better understanding of our application's flow during development. By monitoring these logs in Xcode's console with developer mode enabled, we can effectively visualize our app's behavior and troubleshoot any potential issues. Now let's take a look at how we can handle user actions effectively within our application. In the provided code, we have a function designed to capture user interactions, which is crucial for understanding user engagement and behavior. The onUserAction method receives a parameter called action, which represents the specific user input. This is where we log the action, giving us immediate feedback on what type of interaction has occurred. Logging is essential for debugging, as it provides a way to track the flow of user inputs and diagnose any issues that may arise. Next, we see a comment indicating where we can set a breakpoint. This is an important debugging practice that allows developers to pause the execution at specific points in the code. By doing so, you can inspect the current state of variables and evaluate how the application processes user actions. In this case, when the code hits this line while debugging, you can examine the action variable closely, observing how it influences the subsequent call to handle user action. This strategy enhances your debugging efficiency and helps you identify and resolve any potential bugs. Next, we will write the code to handle camera permissions, which is crucial for ensuring that our app can access the device's camera when needed. The first part of our function checks whether the camera permission has already been granted. We achieve this by using context compat check self permission, which returns the permission status. If the permission is not granted, we need to request it from the user. This is where activity compat request permissions comes into play, allowing us to initiate the request for camera access. We pass in an array containing the camera permission and a request code, which we define as camera request code. This code will help us identify the source of the user's response when we receive it. If the user has already granted the necessary permission, we can safely call init camera to proceed with opening the camera interface. To respond to the user's permission decision, we override onRequest permissions result. This method checks if the user granted permission in response to our request. If granted, we call init camera, allowing the app to function properly with camera features. This dynamic permission handling enriches the user experience by requesting permissions only when absolutely necessary. Now let's see how we can implement analytics tracking within our app to gather insights on user interactions. The Kotlin code defines an analytics service class, which includes a method called trackEvent. This method simulates sending an event to an analytics server by logging a message that indicates which event was tracked. It serves as a robust starting point for integrating more sophisticated analytics capabilities into your application. Next, we have a function called onShareButtonClick. This function is triggered when a user interacts with the share button in the app. By calling analytics service trackEvent, it sends a specific event name, share button clicked, to our analytics service. This allows us to monitor how often users engage with the sharing feature of our app. By implementing this code, we enable real-time tracking of user actions, thus providing invaluable data that can guide future updates and enhancements. As we gather this information while working in developer mode, it becomes easier to make data-driven decisions to improve user engagement and satisfaction. As we wrap up this session about developer mode for iOS applications, it's clear that enabling this feature significantly enhances your capability to develop, debug, and optimize your apps. So far, we've explored the requirements for activating developer mode, how it aids in debugging, handling permissions, and even gathering user feedback for better engagement. To summarize, developer mode empowers developers like you to harness the full potential of iOS devices, allowing for a more thorough testing environment that closely mimics real-world usage. It's a hotbed for testing new features and functionalities, ensuring your app remains robust and user-friendly. In our next discussion, we will dive deeper into other advanced features of iOS app development, including app performance optimization techniques and the vital role of user experience design. This knowledge will further enhance your development toolkit, enabling you to create exceptional applications that resonate with users. Thank you for tuning in and happy coding. In today's lesson, we will unravel the significance of developer certificates when it comes to iOS app development. A developer app certificate is an essential file that gets installed on your iOS device alongside your app, allowing your app to run in a trusted environment. This topic is crucial because it not only secures your app, but also enhances the user experience by ensuring that the app has been developed and signed by a legitimate developer. So far, we've learned about the importance of developer mode in iOS app development. We discussed how it enables real device testing, debugging, and managing app permissions. We also covered the prerequisites for setting up developer mode, such as the correct version of iOS and Xcode in addition to an Apple developer account. You now know how developer mode enhances user feedback gathering and analytics integration, aiding app improvements. Now we will delve deeper into the world of developer certificates, exploring how they work, why they're necessary, and how to set them up correctly. Let's start by understanding what a developer certificate truly signifies. A developer certificate serves as a digital signature that links your identity as a developer to your applications. Essentially, it tells the operating system, hey, this app is safe because it comes from an authenticated source. This is fundamental for maintaining trust in the ecosystem, especially as security concerns continue to grow in mobile app development. To begin, you must create a certificate signing request, CSR, which will be used to generate your developer certificate through Apple's developer portal. You can do this easily using Keychain Access on your Mac. In Keychain Access, you'll initiate a certificate signing request. The steps are straightforward. First, open Keychain Access from your Utilities folder. Then in the menu bar, go to Keychain Access Certificate Assistant, request a certificate from a certificate authority. When prompted, enter your email address and a common name. Ensure you opt for Save to Disk, as you will need this CSR file later. Once you've generated your CSR, make sure to save the file securely. You will now go to the Apple Developer Portal, where you can generate your developer certificate by uploading the CSR file. After logging into your Apple Developer account, navigate to Certificates, IDs, and Profiles. From there, select the Certificates section and click on the plus sign to add a new certificate. You will be given multiple options depending on the type of certificate you require, either for development or distribution. Choose the appropriate one and follow the prompts to upload your CSR. Once Apple has processed your request, you will receive a CSR file which you need to download and double-click to add it to your keychain. This file is the developer certificate that verifies your identity as a developer. Now that your developer certificate is installed, let's explore how to associate it with an iOS app ID and a provisioning profile. App IDs serve to uniquely identify apps that you develop, and provisioning profiles tie together your developer certificate, app ID, and the devices on which the app can run. To create a new app ID, go back to the Certificate, IDs, and Profiles section of your Apple Developer account and navigate to the Identifiers tab. Click on the plus sign to create a new app ID. It could be descriptive or use a reverse domain format like com example myapp. After creating your app ID, proceed to set up the provisioning profile. The figure titled Key Concepts in Developer Certificate Management for iOS Apps presents a breakdown of core activities as a proportional pie. Code signing represents the largest segment at 30%, installation follows at 25%, provisioning profile occupies 20%, generation of certificates is 15%, and testing on devices is 10%. From these proportions, we can draw several practical conclusions. First, code signing is the dominant task and thus requires the most attention and mastery, since it comprises nearly 1/3 of the overall activity and directly ensures app integrity. Installation is also a major component, indicating that deploying and installing builds on target machines is a frequent and significant step in the workflow. Provisioning profiles and certificate generation together form a sizable middle portion, 35%, which highlights that managing identities, device lists, and renewing or creating CSRs are routine but often less time-consuming than signing and installation. Finally, testing on devices, while the smallest slice at 10% remains essential, its smaller share suggests it may be scheduled less often or is more targeted, but neglecting it risks missing runtime issues on real hardware. Overall, the chart emphasizes prioritizing robust signing practices and reliable installation procedures, while maintaining organized provisioning and periodic physical device testing to ensure a secure and reliable development lifecycle. Select the Profiles section and click the Add button. Here you can create a new provisioning profile. Choose either development or distribution based on your needs. Choose the app ID you just created, select your developer certificate, and then add the devices you wish to include in this profile. This is how you ensure your app can be installed and tested on those specific devices. After you finalize your settings, generate and download the provisioning profile, then double-click it to install it in Xcode. This process will allow you to run your app seamlessly on your physical devices. Next, let's look at how you can sign your app using your developer certificate and provisioning profile in Xcode. Open your Xcode project and navigate to your project settings. Under the Signing and Capabilities tab, you will find options to select your team in the provisioning profile. You will also notice the Automatically Manage Signing checkbox. You can check this to simplify the process. Xcode will automatically use your developer certificate and provisioning profile for signing when you build the app. However, if you prefer to manually manage this, You can select the specific provisioning profile you've created and ensure that your developer certificate is selected. Here, we're knowing about code signing allows you to ensure that apps correlate with correct certificates before they are deployed. You can check the code signing settings and make sure that everything's in order by navigating to the build settings in your Xcode project. Look for the code signing identity under the Build Settings tab and ensure it is set to your specific developer certificate. When you build your project, Xcode will take all of this information into consideration, signing your app with the developer certificate and validating it against the provisioning profile. But hold on, we're not done yet. Make sure you understand that the development of apps on iOS is iterative and involves a lot of testing. Your app can only run on devices that are included in your provisioning profile. If you try to install the app on an unauthorized device, you will encounter errors. Thus, to test on a new device, you must add its UDID to your developer account, update your provisioning profile, and then regenerate it. That's right, each time you add a new device, you have to jump through these hoops. While this might seem cumbersome at first, it helps maintain a secure environment. Moreover, always check your certificates and provision profiles are up to date, as they can expire and create issues when you try to deploy your app. Now let's talk about how to manage your developer certificates and profiles over time. As your app evolves and new features are added, you may find yourself needing to renew or revoke certificates. To revoke a certificate, simply return to your Apple developer account and under the Certificates section, find the certificate you wish to revoke. This is particularly useful if you've lost a private key or if a developer leaves the team. Once revoked, you can create a new certificate as we discussed earlier. In terms of renewal, certificates are valid for a limited time, usually 1 to 3 years. Be proactive and keep track of their expiration dates. You can easily renew them by creating a new CSR, repeating the process, and ensuring that you replace the expired certificate in your development environment. As you continue to work extensively with developer certificates, it's also a good idea to familiarize yourself with common errors that developers often face during the signing process. One common pitfall is mismatched certificates. This happens when Xcode detects that the provisioning profile on your project doesn't match the ones associated with your developer certificate. This could arise if you haven't updated your profile to include new devices or if you inadvertently used the wrong profile. If you run into issues, don't panic. Clear the derived data in Xcode and reattempt building your app. It can often clear up signing-related bugs and is a good step to integrate into your troubleshooting process. Through this journey of understanding developer certificates, you've gained a critical insight into maintaining security and establishing trust within your applications. This knowledge is imperative as it ensures your app's safe deployment and helps conform to Apple's security measures. Hence, as we conclude, bear in mind that developer certificates play a vital role in the iOS ecosystem. They are essential for the development cycle, ensuring your apps are signed by validated developers and can run on intended devices. Follow the steps we discussed, stay informed about your certificates and provisioning profiles, and you'll pave the way for a smoother iOS development experience. In our next lesson, we will cover advanced features in iOS development, enhancing how we build apps and explore tools that can elevate your projects to the next level. Until next time, keep coding. Let's dive into the fascinating world of iOS development and simulator usage. Understanding the tools at your disposal is crucial for creating effective applications, not just for iOS but for any platform. Today, we're going to explore how the iOS simulator functions, when to use it, and why testing on actual devices can't be overlooked. So far, we learned about the significance of developer certificates in iOS app development, which act as digital signatures linking a developer's identity to their applications. We explored the process of generating a developer certificate through a certificate signing request, CSR, and how to associate it with app IDs and provisioning profiles. Additionally, we discussed the importance of signing apps in Xcode with the appropriate developer certificates and provisioning profiles for secure deployment. As we continue, we will dive into advanced features in iOS development to further elevate our projects. Now we will cover the iOS development environment, focusing on the iOS simulator and touching upon its strengths and limitations. The iOS simulator is part of Xcode, Apple's official integrated development environment, IDE. It acts as a virtual iOS device where you can run and test your applications without needing actual hardware. The simulator closely mimics iOS devices, providing a robust environment for early-stage development. However, it's crucial to note that some hardware components, such as the camera or GPS, cannot be fully emulated, which may lead to discrepancies between the simulator and physical devices. The displayed pie chart titled Understanding iOS Development, Simulator versus Real Devices divides the workflow into three labeled slices: simulator strengths at 40%, simulator limitations at 30%, and real device testing at 30%. The largest segment, 40%, quantifies the portion of development and verification that the simulator can handle efficiently, tasks like rapid UI iteration, basic logic validation, and testing across OS versions. The other two equal segments, each 30%, highlight a direct relationship between the simulator's shortcomings and the necessity of real device validation. The simulator limitations slice captures areas that the simulator cannot fully reproduce: hardware sensors, camera behavior, live performance characteristics, while the real device testing slice indicates the effort required on physical devices to confirm correct behavior in those very areas. Taken together, the chart shows that although the simulator is the primary environment for early and frequent testing, 2/5 of the effort, a clear majority, 60% of final validation work, relies on recognizing limitations in the simulator and executing equivalent checks on real hardware. The use of green for strengths versus orange and red for limitations and device testing visually reinforces that strengths are distinct and measurable, but that substantial verification must occur on actual devices to ensure real-world correctness. Now let's implement the following code to simulate obtaining a user's current location within our application. This function creates a mock location as if it were being retrieved from a GPS device. Initially, we import the necessary location class, which allows us to handle location data effectively. In the getCurrentLocation function, we instantiate a new location object and specify a provider name, a dummy provider in this case, indicating that this is not a real GPS provider. Next, we set the latitude and longitude of the location to Apple's headquarters coordinates, a latitude of 37.3349 and a longitude of -122.009. This setup enables us to test location-based functionality by providing a predetermined location for the application to use. Finally, the function returns this location object, allowing our app to interact with it just as if it had received a real-time location update. While this won't reflect actual movements, it effectively helps us test geolocation features in a simulated environment, ensuring our app can handle location data appropriately when it eventually runs on real devices. Now let's see how we can implement camera functionality in our Android app using the Camera Access API. This implementation begins with importing necessary classes, such as manifest, activity, and intent, which help manage permissions and user interactions. The camera activity class extends the activity class, allowing us to manage the camera interface within our application. Within this class, we define a constant request code, request image capture, which we'll use to identify the result when we request camera access. The capture image function is where the magic happens. This method first checks if the app has been granted camera permissions. If the permissions are not granted, it requests the necessary permission from the user. It's important to handle permissions correctly to ensure a smooth user experience. Users must always be informed about why specific permissions are needed. If the permission check passes, we create an intent to launch the camera interface. By using startActivity4Result, we initiate activity that captures an image, allowing us to handle the returned result accordingly. This structured approach ensures that users can seamlessly take pictures, although testing this functionality on a simulator may not provide the same experience as on actual devices, highlighting the limitations we discussed earlier. Now let's see how we can implement a push notification using Firebase Cloud Messaging in our application. The code starts by creating a remote message object, which is essential for defining the content of the notification. We use the builder pattern to construct this object, allowing us to set various properties for the message easily. First, we specify a topic to which the message will be sent, ensuring that our target audience is correctly defined. Following that, we set a unique message ID, which is useful for identification and tracking purposes within Firebase's systems. Next, we can add custom data to the notification payload using the addData method. This allows us to include key-value pairs that our application can utilize when processing the notification. Finally, we send the constructed message through the Firebase messaging instance. By calling send, on this instance with our message as an argument, we ensure that the push notification is dispatched to the designated topic. This code effectively demonstrates how to set up and send notifications, but remember that testing this implementation in a real device environment is crucial to validate user experience and interaction fully. Now let's see how we can verify the current OS version programmatically in our application. The first part of the code retrieves the current SDK version using build version SDK-int. This is essential for understanding what features or behaviors may be available based on the device's operating system. Next, we use a when statement to evaluate the current version. This construct allows us to execute different blocks of code depending on which version of the OS is in use. For instance, if the OS version corresponds to build version codes, the application can perform a specific action designed for Oreo. Similarly, for build version CODSB, the code will trigger actions pertinent to Pi. It's important to note that the else block serves as a catch-all for any versions not explicitly handled, ensuring that we can provide a general response for other OS versions. This flexibility is vital for maintaining compatibility across various devices, and while this approach runs seamlessly in the simulator, it's a good practice to test it on real devices to confirm it behaves as expected in diverse environments. Now let's implement a simple snippet for checking user input validation. The code begins with a conditional statement that evaluates whether the user input is valid by calling the isValidInput function. If the input is deemed invalid, the program executes the first branch, which prints invalid input to the console. This immediate feedback is crucial for guiding users to correct their entries, ultimately enhancing the user experience. On the other hand, if the input passes the validation check, the program will execute the else branch where it outputs valid input. This kind of clear communication is essential in applications as it allows users to know the result of their actions right away. By implementing this structured approach, you can integrate input validation effectively into your applications, ensuring that only appropriate data is processed. This method not only aids in debugging by providing logs of user interactions, but also serves to inform users promptly, thus making error tracing and fixing more efficient during development. Monitoring the console for these outputs will help identify and rectify issues as you transition your project from development to testing. In summary, the simulator is an invaluable tool for rapid development, allowing for quick iterations and testing of basic functionality. However, it can never replace the need for actual device testing when it comes to hardware integration, performance evaluation, and user interaction scenarios. As we continue refining our iOS development skills, remember to balance your time between the simulator and real devices. This way, you'll be equipped to create applications that provide a flawless experience, catering to the user's needs. In our next session, we'll delve deeper into using external libraries within our projects and how to effectively manage dependencies. We'll empower ourselves to utilize community resources, enabling our applications to achieve greater functionality and performance. To get started with developing apps for iOS devices, it's important to understand how to run your apps directly on an iOS device using developer mode. This process allows you to install and test applications you create in Xcode on actual hardware, which is crucial for discovering how the app performs in real-world conditions. Here's how to get everything set up. So far, we learned about the iOS simulator, a valuable tool that allows developers to test apps in a controlled virtual environment. We discussed its advantages like rapid deployment, support for various iOS versions, and debugging functionalities. However, we also noted its limitations, particularly regarding the necessity of real device testing to ensure an optimal user experience. Now we will cover how to run your app directly on an iOS device using developer mode, ensuring you can effectively utilize hardware capabilities in your applications. To start running your app on an iOS device, first, you need to prepare your device for development. This means enabling developer mode, which allows your device to trust your development machine and install apps directly from Xcode. It's quite easy, just head over to *settings *privacy and security ***. There you will find an option for *developer mode ***. Turn it on and your iPhone or iPad will restart. Don't fret, this is a typical procedure you'll encounter. Once your device has restarted, you will be prompted to confirm that you want to turn on developer mode. Tap Turn on ***, and after the few extra security prompts, you will have successfully set up your device to communicate with Xcode. This step ensures that all your applications thus installed will run without being barred by system restrictions. Now that your iOS device is ready, let's head to Xcode. Open up your project and select your connected device from the top of the Xcode screen. This might seem straightforward, but if you see your device grayed out, you may need to troubleshoot a bit. Ensure that your device is unlocked, as Xcode cannot deploy to a locked device due to security reasons. Figure 1 presents a rank bar chart labeled Key Concepts in iOS Development that quantifies the perceived importance of 5 core topics: developer mode 90%, real device testing 85%, error handling 80%, protocols 75%, and extensions 70%. The bars descend in uniform 5-point increments from developer mode down to extensions, producing a clear linear ordering. 2 immediate patterns stand out. First, the highest priorities are device-oriented. Developer mode and real device testing occupy the top 2 positions, indicating that getting the device configured and validating behavior on hardware are primary concerns. Second, error handling sits squarely in the middle at 80%, signaling that robustness and resilience are nearly as critical as device setup. Protocols and extensions, while still important, 75% and 70%, trail slightly behind, suggesting that architectural refinements and language features are important but secondary to ensuring the app runs reliably on hardware. From these values, you can conclude a practical sequence for focus. Prioritize enabling developer mode and establishing real device testing workflows, invest in thorough error handling to protect user experience, and then refine code structure through protocols and extensions to improve maintainability and reuse. Now let's implement a simple SwiftUI application that displays a greeting message. The code begins with the necessary import statement for SwiftUI, which allows us to create user interfaces in a declarative way. We define a structure called ContentView that conforms to the view protocol, which is required for any view in SwiftUI. Within the ContentView, we specify the body property where we construct our user interface. Here we use a text view to display the message "Hello, iOS developer." This text is enhanced through the addition of padding for better spacing around the text and is styled with the large title font to make it visually prominent. Next, we define the MyApp structure that serves as the entry point for the application, marked by the @main attribute. Inside MyApp, we also define the body property, which creates a scene. The window group serves as a container for our content view, ensuring that when the app launches, our greeting interface is presented to users. This straightforward implementation sets the stage for exploring more complex features as we learn about developing iOS applications. You're going to observe that your app launches on the device. You'll also be able to see the logs in Xcode, which can help track down any issues as they arise. Remember, testing on a real device is a foolproof way to assess not just performance, but also how your app handles hardware features such as notifications, GPS, and more that the simulator cannot replicate accurately. Another key benefit of using developer mode is debugging capabilities. Having your app on a real device allows you to leverage Xcode's debugging tools effortlessly. For example, if you're experiencing issues with app performance or crashes, you can attach the debugger to your running app on the device by selecting Debug * from the top menu and choosing Attach to Process by PID or Name *. This will enable you to delve deeper into the app's execution and identify potential bugs more easily. Now let's implement the following code to create a simple camera capture interface using SwiftUI. This code introduces a structure called CameraView, which conforms to the UI View Controller Representable protocol, allowing SwiftUI to manage a UIKit view controller. Within the Make UI View Controller method, we initiate a UI View Controller, which will host the camera interface. Inside this method, we also create an AV capture session, a crucial component that orchestrates the flow of data from the camera hardware to the app. Although additional setup for the camera, like configuring inputs and outputs, is needed for a fully functional camera interface, this snippet establishes the foundation for rendering live camera content. The Update UI View Controller method is currently empty, but it can be used to update the view controller as the SwiftUI state changes, ensuring that the camera interface remains responsive to user interactions. Lastly, by integrating this camera view into your main app structure, you facilitate the real-time interaction between your app and the actual iPhone camera, allowing for hands-on testing of camera functionalities such as zoom and focus right on the device. Now let's take a look at implementing a simple logging system in Swift that can significantly aid in tracking your app's performance and debugging issues. This code introduces a custom logger struct that utilizes the oslog framework, which is essential for effective logging on iOS. First, we define a static subsystem and category which categorize the logs, making it easier to filter and manage them later. The main feature of our logger is the log message function, which takes a string message as a parameter. This function utilizes oslog to log the message with a specified log type, in this case, info. The oslog function is particularly valuable because it allows for structured logging and can capture privacy-sensitive data safely using the %publicat format specifier. Finally, we showcase how to use the logger by calling logger with a message illustrating how straightforward it is to integrate this logging system into your app's lifecycle. By embedding logging in this manner, you gain insights during real-time interactions, which is critical for identifying issues that may arise only when your app is on actual hardware. An important aspect of running apps on devices is managing your provisioning profiles and certificates. This setup grants your app privileges to run on your particular device. For personal projects, you typically manage this automatically within Xcode. Just ensure you're logged in with your Apple ID connected to the developer program. But for any team collaboration, understanding how to set up and manage these credentials is crucial for a smooth development process. Finally, as you navigate through the development on an iOS device, be open to feedback from your device testing. Engage with beta testers, take their input, and iterate on the design based on real-world usage. The insights gathered from your app running on actual hardware provide invaluable data that can shape the direction of your application's development. In summary, we've covered the process of running apps on iOS devices using developer mode, emphasizing the practical advantages. We discussed how to enable developer mode on your device, set up Xcode to deploy your applications, and explore real device interactions. We also reviewed debugging techniques and logging best practices while hinting at the importance of managing your app permissions effectively. As we conclude this lesson, consider how the insights gained through real device testing can shape your approach to app development. Whether you're developing simple applications or more complex solutions that leverage the power of iOS devices, the experience of testing on actual hardware is irreplaceable. Embrace it and let your apps shine brightly. Now let's explore the exciting world of building and running iOS apps with Xcode. In today's session, we'll dive into the fundamentals of Xcode and its powerful capabilities to create amazing iOS applications that work seamlessly on actual devices. We'll focus on the importance of real device testing, understanding its advantages over the simulator, and how to set everything up for efficient development. So far, we covered the significance of using developer mode on iOS devices for app development and the preparation required to get your device ready for Xcode. Let's build on that foundation and delve deeper into how to harness Xcode's potential to bring your iOS apps to life. Next, we will write the following code to set up the essential configurations for our app. Here, we define three key parameters: the application's unique identifier name and version. The appid variable holds the bundle identifier, which is crucial for distinguishing our app on the App Store and must follow a specific reverse domain name format, in this case, com example myfirstapp. Next, we set app name to myfirstapp, which serves as the display name for our application. This name will be shown to users on their devices and in the App Store listings, making it an important aspect of our app's identity. Lastly, we define app version as 1, indicating the current release of the app. This versioning is significant not just for updates but also for user feedback and support. By establishing these foundational elements, we ensure that our app is correctly recognized and managed both during development and after its release. These initial settings provide a solid groundwork as we progress with building the functionality and user interface of our app. Now let's see how we can implement a simple user interface in SwiftUI to display a greeting message. We start by importing the SwiftUI framework, which provides the necessary tools for building user interfaces in iOS apps. Next, we define a struct named ContentView that conforms to the View protocol, a requirement for creating views in SwiftUI. Inside the content view, we declare a computed property called body, where the layout and content of the view are defined. Here we use a text view to display the message "Hello World." This is the foundational building block of our UI. To enhance the appearance, we apply the font large title modifier, which changes the text to a larger size, making it more visually striking. Additionally, we add the padding modifier, which creates space around the text, improving the overall layout and readability. It's important to understand that in SwiftUI, this declarative approach simplifies UI development, allowing us to focus on the content and appearance of our app without manually managing the view hierarchy. This snippet serves as a great starting point for building your app's user interface. Now let's talk about how you can see this app in action. You can run your app on the simulator, which is a great way to test your interface. However, as we mentioned earlier, testing on an actual device is crucial because certain components, like the camera, GPS, or gyroscope, can only be accessed with a physical device. To set up your iOS device for testing, connect your device to your Mac using a USB cable. Make sure your iOS device is unlocked and you have trusted your Mac in the device settings. Navigate to Xcode, select your device from the device toolbar, and hit the play button to build and run your app. If everything is set up correctly, you'll see your Hello World message on your iPhone or iPad. The displayed bar chart titled Processes in Building an iOS App compares 3 labeled processes: toast, eggs, and plate and serve by their durations in seconds. Each bar is annotated with its numeric value. Toast equals 2s, eggs equals 7s, and plate and serve equals 1s. Visually, the eggs bar is the tallest and dominates the chart, representing 70% of the total combined time, 7 out of 10 seconds, while toast represents 20%, 210, and plate and serve only 10%, 110. The key pattern is a clear imbalance. One process, eggs, is the primary time consumer, with the other 2 processes contributing relatively little individually. From these values, we can conclude that reducing the time of the eggs process would yield the largest reduction in overall duration. Optimizing toast or plate and serve yields smaller gains. The color coding, green for toast, blue for eggs, orange for plate and serve, and the numeric annotations make it straightforward to identify which step is the bottleneck and prioritize efforts accordingly. Now let's implement a button that changes the displayed text when tapped. In this code, we define a struct content view conforming to the view protocol, which serves as a fundamental building block for our app's user interface. Within this struct, we declare a state variable named message. This state variable is crucial because it allows SwiftUI to track changes and update the view dynamically whenever the button is pressed. Next, we set the body property, which describes what the UI will present. It contains a vertical stack, vstack, which organizes our elements vertically. Inside this stack, we have a text view that displays the current value of the message variable, making it easy to show different messages based on user interactions. Below the text, we add a button that triggers an action when tapped. This button features a closure that updates the message variable to a new string, Hello iOS Developer. The button is styled for better user experience, including a background color, font size, and corner radius. This structure lays the groundwork for creating an interactive and engaging application, further enhancing user experience as they interact with the UI. With your app blossoming into a fun interactive experience, let's shift gears and discuss the debugging process. Debugging is a crucial part of development, and Xcode offers powerful tools to help. When you run your app on a device, you can inspect variables, set breakpoints, and evaluate expressions in real time. For instance, if you want to inspect the value of message while debugging, you can add a breakpoint in your code where you think a bug may occur. Simply click in the gutter next to the line number and a blue arrow will appear indicating a breakpoint. When you run your app and reach that point, Xcode will pause execution, allowing you to examine the state of your variables, including message. This ability to step through your code is invaluable for troubleshooting unexpected behavior. Now let's implement logging within our button action to better track user interactions. In this part of the code, we begin by defining a button that, when tapped, updates the displayed message. The button is set up using an action closure that changes the value of our message variable to Hello iOS Developer. What's significant here is the addition of a print statement right after the message update. By using the print function, we log a message to the console each time the button is tapped. This log output includes the current value of the message variable, providing us with real-time feedback about the button interaction. Logging is an essential practice during development, as it allows you to monitor your app's behavior and make it easier to diagnose issues or understand user behavior when you revisit the code later. Implementing this logging mechanism enriches the development process by creating a clear audit trail of user actions, which can significantly aid in debugging and performance tracking. With this feature, you'll gain deeper insights into how users are engaging with your app and can identify areas that may need further attention or improvement. As we bring our session to a close, let's circle back to the importance of beta testing on real devices, which we lightly grazed earlier. Real device testing not only uncovers bugs that would go unnoticed in the simulator, but also helps in evaluating the app's performance under actual user conditions. Feedback collected during beta testing can significantly influence user experience by refining interfaces and fixing performance issues. It's also recommended to use TestFlight, Apple's official beta testing platform, to distribute your app to testers easily. TestFlight allows you to invite users to test your app before its public release and gather invaluable feedback to iterate and refine your product. In conclusion, today we journeyed through the essentials of building and running iOS apps using Xcode. We pressed on to create an interactive app, implement debugging techniques, and utilize logging for performance monitoring. Understanding the importance of real device testing and organizing a solid beta testing strategy rounds out our exploration, preparing you for tackling the wild world of mobile development. So remember, whether you're developing for fun or aiming for the App Store, focus on building a useful app that addresses users' needs, embrace testing methods, and dive into user feedback. Your journey as an iOS developer is just beginning, and the best part is yet to come. Until next time, keep coding and creating. Let's dive into the world of Swift language basics for iOS development. Today, we will explore how Swift operates, focusing on its simple values and types. Understanding these core components is essential for building any iOS application, so let's get started. So far, we've covered building and running iOS apps with Xcode, emphasizing real device testing. We explored creating a basic iOS app with SwiftUI, adding interactivity with buttons, and discussed debugging and its importance. Now we will talk about Swift's fundamental values and types, laying the groundwork for everything you'll do in iOS development. Swift is known for its clarity and concise syntax, making it an excellent choice for beginners and experienced developers alike. Now let's see how we can implement variables and constants in Swift, which are fundamental to managing data in our applications. In this example, we declare a variable named myVariable and initialize it with a value of 10. Using the var keyword indicates that this value can be changed later in the program, making it dynamic and adaptable. On the other hand, we also declare a constant called myConstant and set it to 20 using the let keyword. Constants are fixed values that cannot be altered once assigned, ensuring data integrity throughout the application. This distinction is critical, especially when building features like a user count in an app. You wouldn't want to accidentally change a constant that is intended to remain unchanged. Thus, understanding when to use variables versus constants helps protect the structure and logic of your code. For instance, if we tried to reassign myConstant to a different value, Swift would generate an error, thereby preventing potential bugs in our application. The displayed chart titled Key Concepts in Swift Language Basics for iOS Development quantifies the relative importance of 6 core topics on a 120 scale. Data types registers the highest importance at 15, followed by collections at 12, variables at 10, constants at 8, control flow at 7, and optionals at 5. These labeled bar heights in their numeric annotations show a clear ranking. Types and collections are emphasized most, suggesting they form the conceptual backbone, while optionals, though essential, are shown with the lowest importance rating in this view. From these values, we can conclude that prioritizing study and practice on data types and collection handling will yield the greatest return for foundational understanding. With solid attention to variables and constants next, and targeted review of control flow and optionals to round out competency. Now let's take a look at how to declare different data types in Swift, which is crucial for managing the data your application will handle. In this example, we define 4 variables with explicit types. An integer is declared as an int and initialized to 100, making it a whole number suitable for counting or indexing. Next, a double is declared as a double, which allows for floating point numbers and is initialized to 75.5, perfect for scenarios requiring decimal precision, such as calculations involving currency or measurements. We also introduce a string, declared as a string and initialized with the text hello Swift. This variable can hold any textual data from user inputs to messages displayed in the app. Lastly, we have a boolean, which is of type bool and initialized to true, representing binary states such as on/off or yes/no. By using explicit type declarations, Swift not only makes your intentions clear but also catches type-related errors at compile time, thus enhancing code safety and reliability. This approach ensures you're working with the correct data types throughout your application, leading to fewer bugs and a smoother user experience. Now that we've established variables and types, let's take a look at how Swift's type inference simplifies code writing. In Swift, when you assign a value to a variable, the language can often infer the type automatically based on that value. This means you don't always have to explicitly declare the type, which can make your code cleaner and more concise. Next, we will write the following declarations. First, we create a variable called inferredInt and assign it the integer value 42. Swift recognizes this assignment and infers that inferredInt is of type int. Similarly, we declare another variable, inferredString, and assign it the string inferred. Again, Swift infers the type correctly as string. This ability to deduce types based on initial values allows us to focus more on the logic of our code, instead of being bogged down by verbose type declarations. Thus, utilizing type inference can significantly enhance developer productivity while maintaining code clarity. Now let's take a closer look at optionals in Swift. An optional allows a variable to hold a value or have no value at all, represented by nil. To declare an optional variable, we utilize the question mark suffix. For instance, when we declare optional int as int, it can either hold an integer or indicate that it has no value. This is crucial for avoiding crashes caused by trying to access non-existent data. Next, we will implement the optional by initializing it to nil, which is perfectly valid. Later, we can assign it an integer, such as 10, changing its state from nil to holding a specific value. This flexibility keeps your app stable, as it allows for scenarios where data might be unavailable without resulting in an error. Now let's see how we can safely access the value held inside an optional. The if-let syntax is a common way to perform optional binding, which checks whether optional int contains a value. If it does, the unwrapped value is assigned to a new variable value and we can safely print it. If optional int is still nil, the else block will execute, confirming that the optional is vacant. This approach enhances code safety and prevents potential runtime errors. Now let's implement an array in Swift specifically for storing a collection of fruits. We start by declaring the array called fruits, which is defined to hold strings. This means each element in the array will be a type of fruit represented as text. We initialize the array with 3 fruit names: apple, banana, and cherry. To access a specific item in the array, we use its index. Since arrays in Swift are zero-indexed, we can access the first item, apple, by referencing fruits 0. This is a straightforward way to retrieve data from the array. Additionally, arrays are dynamic, allowing us to change their content at runtime. For instance, if we want to add another fruit, we can use the append method. In this case, we add date to the fruits array. This flexibility enables developers to manage collections of items easily, making arrays an essential aspect of handling multiple values in Swift programming. Thus, arrays provide both a structured way to store data and the capability to manipulate that data as needed. Now let's see how we can work with sets in Swift. Sets are designed to hold unique values, which means they automatically handle any duplicate entries for us. In the example given, we initialize a set called unique numbers with some integers, including a duplicate value of 2. However, Swift ensures that only one instance of each value is stored, so even if we attempt to add the duplicate, it only retains it once in the collection. Following this, we can utilize the insert method to add a new value, in this case 4. This action enhances our set by including a new element while maintaining the uniqueness property of the set. Lastly, we use print to display the contents of unique numbers. It's important to note that the output may not maintain the order of insertion, as sets do not guarantee the order of elements. Sets are highly beneficial when we need to ensure that our data collection remains free of duplicates, making them ideal for many applications in Swift development. Now let's take a look at how we can implement a dictionary in Swift. A dictionary allows us to store pairs of keys and values, making it easy to manage and retrieve data. In our example, we have declared a dictionary called user profile that holds information about a user. The keys are represented as strings, which help us identify the type of data we're storing, such as the user's name and email. To initialize the dictionary, we've provided key-value pairs: name for the user's name and email for their email address. This structure allows us to easily access and modify data. For instance, we can retrieve the user's name by referencing the key name and using the force unwrap operator to insist that a value exists at that key. However, it's important to remember that force unwrapping can lead to runtime errors if the key is not present, so it should be used carefully. We also demonstrate adding a new key-value pair by setting user profile age to 30. This shows how dictionaries can be dynamically modified to suit your application's data needs, illustrating their flexibility and utility in managing structured information. Now let's take a look at how we can implement an if statement to evaluate a score and provide feedback based on the performance. In this example, we start by declaring a constant called score and assigning it a value of 85. This sets the stage for determining the user's performance level. Using the if statement, we first check if the score is greater than or equal to 90. If this condition is true, Swift will execute the code within the curly braces and print excellent, indicating top performance. If the score does not meet this threshold, we use an else if statement to check if the score is at least 75. If this second condition is met, Swift responds with good job, signaling solid performance. Finally, if neither condition is fulfilled, the else block triggers, printing keep trying, to encourage the user to improve. This structure provides a clear decision-making path based on different score values, illustrating how control flow works in Swift to manage program outcomes dynamically. Such control flow mechanisms are vital for developing responsive applications that react appropriately to user inputs or conditions. Next, we will write the following loop to illustrate how iteration works in Swift. Here, we are using a for loop, which allows us to execute a block of code repeatedly for a specified range of values. In this example, the loop iterates from 1 to 5, effectively executing the codes inside the curly braces 5 times. Within the loop, we have a print statement that outputs a message indicating the current iteration number. The syntax \index is used to include the value of index in the message, showcasing Swift's string interpolation feature. This means that as the loop runs, it substitutes the current value of index into the string, and you would see a sequence of messages displaying this is iteration number 1, followed by 2, 3, 4, and finally 5. This concise structure not only demonstrates the power of loops for repeating actions, but also emphasizes how Swift syntax facilitates readability and ease of use while coding. Loops like this are crucial for tasks that require repetition, making them a fundamental concept in programming logic. Now that we've explored the basic building blocks like values, types, collections, and control flow, it's time to piece it all together. Remember, each of these elements plays a significant role in the way we structure our code and the functionality of the apps we develop. By combining variables, constants, data types, optionals, collections, and control flow, you can create dynamic and responsive applications. As you move forward, practice is essential. Write small applications, experiment with the concepts we discussed, and don't hesitate to make mistakes. That's part of learning. In conclusion, we've covered essential Swift language basics that every iOS developer should know, from variables, constants, and data types all the way to collections and control flow structures. This foundational knowledge will empower you to build engaging and interactive apps for iOS. Make sure to consolidate what you've learned today by writing code and creating your own projects. The best way to learn programming is by doing create, experiment, and iteratively improve your skills. Now go ahead, open Swift Playgrounds or your favorite IDE and start coding. Who knows what amazing apps you'll create? Happy coding! To excel in iOS development these days, understanding the developer mode requirements is essential. This relatively new mode, introduced by Apple during the Worldwide Developers Conference in 2022, has become a cornerstone for developers working with devices running iOS 16 or greater. In our discussion today, we will dive deep into what developer mode is, why it's necessary, and how you can enable it on your devices. Now let's see how we can implement a simple view controller that checks if developer mode is enabled on an iOS device. This code defines a class named Developer Mode View Controller, which inherits from UI View Controller, a fundamental building block for iOS apps. In the viewDidLoad method, called when the view is loaded into memory, we initiate the process by invoking the checkDeveloperMode function. This function's role is to verify the status of developer mode and return an appropriate message. If developer mode is detected as enabled, it returns a confirmation message to the developer, whereas if it's not enabled, it prompts the user to enable it through device settings. The check for whether developer mode is enabled occurs in the isDeveloperModeEnabled function. Currently, this function simply returns true, indicating that developer mode is enabled, but in a real-world scenario, you would include actual system checks to determine this status. In summary, this straightforward implementation allows developers to quickly identify their developer mode status, an essential step in the iOS app development process. The accompanying pie chart titled Distribution of iOS Development Tools Among Developers displays the percentage shares for 6 categories: Xcode 40%, Swift 30%, Objective-C 15%, UIKit 7%, SwiftUI 5%, and Other 3%. The largest slice is Xcode at 40%, visually emphasized as the exploded segment, which indicates it is the single most commonly represented category in this distribution. Swift follows as the second largest slice at 30%, so together Xcode and Swift make up 70% of the total, highlighting a clear concentration in the modern Xcode plus Swift toolchain. Objective-C holds a notable 15%, showing that legacy language use is still present rather than negligible. The UI frameworks UIKit at 7% and SwiftUI at 5% appear as smaller slices, with UIKit represented slightly larger than SwiftUI, which suggests that established UI tooling has a larger share than the newer declarative framework in this dataset. Finally, Other is a minor 3%. From these proportions, we can conclude the dominant role of Xcode and Swift in this sample, the continued presence of Objective-C, and that UI framework usage, UIKit and SwiftUI, occupies a smaller portion of the distribution. Now let's take a look at a practical example of how we can fetch and display user data in Swift. We define a function called fetchUserData, which serves as the main entry point for retrieving and printing user information. Within this function, we call another method, getUserData, which returns a string representing the user's name, in this case, John Doe. The key line in fetchUserData is the print statement, which outputs the fetched user data to the console. This is where we can set a breakpoint while debugging. A breakpoint is a helpful tool that allows us to pause the execution of our code at this specific line, enabling us to inspect the value of the user variable. This insight is crucial when troubleshooting any potential issues or understanding the flow of data within our application. By using the debugger effectively, we can monitor how variables change in real time, making it easier to identify what might be causing problems in our app. This hands-on debugging technique is invaluable for refining our coding skills and enhancing the overall quality of our applications. Now let's take a look at how to configure your app's info list to support background execution. By adding the specified lines to your info list, you are declaring that your application can handle tasks while running in the background. Specifically, these entries allow your app to perform operations related to fetching data and receiving remote notifications even when it's not actively in use. This setup is essential for applications that require real-time updates, such as delivery tracking apps. When you include keys like fetch and remote notification, you instruct iOS to give your app the necessary permissions to maintain connectivity and update content, enhancing the overall user experience. Now let's see how this integration with developer mode plays a crucial role. With developer mode enabled, you can see how these background capabilities behave in real time on an actual device, providing immediate feedback as you test features like live activities. This seamless functionality ensures that your app can meet users' expectations for up-to-date information, even when not in the foreground. As you progress through the iOS development pathway, understanding how to handle projects effectively becomes crucial. Developer mode comes in handy when you need to manage multiple projects or collaborate with other developers. You can easily switch between applications and see how they interact with devices, saving precious time when debugging shared code bases. Always remember, when you are working with developer mode, you should ensure your code is production ready. Rarely do developers venture outside Apple's guidelines, as doing so can result in application rejection during the submission process. Therefore, practicing good coding standards is essential. Moreover, while you're debugging, you might want to be cautious about sharing your project files with others. Sharing only your projects, Xcode proj file or compiled binaries can prevent others from running your code in developer mode on their devices. Lastly, to wrap up our discussion on developer mode, it's essential to keep in mind that this feature is not just a tool for running apps, but a bridging pathway to better performance and user experience. As you become more familiar with the requirements and functionalities of developer mode, you'll find ways to leverage them to enhance your app's functionality and stability. In conclusion, we've covered what developer mode consists of, how to enable it, and the significance it brings to your iOS development efforts. We also focused on how it enhances your testing capabilities and interaction with real devices, ensuring your applications are as polished as possible when they reach the end users. As you continue on this journey with iOS development, embrace the tools at your disposal, including developer mode, to turn your innovative ideas into reality. Happy coding! Let's dive into the basics of Swift language as we begin our journey into iOS development. Swift is a powerful and intuitive programming language designed by Apple, making it easy to build apps for iOS, macOS, watchOS, and tvOS. It's designed to be both safe and fast, providing modern language features while maintaining high performance. Now let's see how we can implement variables and constants in Swift. In the first part of our code, we declare a variable named greeting, assigning it the string hello world. This demonstrates Swift's use of the var keyword, indicating that the value can be modified later. For example, the greeting variable can be easily updated to hello iOS, without any complications. This flexibility is essential when dealing with values that may change during program execution. Next, we introduce a constant named pi, initialized to the floating point number 3.14159 using the let keyword. Constants are crucial for maintaining values that should not change, which enhances code safety and clarity. If you attempt to modify pi later in the code, Swift will raise an error, ensuring that critical values remain unchanged. This showcases the importance of using constants for fixed values in your applications. By practicing with variables and constants, you can write safer and more maintainable Swift code, reinforcing solid programming principles while exploring the fundamentals of iOS development. Now let's take a look at how we can define variables with different types in Swift. In the first piece of code, we declare 4 variables: age, height, name, and as student. The variable age is set to 25 using the int type to represent an integer value. Next, height is assigned a double value of 5.9 utilizing the double type, which allows us to store decimal numbers. The name variable is defined as a string where we assign it the value Alice, showcasing how we can use text data. Lastly, isStudent is a Boolean type representing true or false, indicating whether Alice is a student. Now let's see how we can implement Swift's type inference with the variable temperature. Here, we assign the value 37.5 to temperature without explicitly stating its type. Swift automatically infers that this variable should be of type double, highlighting the language's ability to simplify code while maintaining type safety. This flexible type system allows for easier and cleaner variable declarations, an essential feature in Swift programming. Now let's see how we can implement control flow in Swift using an if statement. Control flow allows us to execute different blocks of code based on varying conditions, which is essential for creating dynamic and responsive applications. In this example, we check whether a variable isStudent holds a Boolean value that indicates if Alice is a student. If isStudent is true, the code will print a message stating Alice is a student, utilizing string interpolation to include the value of the name variable seamlessly within the string. This demonstrates how Swift string interpolation can enhance readability and convenience, allowing us to embed variables directly in output messages. On the other hand, if isStudent is false, the else clause activates and it prints that Alice is not a student. This use of conditional logic is fundamental in programming, empowering us to tailor responses based on user data or application states effectively. By mastering such control flow statements, you can significantly enhance the interactivity and functionality of your applications. Next, we will explore how to use a for loop to iterate through a series of numbers. The example code prints the numbers from 1 to 5 using the closed range operator, which includes both the starting and ending values. In this loop, number represents the current value in the sequence. As the loop executes, the print function displays a message for each number, showcasing Swift's powerful string interpolation that allows embedding variables directly into strings. This means that during each iteration, as number changes, the output dynamically updates to reflect the current value. As a result, you'll see a clear output of each number in the specified range, reinforcing how loops can simplify repetitive tasks in coding, making your programs more efficient and manageable. This technique is foundational in programming, enabling you to handle ranges and repetitive actions effortlessly. Now let's take a look at using a while loop in Swift to manage iterations based on a condition. In this example, we start with a variable called count, initialized to 5. The while loop continues to execute as long as count is greater than 0. Within the loop, we print the current value of count, allowing us to visualize the countdown process. Each time the loop runs, we decrement the value of count by 1 using the shorthand count equals 1. This adjustment ensures that the loop will eventually terminate when count reaches 0. The print statement demonstrates how Swift's string interpolation works, seamlessly integrating the variable count into the output message. This loop is particularly useful in situations where the number of iterations isn't predetermined, such as counting down or waiting for a user action. By utilizing a while loop, you can effectively manage repetitive tasks, relying on conditions rather than fixed numbers, showcasing one of the powerful features of control flow in Swift. Let's examine a straightforward function designed to calculate the area of a rectangle. In Swift, to define a function, we start with the func keyword, followed by the function's name and a set of parentheses containing its parameters. For this example, our function is called calculateArea and it accepts 2 parameters, width and height, both of which are of type double. This allows us to input decimal values, which is crucial for precise calculations involving measurements. The return type of the function is denoted using the arrow syntax, which indicates that it will return a double value representing the area obtained by multiplying width by height. This organization of logic within a function not only improves the readability of the code, but also encourages its reusability. Next, we'll see how to implement the function by invoking it with specific width and height values, 5, 0, and 10. After storing the resulting area in a constant named area, we can print the result via string interpolation. This outputs the area as 50, confirming that the function operates correctly and highlighting the fundamental aspects of defining and utilizing functions in Swift. The accompanying bar chart titled Key Concepts of Swift Language Basics shows 7 categories across the x-axis: variables, constants, data types, control flow, functions, optionals, collections, and a y-axis labeled importance level hypothetical %, with integer values displayed on top of each bar. From the heights and labels, we can see the relative emphasis assigned to each concept. Functions are the highest at 30%, followed by variables at 25% and data types at 20%. Constants and collections are both at 15%, control flow is at 10%, and optionals are the lowest at 5%. The explicit data labels on each bar make it clear to compare categories. The largest gap is between functions 30% and optionals 5%, indicating functions are presented as a top priority in this view while optionals are given minimal weight. The order of bars reflects the categorical sequence rather than sorted importance, so the chart highlights both absolute importance and how these topics are grouped conceptually. A practical conclusion from this distribution is a suggested learning priority. Focus first on mastering functions and the handling of values, variables, and data types, then cover constants and collections, and finally ensure understanding of control flow and optionals, recognizing that despite a lower percentage here, optionals remain conceptually critical in Swift for handling absence of values. Now let's explore how to define and use optionals in Swift through an example. We start by declaring an optional variable named middlename, which can either hold a string value or be nil, indicating the absence of a value. This is fundamental as it allows us to express the possibility that a user may not have a middle name. Next, we implement optional binding to safely unwrap the optional value. We use the if-let syntax where we attempt to assign the value of middlename to a constant called name only if it is not nil. This technique ensures that we only proceed to use the value when we are certain it exists. If middlename contains a value, we print it, effectively informing users of the middle name they provided. Conversely, if it is nil, we handle this case gracefully by printing a message indicating that no middle name was provided. This approach exemplifies Swift's safety features by minimizing the risk of runtime errors caused by unwrapping nil values, making our code more robust and reliable in managing user data. Now let's see how we can implement optional chaining in Swift to work safely with optionals. Optional chaining is a powerful feature that allows us to attempt to access properties, methods, and subscripts on optionals without risking a runtime error if the optional is nil. In our example, we define a variable named length that utilizes optional chaining to obtain the character count of another optional variable, middlename. The expression middlename count means that if middlename contains a non-nil value, length will receive the count of characters in that string. However, if middlename is nil, length will also result in nil without throwing an error. This technique emphasizes Swift's approach to optionals, which encourages developers to be aware of potential nil values and handle them gracefully. By using optional chaining, you can write safer code that avoids crashes due to unwrapped nil references, thus promoting a more reliable and robust application development process. This ensures our applications are not only functional but also resilient to unexpected conditions. Now let's take a look at how we can manage collections in Swift using arrays, dictionaries, and sets. First, we declare an array called fruits, which is designed to hold strings. This array is initialized with 3 fruit names, apple, banana, and cherry. Arrays are index collections, allowing us to access their values by specifying their index. For instance, to access the first element, we use its index, which is 0. By doing this, we can print out the value of first fruit, which will display the first fruit as apple. Next, we move on to dictionaries, which are useful for storing key-value pairs. Here we create a dictionary named ages that maps names to their corresponding ages. In this example, we have Alice associated with the value 30 and Bob with 25. To retrieve a specific value from the dictionary, such as Alice's age, we reference her name as the key. By using an optional binding technique, we can safely handle cases where a key might not exist, printing a default value if necessary. Finally, we define a set named colors, which is a collection that only stores unique string values. Unlike arrays, sets do not maintain any particular order, making them ideal for scenarios where you want to avoid duplicate entries. Here we initialize the set with 3 colors, red, green, and blue. Sets facilitate quick membership checks, enhancing management efficiency. This completes our exploration of collections in Swift, illustrating how they can be effectively used to organize data. To summarize our exploration of Swift language basics, we kicked off by understanding variables and constants. We also covered different types of data, control flow with if statements and loops, function creation, and optionals, which help deal with the absence of values. Finally, we brushed up on collections including arrays, dictionaries, and sets. With these foundational concepts in hand, you're well on your way to mastering Swift for iOS development. So grab your coding gear and let's build some awesome applications. Developer Mode is a new feature introduced by Apple at the Worldwide Developers Conference in 2022. It is essential for developers looking to install, run, and debug their applications on devices operating with iOS 16 or later. This mode not only simplifies the app testing and development process, but also aligns with Apple's stringent security protocols, enhancing developers' control while ensuring user safety. So far, we have explored the fundamentals of Swift programming, digging into topics like variables, constants, and control flow mechanisms. We've learned about functions, handled optional values, and navigated through collections such as arrays, dictionaries, and sets. Equipped with this foundational knowledge, we're now ready to seamlessly transition into the world of app development and understand the critical role developer mode plays in this process. First off, why is developer mode necessary? When you're building an app, testing it on a real device is crucial to identify bugs and ensure a smooth user experience. Prior to the introduction of developer mode, developers had to rely on a limited set of tools and workarounds to test their apps on iOS devices. Apple's emphasis on security meant that many functionalities were restricted unless you were part of their developer program. Developer mode changes that by allowing developers to sideload applications more freely and debug them right from the device. To enable developer mode on your iOS device, you need to follow a straightforward series of steps. First, ensure that your iOS device is updated to at least iOS 16. Go to Settings and scroll down to find Privacy and Security. Tap on it and at the bottom you will see the developer mode option. You can toggle it on here. However, there's a catch. Once you enable developer mode, you will have to restart your device for the changes to take effect. A prompt will appear asking for confirmation to enable this mode. After restarting, you will see a notification asking you to confirm your choice to enable developer mode. It's a simple yet essential step to ensure that your device is prepared to run your development applications properly. The bar chart titled Key Concepts in Developer Mode for iOS Development presents 4 concepts along the x-axis: app testing, debugging, security, and performance, with their corresponding importance levels on a 0-100 scale. The numeric values displayed above each bar are app testing 60, debugging 85, security 50, and performance 70. Visually, the tallest bar is debugging 85 blue, indicating it is considered the most critical aspect by a substantial margin. Performance 70 red is the next most important, followed by app testing 60 green. Security 50 orange appears lowest in perceived importance relative to the others. The y-axis gridlines and labels emphasize these differences in magnitude, making the gaps between debugging and the other categories evident. From this distribution, we can conclude that developers place primary emphasis on robust debugging capabilities when using developer mode, with performance tuning also a major concern. App testing holds moderate priority and security, while still significant, registers lower on this particular importance scale. This suggests that developer mode implementations and workflows should prioritize powerful debugging and performance profiling tools, while ensuring security measures are maintained and not deprioritized in practice. Now let's take a look at how to implement a simple Hello World application in Kotlin for Android. First, we define our package name at the top, which serves as a unique identifier for our application. We then import necessary libraries, enabling us to use key Android components such as bundle, app-compat activity, and TextView. The main activity class extends app-compat activity, which provides the basic functionality for an Android activity, allowing us to manage the user interface. Within the onCreate method, which is triggered when the activity starts, we call super onCreate saved instance state to execute the default behavior for an activity. This is followed by setting the content view to our defined layout with set content view r layout, activity main, linking our XML layout to the activity. Next, we find the TextView component in our layout using its ID TextView. This allows us to manipulate its properties programmatically. Finally, we update the TextView to display Hello World on the screen. This foundational step introduces students to the structure and workflow of a basic Android application, paving the way for more complex functionalities in future lessons. Now, running this app on your iOS device is where developer mode comes into play. With developer mode enabled, you can connect your device to your development machine and run the app directly. This feature allows you to test the app on actual hardware, which provides invaluable insights into the app's performance and usability. After writing and saving the code, you simply need to click Run in Android Studio. If your device is connected and recognized, the app will compile and install it on your device. Assuming you have set everything up correctly, the app will appear on your home screen, and you can open it to see Hello World displayed. Now let's take a look at how we can implement the foundational elements of our Android application in Kotlin. First, we define our activity class, mainActivity, which extends app-compat activity, allowing us to leverage essential features for managing user interface elements and managing interactions. Inside the onCreate method, we call super onCreate saved instance state to retain the properties and states of our activity. This method also sets the user interface layout with set content view r layout, activity main, linking our Kotlin code to the XML layout file where we will design the interface. Next, we initiate a TextView component by referencing its ID from the layout file using findView by ID R-ID TextView. This gives us a handle to manipulate the text view on the screen. The pivotal moment comes when we set the text property of our text view to Hello World. This line not only adds content to our screen, but also provides a clear indication that our app is functioning correctly. Thus, with this code, we've established a simple structure for our application, paving the way for more complex functionalities as we advance in our learning journey. So far, we've covered how to enable developer mode on an iOS device, how to write a simple Kotlin program, and how to debug that program effectively. We've also seen how debugging can illuminate the inner workings of your application, making it easier to identify potential issues. Now let's shift gears and discuss the importance of security in developer mode. The primary concern with developer mode is the exposure it brings to the user's device. While it allows developers to test their applications without restrictions, it also increases the risk posed by malicious software. Any app run in developer mode bypasses the standard security restrictions of iOS, which can lead to potential exploitation. Now let's see how we can update our development environment by using the SDK Manager. Keeping your development tools and SDKs up to date is crucial for accessing the latest features and security improvements that help streamline your app development process. To do this, we will utilize the command line interface and run a simple command, SDK Manager Update. This command communicates with the Android SDK Manager to check for any updates available for both the SDK tools and associated components. By executing this command, you ensure that your development environment remains optimal, allowing you to leverage enhancements and bug fixes provided by newer versions. Regularly updating these tools not only enhances performance, but also reinforces the security framework needed when working in developer mode. It's essential to incorporate this practice into your routine, as a well-maintained development environment reduces potential issues, saving you time and effort in the long run. So make a habit of running this command to keep your SDKs current and to enjoy a smoother coding experience. As we come to the end of this lesson, let's summarize what we've discussed today. We've learned about developer mode, its necessity for app development on iOS, and how to set it up on your device. We delved into a basic Kotlin application showcasing how to run and debug it effectively, and we discussed the importance of security when using developer mode. In essence, developer mode is a powerful tool that opens up possibilities for app developers, but must be used responsibly. By understanding its capabilities and the associated risks, you can create amazing applications while keeping security at the forefront of your development process. Now you're equipped and excited to further explore app development, armed with the knowledge of how to utilize developer mode effectively. In our next lesson, we'll continue to build on these advanced concepts, diving deeper into building complex applications and utilizing more robust development tools. Happy coding! Developer mode is a vital feature for app developers working with Apple's latest iOS devices. Introduced at WWDC 2022, it allows developers to install, run, and debug apps on devices that operate on iOS 16 or later versions. This functionality has transformed how developers interact with their applications directly on their devices, making the development process smoother and more efficient. So far, we learned about developer mode, a key feature for app developers on iOS that facilitates the installation, running, and debugging of applications. We've covered how to enable this mode and its implications for testing applications securely. Additionally, we delved into writing a simple Kotlin application and the importance of utilizing debugging tools effectively. Lastly, we addressed the security risks associated with developer mode and emphasized the importance of following best practices while developing applications. Now, we will cover the intricacies of developer mode, including its functionalities and how to leverage it effectively in your development process. When you first enable developer mode on your iOS device, you might notice some changes in the settings and features available to you. It's essential to understand these changes to utilize the mode fully. Developer mode grants access to a whole set of tools designed to enhance the debugging process and provide deeper insights into how your application behaves during runtime. These tools are tailored to help you monitor and optimize your applications while providing a more interactive development experience. The most significant updates come in the form of simplified installation processes for apps. In a regular mode, developers often needed to deal with provisioning profiles, signing certificates, and other bureaucratic hurdles. However, enabling developer mode streamlines these processes, allowing you to install your app directly onto your device with fewer steps. The figure displays a horizontal bar chart titled Key Features of Developer Mode for iOS Development, where each bar corresponds to a feature and is annotated with its importance score on a 0-100 scale. From top to bottom, the features and their exact scores are Simplified Installation 90, Enhanced Debugging 85, Access to Logs 80, Device Capabilities 75, Resource Management 70, Security Practices 65, and Community Support 60. The pattern shows a clear descending order of perceived importance with consistent 5-point differences between adjacent features, indicating a graduated prioritization rather than a single dominant outlier. Simplified Installation leads the ranking, closely followed by Enhanced Debugging and Access to Logs, which together form the primary trio developers prioritize when using developer mode. Device Capabilities and Resource Management sit in the mid-range, signaling significant but secondary importance for runtime testing and performance tuning. Security Practices and Community Support occupy the lower end of the scale. While still relevant, they are shown as lower immediate priorities compared to direct tooling and installation conveniences. The x-axis is labeled Importance Score %, with grid lines in a 0-100 range, and each bar has its numeric score displayed to the right, making the relative differences and absolute values easy to read and directly comparable. Consider the following scenario. You have created a simple Kotlin application and you want to test it directly on your device. With developer mode enabled, you are free to run your app smoothly without the cumbersome task of signing and provisioning. Here's how you can set it up. Fun main. Println hello developer mode. This basic application will display a friendly greeting when you run it. With developer mode, you can simply compile it and transfer the app directly onto your device to see how it operates in a real-world environment. Moreover, debugging your app has never been easier thanks to the enhanced tools provided in developer mode. The integration between your IDE and Xcode allows you to track down issues more effectively. For example, if you encounter an exception, instead of merely crashing, you can leverage the built-in breakpoints. By placing a breakpoint in your code, you can pause execution and examine the current state of the application, scrutinizing variables and program flow. Here's a practical example of implementing a breakpoint in Kotlin. Fun divide numbers num1 int num2 int. Return num1/num2. Fun main. Val result equals divide numbers 10, 0, setting breakpoint here for debugging. Println result. Attempting to divide by 0 will generate an exception. By running the application with a breakpoint, you can check the values of num1 and num2 before the execution jumps to the division operation. This insight helps you spot potential bugs before they make it to a live environment, saving you valuable time. One significant advantage of developer mode is the ability to access logs directly from your device. Monitoring logs is crucial in your debugging process, as they provide insights into the internal workings of your app. By using Xcode, you can view system logs, identifying what happens behind the scenes when errors occur. You can filter logs to find specifics related to your app, which speeds up diagnosing issues and improving performance. For example, to get logs while your app is running, you can incorporate logging within your code. Import Android util log. Fun perform division num1 int num2 int. If num2 equals 0, log e division error cannot divide by 0. Else, val result equals num1/num2. Log I division result. The above implementation uses Android's log class to log messages at different severity levels. With developer mode enabled, you can track these logs effortlessly, ensuring you are informed of both warnings and errors as you develop. Next, we have device capabilities and configuration settings that you can explore within developer mode. iOS devices come equipped with settings that help control how your app behaves and reacts to the device's hardware features. You'll typically want to test your app under different scenarios to ensure it responds appropriately. For instance, you can simulate various network conditions. If your app relies heavily on data retrieval, you may want to see how it performs when the network is slow or unstable. The Network Link Conditioner tool can help you simulate these scenarios efficiently. To enable this, navigate to your device's settings and enable the Network Link Conditioner. You can then select profiles that replicate slow network speeds, packet loss, or even a completely offline scenario. Testing your app under these conditions ensures your error handling mechanisms work effectively and that the end-user experience remains robust. Another fantastic feature you can utilize in developer mode is the ability to manage your app's usage of system resources, particularly CPU and memory. Monitoring these metrics allows you to identify performance bottlenecks and optimize your app for better efficiency. Tools like instruments in Xcode can provide vital stats, showing you where your app may be consuming excessive resources or causing slowdowns. You can initiate instruments by selecting your app, and it will provide you with options like CPU profiling, memory usage tracking, and diagnostics related to disk I/O, for instance. If you notice high memory usage, you might want to investigate how objects are being managed in your app or check for potential memory leaks. To visualize retaining objects and their references, you can run memory allocation checks in your Kotlin application like this. Class example: var name string equals null. Vun create complex object. Val complex object, some complex object equals some complex object. Reference retained. By profiling the above code, you can see if complex object might be holding onto more memory than necessary, leading to performance degradation. The critical aspect of development mode lies in the security implications it has on your application's data management and operations. With great power comes great responsibility. When enabling developer mode, it's crucial to prioritize security practices, ensuring that you don't unintentionally expose sensitive information or exploit user data. Always remember to toggle off developer mode when you're done testing. Running apps in developer mode can lead to unintended data exposure or app store rejection if not properly handled. Properly securing API keys, using encrypted communication protocols, and regularly auditing your access permissions should always remain at the forefront of your development practices. For instance, securely handling API keys might look like this. Object API constants. Const val API key equals YOUR secure API key. Here, avoid hard-coding sensitive data directly into your application. Instead, explore leveraging secure storage solutions or environment variables to keep sensitive information safe while in development. As we continue to explore Xcode's developer mode functionalities, we should highlight the community aspect and the support available. Apple provides ample resources, from documentation to developer forums, keeping developers informed about best practices and emerging issues. Engaging in these platforms gives you insights into common challenges faced by developers around the globe and strategies they employ to overcome such hurdles. Participating in developer communities can introduce you to new concepts, frameworks, and even collaborations that can elevate your projects. Remember, a well-connected developer benefits tremendously from sharing knowledge and leveraging the experience of others. In conclusion, embracing developer mode on your iOS devices is a game-changer for app developers, allowing you to install, run, and debug apps like never before. Understanding its functionalities and implications ensures that you make the most of the developer tools available while adhering to best practices for security and efficiency. So far, we covered the importance of developer mode and its functionalities in simplifying the testing and debugging processes for your applications. We explored how to leverage logging and monitoring tools, the significance of network management, and the importance of adhering to security best practices. As you move forward in your development journey, take full advantage of these features within developer mode, ensuring that your applications run smoothly in a real-world environment. We hope you find these insights valuable as you continue crafting exceptional user experiences with your Kotlin applications. Developer mode is an essential feature introduced by Apple during WWDC 2022, specifically designed for developers working on iOS applications that run on devices with iOS 16 or later. This mode is crucial for simplifying processes related to installing, running, and debugging your apps on actual devices, rather than just using a simulator. So far, we learned about the significance of developer mode for app developers on iOS, emphasizing its role in simplifying installation, running, and debugging processes. We discussed the enhanced tools for effective debugging, including logging access and network management features. Additionally, we highlighted the importance of adhering to security best practices while utilizing developer mode functionalities. As we progress, we'll continue to explore more features and insights related to optimizing your development experience. Let's dive deeper into what developer mode entails and how to navigate its functionalities effectively. When you enable developer mode on your iOS device, you gain access to a variety of tools that facilitate app development. One of the primary functions of developer mode is the ability to sideload apps, that is, installing apps directly from your development environment instead of through the App Store. This allows for rapid iterations and immediate testing of your latest features. You might find yourself rapidly debugging an application, tweaking a line of code, and almost instantly seeing the changes reflect in your app, a game changer for any developer. The displayed horizontal bar chart, titled Key Features of Developer Mode and Their Importance, lists 5 features on the vertical axis: sideloading apps, enhanced debugging, network management, testing on devices, and security best practices, with corresponding importance scores on the horizontal axis percentage scale. The numeric values shown are security best practices at 95%, sideloading apps at 90%, enhanced debugging at 85%, network management at 80%, and testing on devices at 75%. Key patterns visible are that security is rated highest, 95%, creating a clear priority over other features, while testing on devices is rated lowest, 75%, producing a 20-point spread between the top and bottom items. Sideloading and debugging cluster closely 90% and 85%, indicating they are both critical for rapid iteration and issue resolution, whereas network management sits midway 80%, reflecting strong but slightly lesser emphasis. From these values, one can conclude that practitioners should prioritize secure practices first, then invest heavily in mechanisms that enable sideloading and enhanced debugging workflows, while maintaining robust network inspection capabilities and ensuring adequate device testing to catch hardware or environment-specific issues. Enabling developer mode requires a few simple steps. First, connect your iOS device to your Mac using a USB cable. Then open Xcode, Apple's integrated development environment. Click on Window from the menu bar followed by Devices and Simulators. Find your connected device in the list and you'll see an option to enable developer mode. Once you toggle that on, you may need to restart your device. After the reboot, you'll notice that your device acknowledges it is now in developer mode, allowing you access to various advanced features. Don't rush through this part. Precision is key here, especially as these settings can greatly affect how your application interacts with the iOS ecosystem. A misconfiguration can lead to perplexing errors later in development, wasting precious time. Now let's see how we can implement logging in our application using the Timber library, which provides a robust way to handle log messages. First, we need to set up Timber in our application class. By overriding the onCreate method we call TimberPlant with Timber debug tree. This sets up a logging tree that outputs logs specifically intended for development, allowing us to easily differentiate between various log levels and contexts. Next, we'll move on to how we can use Timber in our activities or fragments. We can define a function named logMessage that takes a string message as a parameter. Inside this function, we will utilize TimberD to log a debug message, prepending debug message to our input message. This allows us to trace specific debugging information while we iterate on our development. Additionally, we can set up an logError function to capture and log errors. Here, we pass a throwable object to TimberD, providing a meaningful message to indicate that an error occurred. This structured logging not only helps in debugging but also assists in understanding application behavior during development and testing, contributing to a more informative debugging experience. Next, let's focus on network management features in developer mode. When you're developing applications that require internet functionality, platform features are vital for efficiently debugging network requests. One such feature is the ability to intercept and inspect HTTP requests sent from your application to the server, which can be done using tools like Charles Proxy or HTTP Toolkit. Setting up Charles Proxy is straightforward. After installing the application, you need to configure your device to route its HTTP traffic through your Mac running the proxy. This can often involve adjusting proxy settings in the Wi-Fi settings of your iOS device. Once everything is set up, you can monitor all outgoing and incoming HTTP requests. This is particularly useful when you want to dynamically change the response you are testing against without having to modify server-side code. Together with logging, monitoring network calls can provide invaluable insights into how your application interacts with back-end services. A good practice while developing is routinely checking the API responses for unexpected data, which can lead to crashes or unusual behavior of your application. Now let's see how we can implement camera permission requests in our application. This is essential, as appropriate permission handling ensures that users can utilize functionality like the camera without interruption. In the code, we begin by defining a function called requestCameraPermission. The first step inside this function checks whether the application already has camera permission using context_compat check_self-permission. If permission has not yet been granted, we proceed to request it by calling activity_compat request_permissions. This method takes three parameters: the current context, an array of permissions we are requesting, in this case the camera permission, and a request code labeled cameraQuestCode. This code allows us to identify the permission request when the user's response is returned. It's also important to note that if permission has already been granted, the function acknowledges this situation by including a comment indicating the user has already provided camera access. By handling permission requests in this way, we ensure a smooth user experience, especially since testing on real devices reveals the variability in how different devices manage permissions. Consequently, understanding and implementing this aspect is crucial in delivering functionalities that are both efficient and user-friendly. Now let's see how we can implement secure storage for sensitive user data using the Android key store. In this code snippet, we define a function called SaveToKeychain, which takes a key and a value as parameters. The first step in this function is to initialize the Android key store, which provides a secure container to store cryptographic keys. Using the key store ensures that the keys are not directly exposed, helping to protect sensitive information. Next, the code loads the key store instance, creating a secure environment for our key operations. The function retrieves a secret key associated with a specified alias, which is critical because this key will be used to encrypt our sensitive data. While the actual logic for saving the value using the secret key is not shown here, it's important to ensure that any data saved is properly encrypted, safeguarding it against unauthorized access. By employing secure storage practices, you mitigate risks associated with sensitive data breaches, aligning with best security practices while utilizing developer mode in iOS development. Always remember the importance of securely managing user information in your applications. As we wrap up our extensive discussion about developer mode, it's essential to emphasize that enabling developer mode significantly alters how you can develop and test your applications. With access to advanced debugging tools, logging features, network management, and enhanced testing capabilities on physical devices, you're now equipped to improve your workflow and create high-quality applications. In the next segment, we'll delve into more advanced features using developer mode, exploring how to optimize performance and address issues in real time as you develop. Keeping efficient practices in mind will not only streamline your process, but also help you achieve smoother user experiences. Remember, developer mode is not just about having tools at your disposal. It's about how effectively you can leverage those tools for a seamless development experience. Continue to explore and practice, and watch how these techniques transform your approach towards iOS app development. Let's dive into the exciting world of building and running iOS apps on actual devices. While the simulator offers a convenient way to test your applications, using a real device is crucial for a number of reasons we'll explore today. So far, we learned about the key functionalities and benefits of developer mode for iOS app development, including sideloading apps, enhanced debugging, and efficient network management. We highlighted the importance of testing on real devices and adhering to security best practices to protect sensitive user data. Additionally, we discussed practical implementations, such as logging techniques and permission handling in Kotlin. Moving forward, we will explore more advanced features and strategies to optimize the development process. Now, we will cover how to build and run your iOS apps on an actual device to ensure that you can test all the features, especially those that rely on specific hardware components. The displayed bar chart titled Key Concepts in iOS App Development presents 5 labeled bars on the x-axis with a y-axis measuring importance %. The exact values shown are developer mode at 30%, enhanced debugging at 25%, sideloading apps at 20%, real device testing at 15%, and user permissions at 10%. From these values, we can observe a clear ranking. Developer mode is given the highest importance, followed closely by enhanced debugging. Sideloading apps occupies a mid-level position. Real device testing is lower relative to the others but still present. User permissions has the smallest share. A key pattern is that developer mode and enhanced debugging together account for more than half of the total importance, 55%, indicating a combined emphasis on developer tooling and debugging capabilities. The distribution also shows a steady decline in assigned importance from the top 2 down to user permissions. which suggests the represented priorities concentrate more on development and diagnostic features than on permission handling or device testing in this specific breakdown. First off, let's talk about the importance of testing on an actual device. When you develop applications, there are numerous hardware features like GPS, accelerometers, camera, and touch interface that the simulator cannot provide. Imagine you're building the next exciting fitness application that tracks user activity and utilizes GPS to log workouts. Practically, the simulator may run your app flawlessly, but it will never be able to simulate the real-world GPS signals, which are pivotal for tracking location data accurately. This is where actual device testing shines. Getting started with running apps on a real device involves a few steps that you must follow carefully. First, make sure that you have an Apple developer account. This account is crucial as it allows you to access tools, resources, and most importantly, allows you to test your apps on actual devices. Once you've set up your account, connect your iOS device to your Mac using a Lightning cable. Next up, open Xcode on your Mac and select your project. You'll need to make some configuration adjustments in order for your device to be recognized by Xcode. Under the project settings, navigate to the Signing and Capabilities tab. Here you'll want to ensure that your team is set to the Apple developer account you are using. If you are new to iOS app development, don't hesitate to set the bundle identifier. It's usually in the format your name, Europe name. Now let's take a look at how we can implement a simple counter app using Kotlin in an Android environment. The main activity class extends app-compat activity, which is a crucial step in building any Android application as it provides access to the app's activity lifecycle. Inside the class, we declare a private variable count initialized to 0, which will keep track of the number of times a button is clicked. We also have a latinate variable count text view, which will be linked to a text view in our layout. This is where we will display the current count to the user. In the onCreate method, which is called when the activity starts, we set the content view to the layout defined in activity main. This is where our user interface elements are found. We then initialize count text view by finding the respective text view by its ID. Next, we set up an on-click listener on the button identified by increment button. With each press, the count variable is incremented and the updated value is displayed in the text view. This setup creates an interactive experience for the user, showing how even simple code can implement engaging features in an app. Once you've set up everything and have your device selected, hit that Run button. Xcode will compile the project and deploy the application to your iOS device. If you see a prompt asking you to trust the developer, follow the on-screen instructions to trust your Mac on the device. This is an important security measure that Apple incorporates to ensure applications come from a trusted source. After launching the app on your device, you should see the user interface as expected. Play around with the functionality you've built. Observe how the app runs under real conditions. This hands-on experience will expose you to nuances that simply cannot be replicated in a simulator, such as user interaction responsiveness, battery usage, and overall performance. Now let's see how we can implement error handling for accessing the device camera in our application. The Open Camera function begins by checking if the device has a camera feature. This is accomplished through the Package Manager has System Feature method, which verifies the presence of the camera hardware. If the device meets the requirement, we can proceed to open the camera for use in our app. However, if the camera is unavailable, the app will not crash. Instead, we provide a user-friendly alert via toast message indicating that the camera is not accessible. This approach ensures that the app maintains a smooth user experience, offering clear feedback rather than unexpected failures. Proper error handling like this is crucial, especially when dealing with hardware features, as it allows the app to respond gracefully in various situations. By implementing such checks, you enhance your app's robustness, ensuring users are always informed about the status of critical functionalities like the camera. Now let's see how we can implement permission handling in our app. The first thing our code does is check if the required permission to access the camera has been granted using the context compat check self-permission method. By passing in the context and the specific permission we're interested in this case, the camera permission, we can determine if our app has the necessary access. If the permission has not been granted, the code then makes a request for it using activity compat request permissions. This method is crucial as it prompts the user to allow your app to access the camera, presenting a user-friendly dialog. It's important to note the callback mechanism in Android that listens for the user's response. This means that after making the request, you should be prepared to handle either granting or denying the permission, enhancing the overall user experience. On the other hand, if the permission has already been granted, the app proceeds to open the camera, which allows users to engage with the camera functionality seamlessly. This flow ensures that the app operates smoothly without crashing due to lack of permissions, thereby maintaining a secure and user-friendly experience. Now let's see how we can implement a feature that ensures our app handles network connectivity gracefully. The first function, fetch data, checks whether the network is available by calling another function, is network available. If the network is indeed available, it proceeds to perform the necessary API call to fetch data from the server. However, if the device is not connected to the internet, it triggers a show retry dialog. This dialog serves as feedback for the user, prompting them to check their connection and try again later, which reinforces a smooth user experience even in unstable conditions. The isNetworkAvailable function is crucial as it determines the current state of the network connection. It utilizes the Connectivity Manager to check if there is an active network connection. The function returns a Boolean value, indicating whether the device is connected to the internet or not. By integrating these two functions, your app can effectively handle situations of intermittent connectivity, ensuring users are kept informed and engaged, which is particularly important when fetching data from the web. This proactive handling of network conditions is vital for maintaining a robust user experience. Finally, let's reflect on how building and running your iOS applications on actual devices can transform your development process. While the simulator will provide you with useful guidelines, it will never fully replace the rich insights that real-world device testing offers. You'll encounter unique behaviors, performance issues, and features you might not have envisioned, like varying screen sizes and different device capabilities. Moreover, user feedback is invaluable. Testing on actual devices allows you to observe how real users interact with your applications. Collect insights about usability, performance, and feature preferences directly from your audience. Engage with beta testers over test flight to get meaningful feedback before deploying your finished app. In conclusion, deploying your application on an actual device not only enhances your development workflow, but also leads to creating robust, polished apps ready to tackle the real world. As you continue your journey in iOS development, remember to leverage the experience that comes from using physical devices. Each session with users will make you a better developer and lead to even more exciting advances in your app building endeavors. Enabling developer mode on your iOS device is a crucial step for anyone looking to dive into iOS app development. It allows you to test your applications directly on your device and ensures that you can debug and utilize all the necessary features. Today, we'll walk through how to enable developer mode and discuss its significance in the app development lifecycle. So far, we learned about the significance of building and running iOS applications on actual devices for thoroughly testing features that depend on hardware components. We discussed the importance of developer mode, proper permission handling, and debugging techniques, all of which contribute to enhancing user experience and security. The practical steps to configure and run apps on real devices were outlined, emphasizing how real-world testing can unveil unique behaviors and performance issues that simulators cannot replicate. Moving forward, we'll explore further strategies to optimize app development and testing. To start, let's delve into why developer mode is essential. Enabling this mode gives you access to additional features in Xcode that would not normally be available for regular users. It helps streamline the development process, provides access to logging and debugging tools, and allows for testing features that rely on real hardware interfaces like the camera, sensors, and GPS. To enable developer mode on your iOS device, go to Settings, then navigate to Privacy and Security. You will scroll down to find the developer mode item and tap on it. However, let's make this even more accessible. Here's a breakdown of the steps you need to perform. 1. Unlock your iOS device and open the Settings app. 2. Scroll down and tap on Privacy and Security. 3. Locate developer mode within the list of options. This may take some scrolling, but keep an eye out. 4. Once you find it, tap on developer mode and toggle it to the on position. 5. A prompt will appear asking for confirmation to enable developer mode. Confirm your choice. By enabling developer mode, your device can now communicate more effectively with Xcode. After confirming, you might need to restart your device for the changes to take effect. Not only does this grant you the freedom to test your apps without the limitations of standard usage, but it also opens the door to real-time debugging. Next, we will write a simple login function that ensures users cannot proceed without providing valid credentials. In this function, we check if either the username or password input fields are empty. If either of these fields is empty, a log entry is recorded to indicate that a login attempt was made without complete information. This debugging step helps us trace issues related to user input effectively. When executing the function, if the validation fails, we use the loggy method to notify that there's a problem, and the function terminates early using the return statement. This prevents any further login logic from being executed if the input is invalid, ensuring a cleaner flow in our application. By implementing this early exit strategy, we can safeguard our application against attempts to log in with insufficient data. This approach not only enhances the user experience by prompting them for the necessary information, but also simplifies our debugging process, as we can set breakpoints here to inspect the values of username and password during testing. Overall, this method provides a structured way to manage user authentication and maintain the integrity of our application's functionality. The displayed donut chart titled Importance of Different Aspects in iOS App Development shows 4 labeled slices with their respective percentages. Testing on device, 35%, debugging tools, 30%, permission handling, 25%, and updates process, 10%. Visually, the largest slice is testing on device at 35%, closely followed by debugging tools at 30%, indicating that together these two categories account for 65% of the emphasis represented. Permission handling at 25% is a substantial portion as well, signaling its significant role in ensuring app functionality and user trust. Updates process appears as the smallest slice at 10%, showing that in this representation it is given less priority relative to the other aspects. From these proportions, we can conclude that runtime validation on real devices and robust debugging are presented as the primary focus areas, while permission management remains a critical but secondary concern, and update deployment is shown as a lower-weighted consideration in the development priorities illustrated by the chart. Now let's take a look at how we can implement permission checks for accessing the camera in our application. The code begins with a function called checkPermissions. Within this function, we first verify if the camera permission is granted by using context compat check self permission. This method checks the current permission status for the camera, ensuring that we act based on the user's consent. If the permission is not granted, the function utilizes activity compat request permissions to request the necessary camera permission from the user. This step is crucial because it prompts the user to allow access to their camera, and without this explicit permission, our app would not be able to utilize camera features. We provide a request code, camera request code, to identify this specific permission request when handling the user's response. Finally, if the permission is already granted, we can confidently proceed to access the camera features without any further checks. This pattern of checking permissions first is essential for maintaining a smooth user experience and ensuring compliance with the app's permission requirements. By correctly managing permissions, we build trust with users and enhance the overall functionality of our application. As we enable developer mode and set up our app to interact seamlessly with the device's features, understanding how to push updates for continuous testing is crucial. When developing, you'll make several iterations, often needing to test each change immediately. Xcode provides tools that allow you to seamlessly build and run your application on your device. When you're ready to test your changes, simply connect your iOS device to your Mac, select it from the list in Xcode, and hit the Run button. This builds the app and pushes the update directly to your device. You'll see your latest changes immediately reflected, which is extremely helpful for rapid development. Consider this incremental integration approach as akin to building a bridge one plank at a time, constantly checking each step for stability before adding more planks. By continuously deploying updates to your device, you can swiftly catch issues that might not arise in a simulator or with older code that you have modified. As we wrap up our discussion on enabling developer mode, remember that this setup not only facilitates debugging and permission handling, but also prepares you for forthcoming updates and better performance assessment. You've now learned how to toggle developer mode, manage permissions, and leverage real-time testing on actual devices. Next, our focus shifts to further optimizations in your development workflow, from understanding various testing techniques to ensuring your app runs efficiently regardless of the hardware capabilities. We'll be diving into how to implement comprehensive testing strategies that ensure your app remains robust and responsive even as you make significant changes. In conclusion, enabling developer mode is a pivotal step in your iOS app development journey. It empowers you to test effectively, debug efficiently, and optimize user experience, 3 pillars that are essential for delivering a successful app. So gear up for your next big coding session and never forget the impact of hands-on testing. Happy coding. Let's dive into a topic that is crucial yet often overlooked in iOS app development: trusting developer certificates for your iOS applications. In this lesson, we'll explore what exactly a developer app certificate is, its role in the app installation process, and why it's vital for ensuring your applications run smoothly and securely on iOS devices. So far, we covered the importance of enabling developer mode on iOS devices, which is fundamental for effective app development, testing, and debugging. We've discussed various practices such as permission handling and real-time debugging techniques to enhance user experience and app stability. The previous steps highlighted the practical methods for enabling developer mode, giving developers access to the essential features in Xcode. Now we will talk about developer certificates, their significance, and how to properly handle them to ensure your apps are trusted by iOS devices. Let's start from the ground up. What is a developer certificate? In simple terms, a developer certificate is a digital document issued by Apple that authenticates the identity of the developer and ensures that the application being installed comes from a trusted source. Each certificate is unique and contains a public and private key pair. The public key is shared, while the private key must be kept secure and secret. Together, they facilitate secure communication and establish trust between the application and the device. When you create an app and attempt to install it on an iOS device, the operating system utilizes this certificate to determine whether the application is safe and has not been altered maliciously. If you're developing an app without a valid certificate, iOS will throw up security flags, preventing your app from being installed or executed, keeping users safe from potentially harmful software. Next, we will write the code to generate a certificate signing request, CSR, using the Keychain Access application on macOS. This process is crucial as it begins the journey of creating a developer certificate, which is necessary for signing your iOS apps. The code comments guide us through the steps of navigating the Keychain Access app. We will start by opening Keychain Access and then look for the menu bar at the top of the screen. Here, the specified steps direct us to select Certificate Assistant and then choose Request a Certificate from a certificate authority. This action prompts the Keychain Access app to assist us in creating a CSR, ensuring our key pair is generated securely. The CSR will include your email address and name, which helps verify your identity as the developer. After completing these steps and saving your CSR, you can upload it back to the Apple Developer Portal, where your developer certificate will be generated. This foundational code snippet not only shows how we initiate this process, but also highlights the secure and professional way developers begin working with certificates for app development. The displayed figure is a donut chart titled Key Concepts of Trusting Developer Certificates in iOS Apps that breaks down 5 distinct concerns and their relative emphasis. Trustworthy sources 30%, secure communication 25%, user safety 20%, expiry management 15%, and app signing process 10%. From this visualization, we can draw several conclusions relevant to our workflow. The largest slice, trustworthy sources at 30%, indicates that provenance, ensuring apps originate from verified, reputable developers or distribution channels, is the most prominent concern in maintaining trust. Secure communication at 25% follows closely, highlighting the importance of protecting data in transit and ensuring certificate-based channels, TLS code signing verification, are robust. User safety at 20% underscores that protecting end-user data and preventing tampering are primary outcomes of correct certificate use. The smaller but still meaningful slices for expiry management 15% and app signing process 10% suggest these are essential maintenance and operational tasks that support the top priorities. Certificates must be actively renewed and revocations handled, and the technical mechanics of signing must be correctly executed. Taken together, the chart shows that while signing and lifecycle management are vital, the emphasis in practice should be on verifying sources, securing communications, and preserving user safety, guiding where to allocate attention and resources during certificate setup and ongoing management. Now let's see how we can implement a conceptual representation of signing an app using a developer certificate. In this code, we define a simple application class instance called MyApp. This instance represents our application that will be used in our signing process. Next, we introduce a function named signapp, which takes an application object as a parameter. Inside this function, we have a print statement that simulates the signing process by outputting a message indicating that the app is being signed with the developer certificate. It's important to note that this representation is conceptual. The actual signing procedure is handled behind the scenes by Xcode during the build process. By calling the signapp function and passing in MyApp, we demonstrate how the signing process is initiated in a programmatic context. This helps clarify the process to students, reinforcing that while our code illustrates the concept, the real signing mechanics are automatically managed by Xcode when the app is built. Understanding this allows developers to focus on the essential parts of app development while Xcode takes care of signing details. Now, let's take a look at how we can implement the trusting of a developer certificate in Kotlin. This code snippet defines a class called Device Management, which encapsulates the functionality needed to trust a developer certificate for an installed application. Inside this class, there is a method named TrustDeveloperCertificate, which when called simulates the action of trusting the developer certificate. It accomplishes this by printing a message to the console indicating that the certificate for the installed app is being trusted. This is a simplified representation of the actual process users go through on their iOS devices when they navigate through the Settings app to trust the developer. By instantiating the device management class and invoking the TrustDeveloperCertificate method, we mimic the necessary action that users must perform on their devices to allow applications installed from non-App Store sources to run without issue. This illustration serves as a lightweight way to convey the importance of handling the developer certificate trust process correctly for successful app installation and execution. So why is trusting the developer certificate so essential? Trusting the certificate ensures that users can confidently download and use apps without fearing that they are at risk from malicious attacks or unauthorized modifications. In a world where personal data security is paramount, this trust mechanism plays a pivotal role in maintaining the integrity of the iOS ecosystem. As a developer, you're responsible for understanding the implications of app signing and the security protocols that come with it. It's not just about getting the app onto the device, it's also about assuring users that their data is safe. Now let's take a look at a simple implementation for managing developer certificates. In this example, we have a class called Certificate Manager, which encapsulates the functionality for certificate management, specifically focusing on revoking old certificates that are no longer needed. The revoke old certificate function takes a certificated as a parameter and prints a message indicating that it is revoking the specified certificate. This is an essential step in maintaining security, as it is crucial to ensure that unused or outdated certificates are properly handled to prevent any potential security risks. Next, we'll instantiate the Certificate Manager class and call the revoke old certificate method with a placeholder ID for an old certificate. This process effectively reinforces the importance of proactive certificate management, as it demonstrates how easy it is to maintain security in our development environment. By adopting such practices, you significantly reduce vulnerabilities in your application, illustrating that security is an ongoing effort rather than a one-time setup. Next, we will write the following function to assist in debugging issues related to developer certificates. The function debugCertificateIssues takes a string parameter called issue, which represents the specific problem encountered. When called, it prints a message to the console indicating that a certificate issue is being debugged, along with the description of the issue. This functionality is crucial for developers as it allows them to log problematic situations that arise during the app installation or execution phases. For instance, if a developer faces an invalid certificate signature error, they can invoke this function providing the relevant issue as an argument. This can greatly aid in tracing back the root cause of the problem, as it neatly formats and displays the debugging information in the console. Using this method effectively simplifies the troubleshooting process, making it easier to identify and rectify certificate-related failures. By systematically logging and addressing these issues, developers can ensure their apps can be installed and run smoothly, providing a better experience for end users while reinforcing the application's security. To wrap it up, developer certificates are an essential component of the iOS app development process as they ensure that apps are trusted and secure. Understanding how to generate, trust, manage, and debug developer certificates will significantly enhance your app development workflow and the overall security of your applications. By grasping the critical role of these certificates, you'll be better equipped to develop robust iOS applications that conform to Apple's security standards while maintaining a high level of trust with your users. So, as you continue your journey in mobile app development, remember that it is not only about writing code, but also about creating secure, trustworthy ecosystems that protect users' data and privacy. Keep practicing, keep questioning, and most importantly, keep building those amazing applications. Running your app on actual devices is one of the most critical steps in the app development process. While simulators are fantastic for initial testing, they often fall short in simulating the real-world environment your app will operate in. Today, we're diving into the importance of testing your application on actual iOS devices and how this can elevate your app development experience and ensure your app performs optimally in the hands of real users. So far, we covered the essentials of developer certificates in iOS app development, which are crucial for ensuring that applications can be trusted and secure. We discussed how to manage these certificates in Xcode and the importance of validating app authenticity. Now we will cover how to set up your environment for testing on actual devices and the steps you should follow to ensure that everything works seamlessly. When it comes to app development, running your app on an iOS simulator is an appealing option since it provides a lot of capabilities without requiring any physical hardware. However, simulating hardware components such as the camera, GPS, or even accelerometer functions often leads to significant discrepancies between how your app behaves on a simulator versus on a real device. For example, if your app relies on the camera's capabilities, testing on an actual device is absolutely necessary to understand how users will experience your app in a real-world situation. The figure titled Importance of Testing Methods in App Development displays a pie chart dividing testing emphasis between two categories: simulator testing at 30% and real device testing at 70%. This breakdown highlights a clear pattern. The majority of testing importance, 70%, lies with real device testing, while simulators account for a smaller but non-negligible portion, 30%. From this data, we can conclude that while simulators remain valuable for early-stage development, automated unit tests, and quick iterations, the dominant share allocated to real device testing signifies that most critical validation, especially for hardware-dependent features, performance profiling, network variability, and user interaction, must be performed on actual devices. The labeled axes testing methods and importance percent reinforce that the chart measures relative priority rather than absolute effort. Thus, teams should translate the 70-30 priority into planning by allocating more hands-on device testing time, device variety in test matrices, and resources, e.g. device farms, manual QA on physical units, to capture issues that simulators will likely miss. In short, the visual emphasizes prioritizing real device validation while still leveraging simulators for fast, early feedback. First up, let's get your device ready for development. Make sure that your iOS device is updated to the latest version of iOS, as compatibility issues can arise with outdated software. After making sure your device is ready, you need to register it with Apple. This is done through your developer account. You first connect the device to your computer and open Xcode. In Xcode, navigate to the window menu and select Devices and Simulators. Once you see your device listed there, you can select it. However, before you can deploy any applications, you need to add this device to your Apple developer account. To do this, go to the Apple developer website and log in to your account. Navigate to Certificates, Identifiers, and Profiles, then select Devices. You can add a new device here using its unique UDID, which you can find in Xcode when selecting your device. Now let's take a look at how to implement a simple network service using Kotlin and the Ktor client, which is essential for making API requests in our app. This code defines a network service class that encapsulates the functionality required to fetch data from a specified API URL. Inside this class, we create an instance of the HTTP client, which is the core component of the Ktor library responsible for handling HTTP requests. The fetch data function is a suspend function, indicating that it can perform long-running operations without blocking the main thread, thus keeping the user interface responsive. This function takes an API URL parameter, which represents the endpoint from which we want to retrieve data. When fetch data is called, it makes a GET request to the specified API URL and returns the response as a string. By utilizing this approach, we can effectively test our app's networking capabilities directly on an iOS device, ensuring it handles real-world conditions, such as varying network speeds and connectivity issues. This hands-on testing is critical to validating the performance and reliability of our networking features before the app reaches users. Now that your app is set up, let's discuss the benefits of testing on an actual device. Real devices provide feedback that a simulator cannot give, such as GPS accuracy, network performance, and actual user interaction with various gestures and touch inputs. For instance, if you are building a navigation app, testing it on a real device is essential. Simulating GPS will not showcase the performance in real time and can lead to unexpected behavior in your app's logic. Moreover, device testing helps you identify performance bottlenecks, such as memory usage or battery consumption issues that might not appear in the simulator. It allows developers to ensure that their apps follow best practices in particular hardware constraints and usage patterns. Now let's see how we can implement haptic feedback in our application. The code defines a function called provide haptic feedback, which takes a vibrator object and a duration parameter specifying how long the vibration should last. In the function, we first check if the device has a vibrator using the hasVibrator method. This is essential because not all devices support vibration, and we want to ensure that our app handles such cases gracefully. If the device does indeed have a vibrator, we proceed to create a vibration effect using vibration effect create one shot, which takes the specified duration and a default amplitude for the vibration. Finally, we invoke the vibrate method on the vibrator object, passing in the effect we've just created. By testing this implementation on a real device, we can assess how effectively the haptic feedback engages users in response to events, and refine the user experience based on their feedback and interactions with the vibration feature. This not only enhances engagement, but also adds a tactile dimension to user interactions in the app. When developing apps that interact with real-time data such as weather, stock prices, or social media feeds, it's crucial to test them in different conditions and environments. Install your app on various devices to collect feedback on how it performs, particularly when it comes to battery consumption and responsiveness. Another way to enhance your understanding of your app's behavior is to utilize analytics tools and crash report services. Implementing frameworks like Firebase Crashlytics allows you to monitor how your app performs on real devices and gives you valuable insights into potential issues that arise outside the simulator's controlled environment. Now let's take a look at how we can implement Face ID authentication in our application. This code utilizes the Biometric Prompt API, which simplifies the process of integrating biometric authentication into your app. First, we import necessary classes like context and biometric prompt, which will help us interact with the device's biometric features. The authenticate user function takes a context parameter that provides the app's current state and environment, which is essential for utilizing system resources effectively. Within the function, we create an instance of biometric prompt, passing in the context along with an executor and a callback. The executor handles background tasks, allowing the authentication process to occur without blocking the main thread. Next, we construct a promptinfo object using the builder pattern. This object specifies the title and subtitle of the authentication prompt, as well as a negative button labeled cancel, offering users a clear way to exit the authentication attempt. Finally, the biometric prompt authenticate method is invoked with the constructed promptinfo, initiating the authentication flow. This approach ensures a streamlined and user-friendly experience, allowing us to leverage biometric security effectively in our app. By testing this code on devices that support Face ID, we can evaluate both the workflow and the responsiveness of the user interface, leading to a seamless user experience. In conclusion, while simulators offer valuable insights during development, nothing can replace the thorough testing that comes with deploying your app on actual iOS devices. By validating your application in a real-world environment, you can better understand how users will experience your app, allowing you to catch and fix issues before they reach your customer base. Your app's reliability, performance, and quality directly depend on this essential step of testing. So as we wrapped up this discussion, remember to leverage the full power of your device, test thoroughly, and gain invaluable insights that a simulator simply cannot provide. Keep experimenting and refining your app using these tips, and you'll elevate your development game like a pro in no time. Overall, equip yourself with the tools, insights, and correct processes to ensure that your app is incredibly refined by the time it reaches users. Trust the device, test effectively, and watch your app flourish in the competitive landscape of app stores. Understanding developer mode requirements for iOS development is crucial for anyone looking to build applications in Apple's ecosystem. Developer mode was introduced by Apple during their Worldwide Developers Conference in 2022, and it plays a pivotal role in installing, running, and debugging apps on devices running iOS 16 or greater. So far, we learned the importance of testing apps on actual iOS devices to ensure they perform optimally in real-world environments. We discussed the setup process for deploying apps to devices, including managing developer certificates and provisioning profiles. Additionally, we explored the benefits of device testing, such as identifying performance issues and ensuring adherence to Apple's human interface guidelines. This lays the groundwork for implementing device-specific features and highlights that thorough testing on real hardware is crucial for app reliability and quality. Now we will dive into developer mode requirements, why they matter, and how you can set them up effectively to enhance your iOS development workflow. The donut chart titled Testing Pyramid in iOS Development shows a clear distribution of testing effort across three categories: unit tests 70%, integration tests 20%, and UI tests 10%. The visual emphasizes that the largest portion of testing effort is allocated to unit tests. The green slice occupies the majority of the circle and is slightly separated from the rest, which draws attention to its dominant role. Integration tests are represented by an orange slice that is noticeably smaller, indicating a moderate allocation for verifying interactions between modules and subsystems. UI tests appear as the smallest red slice, reflecting a minimal but targeted investment in end-to-end verification of user-facing flows. The chart's labels testing types and axis label percentage distribution reinforce that these are proportional allocations rather than absolute counts. From this distribution, you can conclude that a recommended testing strategy prioritizes fast, numerous unit tests to validate business logic and lower-level components, uses a smaller but meaningful set of integration tests to ensure components work together, and reserves a limited number of UI tests for critical user journeys that must be validated on real devices. This pattern supports efficient test suites that are quicker to run and maintain, while still covering system-level and UI risks where they matter most. First, let's clarify what developer mode is. Essentially, it's a setting on iOS devices that allows developers to install apps directly from Xcode, debug those apps, and utilize various development features that regular users might not need or want. With the introduction of developer mode, Apple aimed to streamline the process of testing applications, but this comes with specific prerequisites and configuration steps that developers must follow. It's a bit like giving your iOS device a VIP pass to the developers club. To enable developer mode, you'll first need to get your hands on a compatible device running iOS 16 or later. Making sure you have a recent version of Xcode installed is also a must. You can download the latest version of Xcode from the Mac App Store. Once you've ensured that your device is ready and Xcode is up and running, you will follow the steps to enable developer mode, which I'll guide you through next. To enable developer mode, proceed with the following steps. 1. Connect your iOS device to your Mac using a USB cable. 2. Open Xcode. If this is your first time connecting the device, Xcode will likely prompt you to register your iOS device. Simply follow the on-screen instructions to do so. 3. On your iOS device, navigate to *settings ***, then scroll down and tap on Privacy and Security ***. 4. In the Privacy and Security menu, find and tap on Developer Mode ***. 5. Toggle the switch to turn on Developer Mode. You'll be prompted with a confirmation dialog to enable this feature. 6. Once confirmed, your device will restart, and upon reboot, you'll see another dialog asking for confirmation to enable developer mode. Confirm this, and voila, your device is now ready for development. With developer mode enabled, you're set up to install apps directly to the device. This is important because the regular app installation process through the App Store does not allow for testing and debugging in the same way that a direct deployment from Xcode does. Now let's configure the project to use Kotlin multi-platform for our iOS app. We begin by defining the Kotlin configuration in our build Gradle KTS file. Here we specify that we want to target iOS by setting up the binaries for our framework, giving it a base name, shared. This framework will allow us to share code between our Kotlin modules and the iOS app. Next, we detail our source sets, defining IO's main where we will specify our dependencies. At this point, it's essential to ensure that any necessary Kotlin library dependencies are included, enabling the cross-platform capabilities of our app. Now let's implement the business logic in Kotlin by creating a simple function in a file named greeting.kt. This function greet returns a string that simply says hello Kotlin. This encapsulates our basic greeting logic, which we can easily access from our SwiftUI interface later. Next, we'll take a look at how to build the user interface with SwiftUI. We will create a content view structure that utilizes the greeting we defined earlier. Inside the body of this view, we utilize the text element to display the greeting message, applying padding and a large title font. As we move forward, we will also set up the main application structure to load our content view, effectively linking our Kotlin logic with the iOS presentation layer. In the code above, we are importing the shared module where our Kotlin code resides. The content view displays the greeting message by calling the greet function we created earlier. This integration shows the ability to blend iOS development with Kotlin, making it an exciting prospect for developers familiar with the language. Now it's time to run this app on your device. Ensure that your iOS device is selected in Xcode's Target Device dropdown. Click on the Run button, and if everything is set up correctly, the app should build and deploy to your device seamlessly, thanks to the developer mode we enabled earlier. Let's pause for a moment and appreciate the power of developer mode. It not only allows for easier app installation and testing on real devices, but also lets you run debug sessions and utilize profiling tools directly. You can actively debug your application, inspect memory usage, view runtime errors, and determine performance bottlenecks, giving you the insights needed to improve your app's quality. To illustrate this point further, consider a situation where you are debugging a particular screen that occasionally crashes when a user clicks a button. With developer mode, you can set breakpoints directly in Xcode, allowing you to investigate the app's state at various execution points. This makes it easier to pinpoint issues compared to relying solely on testing through the simulator. Now let's take a look at a simple Kotlin function that will help us understand how to return a greeting message within our iOS app. Here, we define a function named greet, which is designed to return a string. This function encapsulates the logic required to generate the message "Hello, Kotlin." By placing the return statement inside the function, we ensure that whenever greet is called, it will deliver this friendly greeting. This is particularly useful as we can invoke this function from our SwiftUI interface, ultimately allowing us to display the greeting in our app. Next, let's consider where we might place a breakpoint in our function. By adding a comment indicating where to place the breakpoint, we prepare for debugging sessions. This enables us to pause execution when the function runs, allowing us to investigate variables and the flow of execution in detail. Seeing how the app reacts right before returning the greeting can unearth valuable insights into the program's behavior. Overall, this simple function serves as a building block in our app, showcasing how we can integrate Kotlin logic within an iOS environment. Another fantastic feature available through developer mode is memory debugging. The memory graph debugger can help you visualize the memory usage of your app at a specific point in time. Should you notice unexpected memory usage or potential leaks, this tool will help you identify retained cycles or objects that aren't being released. While your app is running in Xcode, you can access the memory graph by clicking on the memory icon in the debug area. This opens a visual representation of all current objects in memory, as well as their relationships. Pinpointing retained objects becomes a breeze, ultimately pointing you toward possible optimizations. As we wrap up our deep dive into developer mode requirements for iOS development, remember that this feature is designed to make the development process smoother and more integrated. It bridges the gap between coding on your Mac and experiencing your app in the real world on your device. By enabling developer mode, you're empowering yourself to efficiently test, debug, and optimize your applications. So far, we've discussed what developer mode is, why it's essential, and how to enable it on your iOS device. We explored creating a simple Kotlin multi-platform app, integrating it seamlessly with iOS, and utilized Xcode for debugging and optimization. From here, your next steps might involve diving deeper into more complex app functionalities, but with developer mode, you'll be more prepared for the challenges ahead. In conclusion, developer mode is not just another feature. It's your industrial-strength toolkit that opens up a wealth of possibilities for building high-quality iOS applications. Embrace it, explore, and happy coding. Congratulations, you have successfully run your app on an actual iOS device. That's an exciting milestone in your app development journey. Today, we're going to build upon that foundation and explore how to advance your iOS application's features using Xcode, while integrating Kotlin multi-platform and SwiftUI to create a seamless user experience. So far, we learned the significance of developer mode in iOS development and its role in installing and debugging apps directly from Xcode. We explored the steps to enable developer mode and discussed how it allows real-time testing, debugging, and optimization of applications on actual devices. Additionally, we looked at creating a simple iOS app using Kotlin multi-platform, integrating it with SwiftUI, and utilizing Xcode's debugging tools to enhance app quality. Moving forward, we will dive deeper into advanced app functionalities and further leverage the capabilities of developer mode. Now let's implement a simple user interface using SwiftUI that will display a welcoming message and allow users to interact with it. We begin by defining a content view struct that conforms to the view protocol, which is essential in SwiftUI for building user interfaces. Inside this struct, we declare a state property called greeting using the @state property wrapper, initialized with a welcoming message. This allows us to track changes to the greeting message and update the UI accordingly. Next, let's create a body property that describes the UI layout. Inside this body, we utilize a vertical stack, VStack, to arrange our elements vertically. The first element is a text view that displays the current value of the greeting variable, styled with a large font and some padding for better presentation. Following this, we introduce a button labeled Say Hello. When this button is clicked, it triggers an action that updates the greeting to a personalized message, showcasing how state management in SwiftUI allows dynamic updates of the UI by refreshing whenever the state changes. This interactive functionality enhances user engagement with the app, making it more lively and personalized. Now let's implement a basic navigation structure using SwiftUI's navigation view and navigation link. In this setup, we begin by embedding our content in a navigation view, which serves as a container that facilitates navigation between different views in the app. Inside the navigation view, we create a vertical stack, using VStack to arrange our UI elements vertically. Next, we utilize a navigation link to enable the transition to a new view, Info View, whenever the user taps on the Learn More button. This link not only triggers navigation but encapsulates a text element that visually indicates the action. We style this text with a bold font, padding, background color, and corner radius to enhance its appearance, making it clear that it is interactive. Finally, we conclude the navigation setup by defining the title of the navigation bar with navigation title, Home, which helps users understand the context of the current screen and improves overall user experience. Transitioning to Info View, we display more information about the app, offering an engaging way for users to interact with additional content. This seamless navigation approach enriches the app's usability. Now that we've defined our data model, let's see how we can implement this in our iOS app using SwiftUI. We start by creating a struct named ItemListView, which serves as the main view for displaying our list of items. This struct takes an array of item objects as its input. Within the body of this view, we use SwiftUI's list component to present the items dynamically. The list enables us to create an efficient scrolling interface displaying each item in a vertical format. Here we ensure that each item is identifiable by using the item's id property, which helps SwiftUI recognize and optimize the views. For each item in the list, we implement a vertical stack, VStack, to organize the layout. This stack allows us to display the item's name prominently as a headline and its description in a more subdued font below it. With this setup, users can easily browse through the available items, providing a smooth and engaging experience. This approach exemplifies how we can effectively marry Kotlin multi-platform's data capability with SwiftUI's UI elements to create a cohesive app interface. The figure titled Journal Entry Ratings Over Time is a bar chart showing 3 dated entries on the x-axis, 2020-40-829, 2020-40-830, 2020-40-901, and a y-axis labeled Rating 05 that defines the rating scale. The leftmost bar for 2020-40-829 reaches the top value of 5, is colored green, and is annotated Good Day, indicating the highest positive rating in this short series. The middle bar for 2020-40-830 sits at 0, is colored red, and is annotated Bad Day, showing a complete drop to the lowest possible rating on that date. The rightmost bar for 2020-40-901 rises to 3, is colored orange, and is annotated OK Day, representing a partial recovery to a mid-level rating. Visually, the pattern is a sharp fall from a peak 5 to a trough 0 over one day, followed by a rebound to an intermediate value 3 2 days later. The color coding green right arrow red right arrow orange, the bar heights relative to the 0-5 scale, and the textual annotations together make it immediately clear which days were most positive, most negative, and neutral in between. Now let's implement a simple state management solution using SwiftUI to efficiently fetch and display data. We start by defining an ItemViewModel class that conforms to the Observable Object Protocol. This allows us to use the @published property wrapper, marking an array of item objects, items, for automatic updates to any observing views when its content changes. To simulate data fetching, we create the fetchItems method, which mimics a network call using DispatchQueue. This method uses a syncafter to delay the assignment of items with data from a placeholder function getItems, simulating retrieving items from a remote source. Next, we define ItemListView, a SwiftUI view that observes our ItemViewModel. By declaring ViewModel with @observedObject, the view lessens for any changes to items. Inside the view's body, we utilize a list to display each item's name and description, ensuring a well-structured UI. Finally, using onAppear, we trigger the fetch process when the view appears, integrating smooth data operations seamlessly within the user interface. This structure helps keep data and UI synchronized effortlessly, leading to a fluid user experience. Now let's see how we can implement error handling within our data fetching functionality. In this example, we simulate a network fetch by offloading the task to a background thread using dispatch queue global async. This ensures that the main thread remains responsive while we attempt to retrieve data. Within this async block, we introduce a do-catch statement to handle potential errors gracefully. As a demonstration, we use bool random to simulate a scenario where an error may occur. If it evaluates to true, we throw an NS error, which mimics a failure in fetching items. This helps in understanding how to alert users when things don't go as planned. Upon a successful fetch, we switch back to the main thread to update our UI with the retrieved items. However, if an error occurs, we catch it and output an appropriate message to the console. This is where you can adapt the error handling to show alerts or updates in the user interface. By implementing this approach, we enhance user experience by being transparent about errors and maintaining a smooth operation within our application. Wrapping up, now that we've gone through how to build a simple iOS app with navigation, data models, UI enhancements, state management, and error handling, you've got a solid foundation on which to build and scale your applications further. The design principles and frameworks we discussed today, especially the prowess of SwiftUI in combination with Kotlin multi-platform, empower you to create high-performance applications that can serve users on multiple platforms efficiently. Next time, we'll delve into integrating external libraries, advanced UI techniques, and optimizing our app performance even more. You're doing great, and I can't wait to see where your coding journey takes you. Welcome back, everyone. Today, we're diving into the exciting world of Swift programming concepts, specifically tailored for iOS development. If you're looking to enhance your app skills, you've come to the right place. So far, we learned about the importance of enhancing app user interfaces using SwiftUI, focusing on its simplicity and adaptability. We explored how to implement navigation with Navigation View and Navigation Link, allowing users to transition between views seamlessly. Additionally, we discussed managing data with Kotlin multi-platform, creating a data model, and leveraging state management in SwiftUI for effective UI updates. Finally, we covered error handling techniques to improve app robustness and user experience. Now, we will talk about the Swift language itself and learn how simple values and types are used in Swift programming. Firstly, let's understand what Swift is all about. Swift is a powerful and intuitive programming language created by Apple for building apps on iOS, macOS, watchOS, and tvOS. It emphasizes safety and performance, making app development more enjoyable and less error-prone. As a programmer, you'll find that Swift has a clean and expressive syntax that allows you to write code that is both concise and readable. The displayed figure, titled Understanding Key Swift Programming Concepts for iOS Development, is a bar chart that quantifies the relative importance of 5 core Swift topics: data types 25%, control flow 30%, functions 20%, optionals 15%, and collections 10%. The x-axis lists the concepts and the y-axis shows importance as a percentage. Each bar has its percentage label on top for immediate comparison. Key patterns are clear. Control flow is emphasized most at 30%, indicating that decision-making and loop constructs are a primary focus. Data types follows at 25%, highlighting the foundational role of types in Swift. Functions sit in the middle at 20%, underscoring their role in structuring and reusing code. Optionals are shown at 15%, signaling the importance of safe handling of absent values. And collections appear at 10%, still necessary but given comparatively less emphasis. Because the values sum to 100%, the chart presents a prioritized view of topics to learn first. Start with control flow and data types, then move to functions, and ensure you address optionals and collections as supporting concepts. This visual ordering aligns with the lesson flow and helps set learning priorities for building robust iOS apps. Now let's explore how we can declare variables and constants in Swift. In the given example, we begin by declaring a variable named age, specifying its type as int and assigning it the value of 30. This highlights the flexibility of Swift, allowing you to define a variable that will hold an integer. Next, we introduce two constants, pi, which is defined as a float and initialized to 314, and greeting, a string that holds a friendly message. Constants are immutable, meaning their values cannot be changed once set, promoting safer code. Swift is also intelligent enough to infer variable types. For instance, when we declare the variable name and assign it the string John Doe without explicitly stating its type, Swift automatically understands that name is a string. This feature not only simplifies the code but also enhances readability. It's a testament to Swift's design, allowing developers to write clean and efficient code while focusing on the logic rather than overwhelming type declarations. Now let's explore Swift's type safety through a simple example. In this snippet, we first declare a variable named score of type int and assign it a value of 100. This clearly establishes that score is intended to hold an integer value. If we attempt to assign a string to this integer variable, Swift provides an immediate feedback by throwing a compilation error. This feature of type safety is crucial, as it helps developers avoid accidental type mismatches and ensures that data types are consistent throughout the code, leading to fewer bugs and a more reliable code base. Next, we will work with arrays, which are essential for storing multiple values. Here we declare an array called fruits that holds several string values representing different types of fruits. We then use the append method to add orange to our existing list. Swift's arrays are zero-indexed, meaning the first fruit, apple, is accessed with index 0, and if you want to retrieve banana, you reference it with index 1. By demonstrating this array manipulation, we show how easily collections can be managed in Swift, enhancing flexibility in handling groups of related data. Next, we will explore how to create and manipulate dictionaries in Swift. A dictionary is a powerful collection type that allows us to store data in key-value pairs, making it easy to retrieve values by their unique identifiers. Now let's see how we can implement a simple dictionary called student grades. In this case, we define a dictionary that maps student names, represented as strings, to their corresponding grades, also stored as strings. We initialize the dictionary with 3 entries: Alice with an A, Bob with a B, and Charlie with a C. This illustrates how straightforward it is to associate particular keys with values. Importantly, dictionaries in Swift are unordered collections, meaning the key-value pairs do not maintain any specific order as you add them. Next, we will enhance our dictionary by adding a new entry for a student named Diana, assigning her a grade of A. This demonstrates how flexible dictionaries are, since we can update them on the fly by simply using the key. Finally, when we print the student grades dictionary, we'll see all the entries, including the newly added one. This showcases the dynamic capabilities of dictionaries, making them integral to data storage and retrieval in your Swift applications. Now let's take a look at how we can iterate through the fruits array. In this example, we use a for loop, which is a fundamental construct in Swift for repeating an action a specific number of times or iterating over items in a collection. The loop begins by declaring a variable fruit that takes on each value in the fruits array sequentially. Inside the loop, we use the print function to output a message indicating our preference for each fruit. This simple structure not only showcases how easy and efficient it is to access each element, but also highlights Swift's ability to express repeated actions clearly and concisely. Next, we will write the code to iterate through a dictionary called student grades. Here, we use another for loop, but this time we unpack each key-value pair using tuple syntax. The variables student and grade represent the key and value from the dictionary, respectively. As we loop through, the code prints each student's name followed by the grade they received. This method illustrates how dictionaries allow access to both keys and values seamlessly during iteration, providing a straightforward way to handle data in collections beyond simple lists. Now let's take a look at how to define and work with optionals in Swift. Optionals are crucial when dealing with variables that may not have a value. In our example, we declare a variable called name of type string, indicating that it can hold a string value or be nil. Initially, we assign John to name, but later we set it to nil, illustrating how the variable can toggle between having a value and being empty. Next, we need to safely access this optional variable to avoid runtime crashes if we try to use a nil value. This is where optional binding comes into play. By using iflet, we check if name contains a valid string. If it does, we assign that value to unwrapped name, allowing us to use it confidently within the scope of the if statement. If name is nil, the else clause executes, informing us that the variable has no assigned value. This approach emphasizes Swift's safety features, enabling you to write robust and error-free code. Now let's see how we can implement an if statement in Swift to make decisions based on conditions. In our example, we start by declaring a variable score with a value of 85, which represents a student's score. The if statement evaluates the score and determines which block of code to execute based on defined conditions. First, it checks if the score is greater than or equal to 90. If true, it prints you got an A, indicating exceptional performance. If that condition isn't met, the code checks whether the score is 80 or higher, printing you got a B. If so, which signifies a good achievement. Finally, if neither condition applies, the else block executes, printing keep trying, to encourage the student to improve. This structure illustrates how control flow statements like if can be used to create dynamic responses in our applications, enhancing user interaction and feedback. By leveraging conditionals in this way, you can tailor the application's behavior according to the user's inputs or actions, making your app feel more responsive and engaging. Next, we will explore the switch statement, which offers a structured way of handling multiple potential values for a variable. In our example, we start by defining a variable called grade, assigning it the value b. The switch statement then evaluates this variable against several predefined cases. When the switch executes, it will match the grade to one of the cases, a B or C. If a match is found, Swift runs the corresponding block of code. In this scenario, since our variable holds the value B, the program outputs a friendly message. Good job. This illustrates how quickly a switch can simplify code that might otherwise require numerous if statements. Additionally, the default case serves as a catch-all for any values that don't match the specified cases. It ensures that even unmatched conditions are handled gracefully, prompting users to keep trying, if none of the cases are satisfied. This structure makes switch statements highly efficient and easy to manage, particularly when dealing with multiple discrete values, enhancing the readability and maintainability of your code. Now let's see how we can define a simple function that adds two integers in Swift. The function is named addNumbers, and it takes two parameters, both of which are integers. Notice that we use underscores before the parameter names, enabling us to call the function without needing to label the parameters during the function call. This can make the code cleaner and easier to read in many contexts. Inside the function body, we simply return the sum of the two parameters. The return type of the function is specified as int, indicating that it will provide an integer output. After defining the function, we invoke it by passing two integer values, 5 and 10. The result of the addition is stored in a constant named result. Finally, we use the print function to display the output, which shows the user what the sum is. This exemplifies how functions in Swift can encapsulate logic for reusability and clarity, making your code more organized and efficient. Functions like this lay the groundwork for more complex operations and logic as you progress in Swift programming. Now let's take a look at closures in Swift, which are a powerful way to encapsulate functionality. In this example, we define a closure called addClosure that takes two integer parameters, a and b, and returns their sum. The closure is defined using curly braces, and the parameters are specified along with their types, followed by an arrow indicating the return type. This structure allows us to neatly package the addition operation into a self-contained unit that can be reused throughout our code. To utilize the closure, we then call addClosure with two integers, 10 and 20, which demonstrates how we can execute this block of functionality. The result of this operation, stored in a variable named sum, is then printed out. This method of defining operations as closures is particularly beneficial in scenarios such as asynchronous programming, where it allows us to define concise completion handlers that execute once a task is completed. Understanding closures is essential for writing efficient and modular Swift code, enabling a flexible approach to code organization and reuse. To wrap things up, we've covered a lot in this session. We explored basic data types, collection types like arrays and dictionaries, optionals for safe data handling, control flow statements for dynamic decision-making, and functions as reusable code blocks. Each of these concepts is critical as you develop your iOS applications using Swift. Take time to practice these concepts by writing small programs or snippets. Apply them in real-world projects as you develop your apps. Understanding Swift programming concepts will give you the foundation needed for successful iOS development, opening new doors to achieve your app-building dreams. Thanks for tuning in, and I look forward to seeing you in the next video, where we'll dive deeper into more advanced Swift programming techniques. Happy coding! Now let's dive into mastering Xcode for iOS app development. Congratulations, you have successfully run your app on an actual iOS device. This is a significant milestone in your journey as a developer. Today, we will go through the essential aspects of Xcode and how you can use it to build robust iOS applications. So far, we learned about enhancing user interfaces with SwiftUI, focusing on navigation, state management, and data management using Kotlin multi-platform. We discussed the basics of Swift, including its type safety, essential data types, and control flow statements. In our current lesson, we will be exploring Xcode, its environment, and how to effectively manage your iOS app development workflow. Xcode is Apple's integrated development environment, IDE for macOS, designed specifically for developing iOS applications. Its interface allows developers to manage all aspects of iOS app development from a single location, giving you access to coding, debugging, and user interface design tools. When you open Xcode, you'll notice a streamlined workspace, including the navigator, editor, and utility areas, each serving its unique purpose. Let's start with the Project Navigator, which is located on the left side of your screen. This is where all your project files are organized. You can think of it as the file manager for your app. Whether it's your Swift files, image assets, or storyboards, everything is easily accessible here. To create a new file, simply right-click your project name, hover over New File, and select the type of file you want to create, like a Swift file or a storyboard. Figure 1 displays a horizontal bar chart titled Key Aspects of iOS App Development in Xcode, with the x-axis labeled Importance % and the y-axis listing 5 concepts: project management, interface design, debugging, version control, and testing. Each bar is color-coded and annotated with its numeric value: project management at 30, interface design at 25, debugging at 20, version control at 15, and testing at 10. The chart uses a scale from 0 to 40 on the x-axis and includes grid lines along the x-axis to make the percentage differences clear. Key patterns visible are the descending order of emphasis from project management down to testing, a relatively steep drop from the top two priorities, 30% and 25%, to the mid-level debugging, 20%, and smaller increments between version control, 15%, and testing, 10%. From this distribution, we can conclude that planning and interface work are being given the largest share of importance. Debugging retains a substantial but smaller focus, and version control and testing receive the least allocated importance. In the context of our lesson, these proportions suggest prioritizing time for project organization and interface design within Xcode, e.g., using Interface Builder, Project Navigator organization, while also explicitly recommending that developers deliberately allocate effort to version control workflows and automated tests to avoid underinvesting in those critical areas. Now let's implement a simple Swift function to get familiar with coding in Xcode. We begin by importing the foundation framework, which provides essential functionalities like data manipulation and system services, giving our code access to numerous useful features. Next, we define a function called greet. This function contains one action to print the message "Hello World" to the console. This action is a staple for learning programming languages as it demonstrates the basics of output and function execution. After defining our function, we immediately call it by writing greet. This triggers the execution of the code within the function, leading to the output appearing in the console. By running this code in Xcode, you will see "Hello World" displayed, confirming that our function executed correctly. This exercise not only introduces you to function syntax and the print statement within Swift, but also lays the groundwork for more complex functions and interactions as we continue to explore Xcode and iOS app development in future lessons. Next, let's talk about user interface design within Xcode. One of the most powerful features of Xcode is Interface Builder. This tool provides a visual way to construct your user interface using storyboards and SwiftUI. You can drag and drop UI elements onto your canvas while simultaneously seeing how they will appear on an iOS device. Let's say you want to add a button that will trigger a greeting message later. Drag a UI button from the object library into your view controller. You can then set its properties in the Attributes Inspector on the right side of Xcode. Now, let's create an outlet for this button so we can reference it in our code. Now let's take a look at how to create a connection to our UI button in the ViewController class. First, we define an IBOutlet property called greetButton, which is of type UIButton and marked with the @IBOutlet attribute. This connection allows us to reference the button from our code, enabling us to programmatically manipulate its properties or respond to user interactions. The IBOutlet property is crucial because it bridges the user interface element in the storyboard in our Swift code, ensuring they can communicate effectively. Following the property declaration, we have the viewDidLoad method, which is part of the UI view controller lifecycle. This method is called after the view has been loaded into memory, making it the perfect place to perform any additional setup once our view is ready. In this case, it currently has no additional functionality, but this is where we could configure the button's appearance or initial state if needed. Understanding this connection lays the foundation for adding actions to our button, allowing us to create engaging and interactive user experiences in our app. Now let's implement the following action method to handle the button tap. The @IBAction keyword is used to link this method to a user interface element in our storyboard, in this case, the UI button we created earlier. The method name greetButtonTapped clearly indicates its purpose. It will be triggered when the button is pressed. Inside this method, we have a simple line of code that prints the message "button was tapped" to the console. This demonstrates how actions can respond to user interactions in real time. By using the sender UIButton parameter, we can access the button that triggered the action, opening up the possibility for additional logic based on which button was pressed, should we have multiple buttons. In essence, this method serves as a foundation for implementing more complex user interactions, such as altering UI elements, performing calculations, or fetching data. As you build your app further, this action can be expanded to include more robust functionality, giving a responsive experience to the users interacting with the app. Another critical aspect of using Xcode is debugging. When developing your app, you might run into issues or bugs that need diagnosing. Xcode comes equipped with an excellent debugging toolset which is invaluable for developers. When you run your app, make sure you utilize breakpoints. To set a breakpoint, click on the gutter next to the line of code where you want the execution to pause. This way, when you run your app, you can inspect variables in the debug area and examine the flow of your code. For example, adding a breakpoint inside the greet button tapped function will allow you to check the values of any variables you might want to inspect at that moment. You can hover over them in the editor, and Xcode will give you a pop-up with their current state. If you find that your app is crashing, don't panic. Xcode provides a powerful tool called the Debug Navigator, which shows the call stack and memory usage among other things. By analyzing the stack, you can often pinpoint where the issue occurred. Errors will also appear in the Issue Navigator. Clicking on an error will take you to the corresponding line of code, allowing you to address issues directly. Understanding how to navigate and utilize these debugging tools is vital. It not only improves your efficiency, but also helps to foster better coding practices as you learn to identify and fix issues within your code effectively. Now, let's briefly touch on the version control system integrated within Xcode. Using Git effectively in your iOS development can significantly enhance your collaboration process. Xcode has built-in support for Git repositories. You can initialize a Git repository from the source control menu. Once set up, it's easy to commit changes, create branches, and manage your project's history. A best practice is to commit often with clear messages explaining what changes were made. This habit will serve you well as your project grows more complex. To commit your changes, navigate to the source control menu and select Commit. You'll see a list of modified files with options to stage them. Add a message describing the commit, such as added button action for greeting, and hit the commit button. Next, we will write a simple unit test for our greet function to ensure it behaves as intended. In this code, we begin by importing the Xcode test framework, which provides tools for testing in Xcode. We then declare a test case class inheriting from Xcode test case. This allows us to structure our tests methodically. Inside the class, we define a method named testGreet, which acts as our actual test. Here we establish what we expect the output of the greet function to be. This is our expected result, hello world. We then call the greet function to capture its output in a variable named actualOutput. To verify that our greet function works correctly, we use the xct_assert function, which compares the expected output with the actual output. If they match, the test passes. If they don't, it fails. This testing process underscores the importance of validating functionality within our applications, helping us catch bugs early and ensuring our code adheres to expected behaviors. By implementing such tests, we contribute to the robustness and reliability of our iOS applications. In conclusion, mastering Xcode is key to becoming a proficient iOS developer. By understanding its environment, seamlessly designing user interfaces, managing debugging with precision, utilizing Git version control, and writing comprehensive tests, you position yourself for success as you embark on more complex projects. Congratulations on taking significant strides in your app development journey. Keep practicing and exploring different features Xcode offers, and you'll soon be creating impressive applications that cater to users' needs. Congratulations, you have successfully run your app on an actual iOS device. This is an incredible milestone in your journey as an iOS developer, and it opens up a whole new realm of possibilities for your app development skills. Today, we will dive deeper into mastering Xcode and essential iOS development techniques that can enhance your workflow and expand your capabilities as a developer. So far, we've learned about the capabilities of Xcode as an integrated development environment for iOS app development, focusing on project organization and user interface design using tools like Interface Builder. We've explored creating and managing Swift files, adding interactive elements like buttons, and handling user inputs with actions. Additionally, we discussed the importance of debugging, version control with Git, and the need for testing to ensure application reliability. This comprehensive understanding of Xcode prepares you for more complex app development challenges ahead. Now we will cover advanced features and techniques that will take your iOS development skills to the next level. Now let's see how we can implement an image view in our application to display images stored in our asset catalog. First, we create an instance of UI image view, which is a view specifically designed to show images in the interface. Once we have our image view set up, we load an image by calling the UI image named initializer, where we pass the name of the image file we want to display, in this case, my image. This makes it simple to access our images by reference, allowing for clean and manageable code. It's important to note that using the asset catalog means our app can automatically adjust and load the appropriate image resolutions for different devices, ensuring optimal display quality. By organizing resources this way, we enhance our project structure and make it easier to manage visual elements across various device screen sizes. Keeping images in the asset catalog not only aids in scalability, but also fosters a more efficient workflow, as you can easily add, remove, or update your assets without altering much of the code. Now let's implement a custom view by creating a circular progress view that visually represents progress via a circular arc. In this class, we define a property called progress, which is of type CG_float. Whenever this property is modified, the didSetObserver is triggered, calling setNeedsDisplay to indicate that the view needs to be redrawn, ensuring that changes to progress are reflected visually. Next, we will override the draw method to handle the actual rendering of the progress arc. Within this method, we first obtain the current graphics context, which is essential for drawing. We set a line width and color here using a blue stroke. The drawing occurs around a circular path centered within the view's bounds, with its radius calculated based on the view's size. The drawing starts from the top of the circle, and the endpoint of the arc is determined by the value of the progress property multiplied by \2\pi\, which defines its extent. Finally, we call strokePath to render the arc onto the view. This custom view can be easily integrated into any view controller, allowing for dynamic visual updates as the progress changes. Now let's see how we can set up a UI button using auto layout to ensure that it adapts well to different screen sizes. First, we create a button of type system and assign it a title that will be displayed to the user. Setting translates auto-resizing mask into constraints to false indicates that we intend to use auto layout for positioning this button instead of the default auto-resizing mask. This is a crucial step because it allows us to define the layout rules programmatically. Next, we add the button as a subview to the main view, making it part of our interface. Then we use NSLayout constraint activate to efficiently create and activate multiple constraints at once. Here we position the button at the center of the screen using its center X anchor and center Y anchor, ensuring it remains in the middle regardless of the device orientation. Additionally, we define fixed width and height for the button, making it easy to interact with. This technique not only provides a clean and responsive design, but also adheres to best practices in iOS development, making sure the layout adjusts seamlessly across various devices. Now let's take a look at how to perform a basic network request using Swift's URL session. First, we define a URL string pointing to our desired API endpoint and initialize a URL object. This is crucial as it tells our application where to fetch the data from. Next, we create a data task, which is the component that actually performs the network request. Inside the closure for this task, we handle the response by checking if the data came through successfully or if there was an error. This is done using a guard statement, ensuring we can safely unwrap the received data. If there's an error, we log a message to the console, which is essential for debugging purposes. When the data is successfully retrieved, we attempt to parse it into a JSON object. This is where the powerful JSON serialization comes into play, allowing us to convert the raw data into a readable format. If the parsing fails, we catch the error and print it, helping us identify potential issues in our data structure. Finally, we call task resume to start the network request, enabling our application to communicate with the API and retrieve the information needed. The figure titled Key Concepts in iOS Development Techniques displays a bar chart with 5 concept categories and their associated importance percentages. Xcode features 25%, advanced techniques 20%, networking 30%, UI testing 15%, and CI/CD 10%. From the data shown, networking is the single largest category at 30%, indicating it is emphasized more than any other concept on this chart. Xcode features follow at 25%, and advanced techniques are next at 20%, forming a mid-range cluster between 20–25% that together represent nearly half of the chart's total importance when combined. UI testing 15% sits below those, and CI/CD 10% is the smallest slice, indicating it is the least weighted topic on the chart. The clear pattern is a descending order from networking down to CI/CD with noticeable gaps. Networking is 5 percentage points higher than Xcode features and 10 points higher than advanced techniques, while CI/CD trails the leader by 20 points. The conclusion drawn from these displayed values is that, according to this visualization, prioritizing networking skills should be a primary focus, followed by solid mastery of Xcode features and advanced techniques, while UI testing and CI/CD, though still important, receive comparatively less emphasis in this set of key concepts. Now let's see how we can implement a UI test using Xcode test in our iOS application. In this test class, we start by importing the Xcode test framework, which provides the necessary tools for writing tests. Within the class, we define a test method named test_button_tap. This method initiates the test by creating an instance of Xcode application, which represents the app being tested, and then launches it. Next, we locate the button we want to interact with, identified by its accessibility label Click Me. By calling the tap method on this button, we simulate a user tapping it. This action triggers any associated behaviors within the app. Following the button tap, we need to verify that the expected outcome occurs. We check for the existence of a label displaying Hello World using the xct_assert function. This assertion ensures that the label appears after the button has been tapped, confirming that the button's functionality is working as intended. UI tests like this not only validate user interactions, but also enhance the reliability of your app across different devices. Now let's see how we can implement a simple sprite scene in our game using SpriteKit. We begin by importing the SpriteKit framework, which gives us access to all the necessary classes and methods for building 2D games. We define a new class called GameScene, which inherits from SKScene. This is a primary building block in SpriteKit, representing a scene in our game environment. Inside this class, we override the didMoveToView method, a crucial lifecycle method that is automatically called when the scene is presented. It's here that we want to set up the initial state of our scene. We create a sprite node using the skSpriteNode class and name the image Spaceship, which we assume has already been added to our asset catalog. By determining the position of this sprite, we place it right at the center of the scene using the dimensions of the scene accessed via sizeWidth and sizeHeight. Finally, we add this sprite to the current scene using addChildSprite, making it visible when the scene loads. This setup is fundamental as it introduces animated objects on the screen, allowing for creative gameplay mechanics to be developed further. Now let's implement the following extension to enhance our UIViewController class. This extension introduces a convenient method, showAlert, which you can use to present alert dialogues in your app with ease. By defining this method within an extension, we're not only keeping our code organized, but also promoting reusability, as we won't have to duplicate this alert logic across different view controllers. The showAlert function takes two parameters, the title and message for the alert. Inside the function, we create an instance of UIAlertController, specifying its title, message, and preferred style as an alert. We then add an action to the alert, using UIAlertAction to define what happens when the user taps the OK button. It simply dismisses the alert. Finally, we call the present method to display the alert on the screen. This approach not only streamlines your alert presentations, but also contributes to better code readability and maintenance, ensuring that your app remains user-friendly and efficient. By employing this best practice, you can deliver a consistent user experience throughout your application. To sum up today's discussion, we explored essential and advanced Xcode features, from managing app resources to creating custom views and handling networking. We also touched on UI testing, game development with SpriteKit, and the importance of coding best practices. With every lesson, you are becoming more proficient in iOS development, enabling you to tackle larger and more complex projects. As you continue to develop your skills, implement what you've learned into your projects. Practicing these techniques will not only solidify your understanding, but also help you create applications that are polished and professional. Keep pushing your limits, keep experimenting, and most importantly, enjoy the creative process of developing amazing apps. Thank you for joining me today, and I look forward to seeing you next time as we delve into even more exciting topics in iOS development. In this final section, we will do a project challenge to apply what we have learned so far. You are tasked with developing a fully functional Android application using Kotlin and Jetpack Compose, integrating best practices in app architecture, UI design, and data management. Choose from engaging concepts such as a task management app, a weather application, or a recipe app, and implement features including a clean and responsive UI adhering to material design principles, the MVVM architecture for better separation of concerns, dependency injection with Coin, and local data persistence using Room. You'll also need to make network calls to fetch data from a public API, ensuring a complete user experience. Your project will be evaluated on code quality, UI/UX design, and the robustness of your features. For detailed project guidelines and resources, find the final project in the GitHub repository linked in the description. Good luck, and let your creativity shine as you bring your unique app concept to life.